stream. And that should be live, and we're also recording. Good. So I will begin. Welcome everybody to this CVPR workshop today, Robust Video Scene Understanding. So to start with, I'm going to talk for 10, maybe 15 minutes, introducing the workshop, the motivation, the lineup, everything exciting that's going to happen, everything that exciting that already has happened to put this workshop together. So let's begin. So why did we want to put this workshop on? What was the original motivation? So let's start with kind of the topics that we are talking about here. So the first topic is kind of the general topic, which is just robust understanding of video in general and scenes in the real world. And the second topic is more specifically tracking and video segmentation. So that's kind of a subtopic of understanding video. So let's talk about the first one, general robust understanding of video and scenes. So computer vision has gotten really good at understanding images, classification, detection, segmentation, depth estimation. However, as soon as you throw in that temporal aspect, as soon as you try and work on video, things become a lot more difficult and there's a lot more work to go. Video has a lot of unique challenges, such as the size of data. One unit of video is just a huge amount of data to deal with. The difficulty of labeling. Labeling video is much harder than labeling images. Dealing with objects in motion, making predictions consistent across frames. And there's more and more challenges that make video just such a harder challenge than just dealing with images. And so as one of the main topics here, we want to move towards algorithms that do that much better. And why do we want to do that? It's because when we deal with video, there's immense opportunity. So there's, dealing with understanding video has applications in robotics, in self-driving, in augmented and virtual reality, in video editing, in content creation, for many industrial applications like optimizing pipelines or monitoring automatically certain industrial applications, etc. So why specifically a focus on tracking and video segmentation? Well, tracking and video segmentation, we kind of use these terms simultaneously here. At least I do use them kind of for the same thing, whereas video segmentation is just a more dense form of tracking with a different representation. So tracking where you require segmentation mask as output. And for me, this is a great representation as a dense understanding of what's happening in video. So it's specifically focusing on objects, but objects are usually the most interesting things because they're moving. You have to deal with the problems of video, such as motion and consistency. And if one can create good solutions for the tracking and video segmentation, this will open up wide opportunities for general video understanding and many different other related tasks to understanding video. And obviously, the specific task has a lot of applications, and many of these could change the world, from self-driving cars to one that recently got pointed out to me on Twitter, which was tracking clouds to help save the world from climate change. So there's a lot of interesting things going on and a lot of interesting reasons to be working on this. And that's why we wanted to put this workshop together. But specifically, why robust video understanding / robust tracking and segmentation? Because of all the many difficulties of dealing with videos that I talked about before, many methods are very handcrafted, very overfit to the specific domain that they're designed for. And they don't really work robustly across all different settings, across all different benchmarks. And in the real world, we need robust methods. We need methods that are just going to work in the real world, that are going to work no matter what kind of data you throw at it. So tracking and video segmentation is exploding recently. So I've listed here basically a bunch of benchmarks that people have been evaluating on and the year they come out on. So in 2012, Kitty came out, and this was a huge thing for tracking. The benchmark to finally evaluate this kind of stuff, super useful eventually for self-driving. In 2015, MOT Challenge came out, and since then that's been one of the main benchmarks. And since then there's been more and more. 2016 Davis, 2018 YouTube VOS, 2019 MOTS. In 2020, there's been a huge amount of different benchmarks, Waymo, BDD, Tau. And now this year already, we've seen just even so much more with the OVIS benchmark coming out, Open World Tracking benchmark, unidentified video objects, and the segmenting and tracking every pixel benchmark as well. So this field is exploding. There's so much happening. And I've only kind of mentioned those that are kind of related to to kind of the multi-object tracking sense, but there's also so much more going on in like first frame given tracking, where you get given the object to track and then you have to track that throughout the video. That's also super interesting. Plus 3D tracking on bounding boxes. There's a lot of interesting data sets in new scenes and Argoverse, etc. And so this is fantastic. The increase in interest, increase in investment, increase in research into tracking is absolutely amazing for the field. But this growth, and specifically this growth of so many different benchmarks, definitely comes with downsides. And one of the downsides that has come up recently is that with so many different benchmarks and so many different challenges and so many different workshops, this fragments the community. So different people are working on different benchmarks and creating solutions for different sub-problems. But at the end of the day, these things are kind of all trying to work towards the same thing. And solutions for methods that say work on BDD tracking should also be working on, say, YouTubers, because both of them are trying to understand video, both of them are trying to track objects. And currently in the community, that hasn't so much been the case. So that was one of the big motivations behind creating this workshop and behind creating this challenge, was to bring together the currently fragmented video understanding, tracking, video segmentation community together into one place, to share ideas together and work towards solving all of these problems together. And specifically for the challenge that we set up, we wanted to move towards creating robust algorithms that work across all of these different domains and hopefully generalize better to the real world. So that was the motivation why we started this. So sometime last year, basically, I emailed a bunch of people, the people that belong to all of these different benchmarks. So there's 8 benchmarks here that we set up a challenge for. And I said, okay, between all of you in this email, you have 8 different benchmarks, all doing a very similar kind of thing. Let's pull these together and create a super benchmark and a super workshop. And let's really push to move towards algorithms that work robustly across all of these different things. So one of the focuses of this workshop was to host this challenge. We called it RobMots, Robust Multi-Object Tracking and Segmentation. And the idea was to create trackers that work robustly across all of these different settings. So across tracking people and MOTS challenge, across driving scenes for people and cars and Kitty and BDD and Waymo, all of these different driving scenes with different setups, tracking more general objects, and say that from YouTube Verse, from Tau, or from Ovis, or from Davis, and put all these together to see how algorithms can work robustly across all of these different settings. So one of the problems with setting this up was that all these different settings have different classes and different settings. So we basically converged on a unified set of classes to evaluate, which was those classes that belong to the COCO set of classes, which also enabled methods to use the COCO data for learning, say, detection if they wanted to. So that was the challenge. So we ran this challenge. We ran it over the last couple of months. In the end, we had 12 submissions to the validation set, 10 submissions to the test set. 6 of those submissions beat our original baseline and were invited to submit papers. 2 of those declined to submit papers, so we ended up with 4 final submissions accepted to submit a paper at our workshop. So one of the other features of this challenge was that for the first time, basically we had a big challenge where all the methods could be compared using this novel HOTA metrics, which were recently proposed, which enable a better analysis of how well trackers are performing and enable better separating of how well trackers perform detection versus association, and specifically even more in detail, precision versus recall versus splitting tracks up versus merging tracks together, etc. So I'm not going to go into too much details on this, but this was a big component that's going to enable future tracking research to really understand how to improve trackers. So what were the results of the challenge? So the top 4 place methods were here. So the top 3 are going to give orals later, and all of them will be presenting spotlight videos and will be present in the poster session later. So these are the top methods. So congratulations to all of the top methods here. So these were the final results. I'm not going to linger long on the slide, but you can see that the scores can be separated nicely by how well methods perform detection versus association. So there was very little increase in the detection, but compared to our baseline method, but overall much more improvement over the association for the competing methods. So like I said, stick around for this workshop. At these times over here, you'll see the 10-minute oral presentations for 3rd, 2nd, and 1st place. And later on in the spotlight, all methods will have spotlight and poster sessions. So for this workshop, we also had submitted papers that were separate from the challenge. So papers were limited to 4 pages to enable co-submission to a full conference, and all papers were reviewed, and the top 3 papers will give orals later, and all 7 papers will present at the Spotlight poster session. So congratulations to the paper that was given the Best Paper Award for these papers, Self-Supervised Video Object Segmentation by Motion Grouping from Yang et al. At the University of Oxford, and 2 second place Best Runner-Up Best Papers. So we had multiple object tracking using mixture density networks for trajectory estimation from Gerbau et al. And from Catalonia, Universitat Politecnica, and motion vector extrapolation for video object detection from True et al. From Ryerson University. And there was 4 other, like I said, there were 7 papers in total accepted. So there's 4 other papers here. I'm not going to go through them all now, but they will be presented at Spotlight sessions later, poster sessions later, and there'll be a chance to talk to the authors there. So definitely take that opportunity. So now one of the most exciting part of these workshops are the invited speakers. So for this workshop today, we have 8 very exciting speakers, 8 very exciting invited talks, keynote talks. So these times are presented in European East Time, the EDT time zone. So first up, we're going to have Michael Falsberg giving a talk, and then the rest of the speakers going through. So I'll introduce these as they come. I'm not going to spend too much time here, but I just wanted to share a little bit of information about why I particularly chose these speakers to talk today. So when I was organizing this conference, this workshop, I wanted to have the best workshop possible, obviously, putting a lot of effort into this, so I wanted to make it as good as possible. And the question is, who do we invite to speak? This is the 3rd one of these workshops that I've organized over the last few years. And one of the factors is that often you hear the same people speaking again and again. So the question is who would be the best people to ask to speak? So instead of going through and thinking of all the people that I could think of, that was never going to end up with a good solution. Instead, I jotted down 8 different categories of things that are related to video understanding and tracking and segmentation that I thought would be most interesting for our listeners today, the people that have turned up. So I can just go through those quickly. So the question was, okay, well, we've talked about tracking and segmentation as separately. So I wanted to have somebody talk about how segmentation and tracking are related. So for that, I invited Michael to give a talk. Towards the future of tracking, I think self-supervised is going to be something super important for understanding videos. So therefore I invited VD. And I invited Lorenzo because he's done a whole lot of work on video understanding, action recognition, backbones for understanding video. So I thought this was also a super interesting topic. And Lorenzo's done a lot of interesting work on that. As a 4th topic that I thought was super interesting for our audience was moving towards 3D tracking. And Philip Cramble has done a lot of interesting work on that, so I invited him. One of the main topics of this workshop, as I've said, is working towards robust methods. So I wanted to have someone particularly talking about robustness, and from that kind of domain adaptation comes up as one of the main topics in kind of robust methods. So Judy Hoffman was one of the world experts in domain adaptation, so she's going to be talking about domain adaptation for video understanding. Another aspect that's super important for kind of tracking is future prediction. So if you can predict the future, if you can kind of predict how objects are going to move, you can track them. And so Chris Katani and his PhD student, Shinshaw, I might be pronouncing that wrong, but I tried, will be giving a talk on future prediction and how that interacts with tracking. Another interesting aspect is using simulation for tracking. So that's something else that I think is going to be super important in the future and currently. And Sanya Fidler has done a lot of amazing, excellent work on using simulation for understanding scenes. And then finally, 3D representations for tracking and self-supervised tracking kind of tied up together. There's been some amazing work from Katarina Flakiadaki recently. So that was the final topic that I was interested in. So yeah, there's an amazing lineup of speakers. Definitely stick around for the talks. So the full schedule is available on the website. So definitely check it out. Like I said, we have orals from the challenge winner. We have all of the 8 invited speakers. We have orals from the best paper runner-ups and the best paper. And then I just wanted to highlight a few very interesting things, which is at 10:10 East Coast US time, will be a spotlight session followed directly by a poster session on Gatherly. So don't come to the Zoom room at this time, go to the poster session on Gatherly. And then at 1:30, there'll be a 1-hour panel session with some of our invited speakers. So also turn up for that, that'll be super interesting. So now the last couple of slides from me is a huge thank you to all the co-organizing team. So there's a lot of people that were involved in putting this together because we had to bring together these 8 different challenges. So all of the organizers of those 8 different challenges have come together and helped out to put this together. So thank you to all of those people. The list is on the website if you want to check it out. And finally, a huge thank you to our workshop sponsors. Google, Facebook, and the Computer Vision Lab at the ETH Zurich have all sponsored money to ensure this workshop works and to provide prizes for the winners. So huge thank you to them. So that's all of the slides I have today. So I think if Michael's ready to present, then he can start sharing his slides and we can begin with the first oral talk of today. So talks are going to be around about 20 minutes, maybe a bit longer. There's 30 minutes in total with hopefully 5 to 10 minutes of discussion afterwards. So please, if you're in the Zoom session today, think of your questions and feel free to ask them afterwards. If you're not in the Zoom session today, then but you're watching on YouTube, post your questions onto YouTube and I can ask them for you. So please think of questions and ask them. So over to you. So our first speaker is Michael Felsberg from Linköping University, and he's going to be talking about going from discriminative object tracking to video object segmentation.
Yeah, thank you very much for the introduction. I'm, as you said, I'm from the Computer Vision Laboratory in Linköping in Sweden, but I'm also co-affiliated as honorary professor in Durban, South Africa. I would like to say a few words about myself. Those of you who don't know where Linköping is located, it's like in the southern part of Sweden. My background is actually from Germany, and I made my PhD under the supervision of Gerald Sommer in 2002. I'm professor at Linköping University since 2008, and I'm heading a division with about 25 people doing research in machine learning for robot vision and machine perception. Most of our research is funded by WASP, and I'm also in the program management of WASP. And I would like to say a few words about this huge project cluster. So WASP, that stands for Wallenberg AI Autonomous Systems and Software Program. It's Sweden's largest project in history. You see some figures here, so very ambitious plans. And the vision is to do excellent research and competence in artificial intelligence, autonomous systems, and software for the benefit of Swedish industry. And it's funded by the Knut and Alice Wallenberg Foundation. Within this huge project, we are also constantly hiring. Very soon, we will hire 2 assistant professors on machine learning on the specific topic of integration of data and simulators. These are tenure track and come with a welcome package. Please check out the links and the QR codes on this page. They will come up very soon. But now to this talk. The background material to this talk can be found in a chapter of an upcoming book by Davis, Camps, and Turk, Advanced Methods of Deep Learning Computer Vision. And the chapter will be available in October, I guess. So, but now to the contents. I mean, I will talk about tracking, but I think it's worthwhile to think about, in particular, when we talk about object-specific tracking and generic tracking, to recall what we are usually doing and talking about if we talk about classification or categorization, like confirming or rejecting whether a dog is in this image, the localization task, where we determine the position of the dog, or the detection task where we want to detect all dogs in the image. And when it comes to tracking, we would like to distinguish between class-specific tracking and generic or class-agnostic tracking. So if you for a second think about tracking a person, you could take this sequence here. You could specifically track this runner. And now, in this case, the tracking is actually done by a generic tracker. I just want to take this as an example. But this is not the case I will talk most about. I will talk more about generic object tracking for various reasons that I will shed some light on a bit later. So Jonathan has talked about various applications of tracking and video understanding. And one such application area is autonomous systems for rescuing people. So this is a use case that was drawn up in the WASP project. In this video, you can see autonomous boats and autonomous drones that communicate with each other, but they also track each other. They track people, they detect and track people, and they try to locate people that are in danger. And we will revisit these two platforms now in the coming 20 minutes. So the first one, I mean, you've all seen this before, I guess, is if you want to do virtual leashing, that is connecting a drone by a virtual leash to an object, for instance, a person. So this goes back to quite old work from my lab by Martin and Gustav. It is actually the method that won the VOT challenge in 2014. And this has been used on a drone to track a person and make the drone following the person. So this is quite old work, but this is where all begins. And I will say a few words about this tracker and then go all the way to segmentation. But so far there was clear focus on people. I mean, I talked about that the drone would also track the boat and the boat would track the drone. But I also promised to give some motivation why we want to do generic tracking. The first problem is that whatever we track in the real world and that we want to track robustly has a very high intra-class variability. So look at the cyclists here, for instance. I mean, these are both city bikes, but still just by the aspect, they look quite different. But you could also imagine like a racer bike versus an e-bike, a very comfortable e-bike. They have completely different appearances. The second problem, and this is probably the most dominating problem in video analysis, is that we have constantly new classes appearing. So we cannot apply the closed world assumption. So in the closed world assumption, you would reject anything that is not present in terms of a statement or in terms of detections. Or if we speak in terms of machine learning, everything that is not in the initial training data set would be simply ignored because it's considered irrelevant. And this we can't do in video understanding, in tracking and segmentation of videos. So now let's start with the tracking problem. And here I borrow the formal problem definition from the VOT challenge, as it was already formulated at the ECCV workshop 2013 by Mate and colleagues. So the input to the tracking problem is an image sequence together with an object bounding box in the first frame. And the expected output are all the bounding boxes in the frames, in the later frames, t larger than 1, and they may only be determined by the older frames, so a causality assumption. We would like to apply this method online or in real time on sequences. We make some assumptions, and in the VT challenge explicitly, it is assumed that the object is always at least partially visible. There's no long-term full occlusion or leaving the field of view. On the other hand, we have moving cameras all over, so we're not interested in background models here. So the challenge that originates from this setting is to build a model from one annotated training sample, that is the first frame, and that even for unknown object class, because it might have been that this class of objects has never been considered before. And during the sequence, the challenge is to update the model from previous estimates. It's a kind of bootstrapping process. I've illustrated these two steps here in these two graphs. So on the left, you can see the initial annotation leads to some model And this model is the initial tracking model. And then during the tracking, we have a new frame at time t. We have the old model t-1, and that produces a prediction. And the frame together with a prediction and the old model are used to produce a new model for time step t. Now, you might wonder, why is it necessary to update the model all the time? Why can't we go with the initial one? Well, there are many reasons, and there are many challenges in visual object tracking. So we have several problems like occlusion, clutter, changes in viewpoint, scale changes, illumination changes, motion of objects, articulation. Many of these are displayed in this video. We also have motion blur and change of appearance because we have like faces articulated. So if you want to address all these challenges, you need a model that is adaptive. So you need to update the model through time. So now the question is, which models are the most robust ones? And here we learned a lot from the VOT challenge. So this is the result from 2018 at the ECCV workshop. So you can see on the left, you see a graph with all the submissions, over 70 in that case. And we made some statistics on how many of the trackers were based on a discriminative model and how many were based on a generative model, and also how many were part-based and how many were holistic. And it turns out that the vast majority is holistic and discriminative. So this comes a bit as a surprise, because if we think about partial occlusion, part-based systems might appear interesting. But I have one example here of a generative tracker with occlusion that is based on an approximation of a density estimation. And this one allows to track very stable, despite the fact that it's a holistic model and that occlusion occurs. So it actually turns out if you have a good representation, there is no issue with challenges like occlusion or articulation, like in this case. Okay, but the other class was discriminative versus generative. So when we say now we go for holistic models, but why should we go for discriminative ones? And in this graph, I have displayed briefly what the main difference is. So we start with a generative model, like the one used in the previous one. So we have, in the new frame, we have candidates like a moving window, and we have our old template. And then we have some kind of distance measure between these two. And this distance measure generates a score map over all positions in the image, or a selection of positions. And then we pick the maximum, that's the best candidate, and we use the original window to update our template. And the main challenge here is to find a distance or similarity measure that is robust with respect to the variations of the object that occur, and at the same time discriminative between the different objects. In contrast, the discriminative model here to the right works slightly different. So the idea is that we do not calculate a distance similarity between the current window and the template, but we calculate a scalar product. And here it becomes already obvious that the template is not necessarily a representation of the appearance of the object, but rather dual to it, so that it gives a very high score if it's a good fit and a very low score if it's a bad fit. So all these scalar products, they generate a score map. We detect the maximum again. And at that maximum, we then locate a prototypical response that we would like to see from our template. Typical Gaussian function located at the maximum. And now we can use this together with the input window from the current frame to update our template. So to compute some model increment and update the template. So this is on a conceptual level what we do in a discriminative tracker that is based on a holistic approach. Now we come to the more technical realization. The trackers that we used mostly, and also the trackers that were most successful in the VOT challenge, or at least the discriminative trackers. Most of them were based on the MOSE, the minimum output sum of square error by Bohm et al. In 2010, where we have a previous input image and a previous response to the left. From that, we optimize a filter, F tilde, and this filter is then applied to new input xt to produce an output score y tilde. And the maximum of this y tilde is then used to locate a Gaussian at the correct position to produce the yt. Or if we put this in math, we can say if we have more than just one sample, so we have a set of samples, xt and yt, we want to minimize the quadratic distance between the correlation of the inputs with our filter and the desired response function. In the Fourier domain, we can express this by pointwise product instead of a correlation, which allows us to calculate the solution in a very efficient way by simply pointwise products of the output and the input summed over t divided by the pointwise product of the inputs divided over t. Now, this solution can be calculated in a closed form this way, but due to this summation in both the numerator and denominator, we can also produce incremental solution with finite memory. So we simply have a moving average of these two pointwise products, x dot y and x dot x. And we initialize this with a corresponding first frame result. And now we can calculate at each time step the filter as the quotient between AT and BT. So we store AT and BT in memory, update it in each time step, and calculate the quotient to get the filter. Now, if we go a bit on in the literature to improve the robustness of the approach, Enrique et al. Suggested to use ridge regression, that is quadratic penalizing the filter coefficients. And the nice benefit is that you can calculate the filter solution to this in exactly the same form. The only thing you have to change is that you have to add this meta parameter lambda to the denominator. So far, so good. So all of this works for single channel images or single channel input, but already for color images, this is an issue, in particular if we would feed in feature maps from deep networks. And this is approached by the discriminative correlation filter, so to say the multi-channel version of the MOSE approach. Here we have an input image and extract multiple channels from it. And then we have a corresponding number of filters such that we calculate a score map by applying each filter to the respective channel of the feature map and then summing up the scores. So to put this in some equation, we can see here the summation over the feature channels from 1 to D. And we take our input image, we split it into our channels. In this case, it's the green channel. And we have the corresponding filter that we obtained from the optimization that is applied. And these results are summed to get the score function. Now during training, what we do is we have our input data and our responses that we want to approximate. And then we minimize this functional here below, this objective. This optimization is rather simple. You can write these expressions in rewrite them in matrix form. So when you minimize this, you can reformulate it in the Fourier domain, and you finally get an expression where you have very similar to the MOSE. You have the inversion of a matrix, which is mainly consisting of x times x and some regularization term, and in the numerator xy. The problem here is that this inversion is a d by d system. So if you would like to do some kind of incremental update, this is problematic. There are ways to do this in an efficient way, but it's also found that if this is done in a rank 1 approximation by simply using the previous update equation, the result is pretty much robust. So the penalty you pay is very low, but you gain much performance. Now, if we apply these filters, we get quite good result, like the runner in the first video that I showed. But there is one problem, and that is if you apply the Fourier domain approach, it corresponds to circular convolution, which means a periodic extension of the image. And that could lead to filter coefficients that have rather high values outside of the bounding box. And they might suddenly focus on the background. And just blowing up the region doesn't work because we get too many background pixels. Instead, it's better to change the penalty term such that coefficients far away from the bounding box get a much higher penalty. And by doing this, we can suppress high coefficients in the vicinity. So if we look at the formalization of this, the main thing that we change is in the regularizer. So instead of the L2 norm of the filter coefficients, we have some weight W here that is multiplied pointwise. Now, there's an issue here because if we go to the Fourier domain, the pointwise product becomes a convolution, and that makes it slightly more expensive. But it turns out that it's not that bad. So if we look at the solution from the non-regularized filter, that is the second equation here, it's just rewritten so that the inverse is written to the left, this matrix. We can now see that the X can be turned in a real valued matrix, exploiting the Hermitian symmetry, and similarly for the target values Y. And the lambda I is changed to convolution matrix, and under this mapping to the Hermitian matrices, we can find the corresponding matrix W transpose W that correspond to the convolution in the Fourier domain. So this is a pretty straightforward mapping. So in the end, we get a real valued matrix equation where we have a symmetric matrix to the left, and then we have our F tilde that we look for, and on the right-hand side, we have some data term that is calculated. Now, instead of using this incremental update of numerator and denominator, the approach in this work on the spatially regularized filter was a different one. So Gauss-Seidel, the decomposition is used here. So the left-hand side is divided up into a lower triangular and a strictly upper triangular part, LT and UT. And then the LT is associated with the new values of F tilde and UT with the old values. And this is then fed into iterative approach. So you can see here the iterative solution. On the left-hand side, you have the lower triangular matrix LT times the filter that we look for at time step J, or not time step, but iteration step J. And on the right-hand side, we have the UT times the old F tilde J minus 1. This is iterated, and usually if the W doesn't contain too many coefficients, these iterations converge very fast. This brings then us to the algorithm of the SRDCF, the spatially regularized correlation filter. And to the right, I will in a second start a video where the red one is the regularized one, the green one, DSST, is the one that won the challenge in 2014 without this regularization. And you can see the robustness is significantly improved. So most trackers fail at this small occlusion at the traffic light. Still, this tracker is not perfect either. So I will start a video on the left, and you can see that the SRDCF tracks the head of the guitar instead of the head of the guitar player. And this is caused because there was a consistent occlusion by the guitar head in the beginning. And this was somehow contaminating the training data. So during the update in the first iterations, it was going towards the guitar head instead. So this type of behavior can be avoided if we have more balanced training data for our tracker. And this was addressed in the work of the Echo tracker. So you can see here in these images a representation of the learning set for incrementally updated tracker, like the SRDCF, in this case CCOT, so it's working on a continuous approach. I will get back to that in a second. But what you can see is that all the samples are very similar, and the result of the optimization will be dominated by the filter that fits this particular instance of the object appearance. Instead, what we do in Echo is that we cluster the different windows that were identified as the best fits, and we build a mixture of Gaussian model of this in order to balance the different appearances of the same object. And this makes the tracker much more robust. So even if we have a sequence where there is a constant view on the object that we're interested in for a very long period, the model will not degenerate. It will still maintain the original views or aspects of the object as well. Now, as I said that we use CCOT and not SRDCF, it's a continuous approach, and this is because we now use multiple channels with different resolutions, as we use different network layers in a deep network to produce the feature maps. So in this first work from 2015, we used VGG layers 1 to 5 in addition to the input layer, and fed all of these into the tracker to improve the robustness. In a follow-up work, we also used motion features shown at ICPR 2016. And as you can imagine, now we are blowing up the number of channels exhaustively. This improves the flexibility of the model quite a lot. But what happens is that in most of the situations, most of the channels are of very low activation. And on the other hand, we have a huge amount of weights that we have to optimize in each time step. So we are doing overfitting to the data that we have access to. So this was the second thing that was changed in the Echo tracker, where, so to say, a subspace projection was learned in parallel with the weights themselves. And this gives a reduction of parameters by 80% and better performance even. Now, the Echo tracker was a very popular baseline for many follow-up works. And one of its problems was, however, that even if you use newer or more recent backbones than VGG, like GoogleNet or ResNet, the performance wouldn't increase that much. So you can see this in the red pillars here. And this has a particular reason, and that is that you cannot exploit the dynamics in the different features, in the feature maps that come from different layers of the network. So we would like to base our decisions of the tracker only on very shallow features or only on very deep features in certain situations, but this is not allowed by the Echo approach because it has a fixed scheme to fuse the different layers. And it actually turns out that shallow and deep features, they have complementing performance, as you can see on the right-hand side. So this is then the idea of a follow-up work where deep and shallow features or deep and shallow models were fused very late. Actually, they were trained independently, so they don't know about each other during training. Only at the time of inference, when the maximum detection is done, the scores are fused, and this is done by an adaptive weight with different coefficients beta. Illustrated to the right, you can see 3 different cases. And the first case, shallow features dominate, and the second, You can see both shallow and deep features are used, and the last one, only deep features are used for the final output. This improves the robustness significantly. And of course, robustness is always a primary interest, but also accuracy is important. And in a follow-up work to that, we improved the accuracy by an additional intersection of a union predictor that specifically focuses on optimizing or maximizing the intersection of a union, and by that giving a better accuracy in the location of the bounding boxes. Why I mention this is in the time of that paper, so in 2019, the old challenge from 2013 to 2015 was already superseded by the accuracy of modern trackers. So the limit in the evaluation was the accuracy of the data set. So in 2015, manual annotation were used, and they were often inconsistent. And in 2016, a semi-automatic procedure was used based on the segmentation of the object. So this was one of the main contributions from the VOT challenge in 2016. Now, besides getting a more repeatable bounding box from a segmentation mask, there's another point that is advantageous with segmentation masks, and that is illustrated in this picture. On the left, you can see a bounding box and an anisotropic Gaussian that corresponds to the position of the center point of the bounding box. So this is about the information that has been used in tracking when only bounding boxes were tracked. Whereas on the right-hand side, you can see segmentation of the same object, and you can immediately see that there's much more information contained. So for the purpose of video analysis, this is very beneficial, but it is also the key to higher accuracy and measuring differences in accuracy between different methods. But this actually means that we go from sequences with bounding boxes to sequences with segmentation masks. So we arrive at video object segmentation. So in the Davis challenge, the typical setting is that you have a training set of sequences with annotations for each frame. And then you have test data where you have a sequence. And in the supervised case, you have a segmentation mask for the first frame. In the unsupervised case, you have no segmentation mask. I will only talk about the supervised case here. Now, this type of challenge can be nicely approached by generative methods. One example is the A-game algorithm, where a Gaussian mixture model is used to learn the appearance, and the classification of the pixels is done based on the mixture coefficients, as illustrated by the graph below. This gave state-of-the-art results in 2019. You can see some examples here in the video that is playing. Now, what we then approached was to bring the discriminative approach that was so successful in tracking to the segmentation. And this was done in the work by Andreas in CVPR 2020, where instead of building a generative appearance model, a target model was suggested. The target model is nothing but a discriminative model that produces as output something that is of high value if it's inside the segmentation mask and low value if it's outside. So in the processing, what is done, a memory is built, and then by a Gauss-Newton conjugate gradient optimizer, the target model is re-optimized during the sequence all the time to produce low resolution score maps, and these are then upscaled by a segmentation network to high resolution segmentation mask. The target model used in this work is really, really simple. You can see it here. It's two linear layers, and it gives quite good results. So you can see to the right, lower right, the output of the target model. And in numbers, you can see that it's both faster and better than many other approaches. And yet another sequence. Yeah, and I see my time is running up, so I have one last item to show, and that is all these approaches, they are based on single targets, basically. So like the work that I just showed produces a target mask. In some follow-up work, learning what to learn, instead, the multi-channel representation of the target mask was used and was, so to say, the target of the optimization. And in very recent work, this was extended to also produce masks for distractors. And this works so nicely that in some cases like this with the camels, so the one in the foreground was the one that was annotated, and the distractor channel identifies the one in the background as a distractor camel. Or here in this car sequence, the car in the center is annotated and the one in the background is considered a distractor. So I think that brings me to the end. I had some extra slides, but I have to skip through them. It was just about another use of discriminative correlation filters. And well, I want to leave some time for question, although it's very little, I think, I'm afraid. Thank you very much for listening.
Awesome. Thank you. Thank you very much for the talk. Super interesting. Does anybody on Zoom, I think we might have time for one question or quick if there's a few, if they're quick, maybe a few. Does anybody on Zoom or have any questions, or they want to type them in the chat? Otherwise, I can go. Let me start it off while people maybe are thinking about it. So you talked a lot about the history of a lot of this work, and a lot of it's been done in your group from 2010 until now. The next question is, where do you think is going to be the next big change? Where do you think discriminative tracking and video object segmentation, what's the next big thing that really needs to be investigated that we're not quite there yet?
Well, I think the unsupervised learning is the key point, because one of the major concerns was always, where does the first bounding box come from? Where does the first segmentation mask come from? So I think the real challenge is unsupervised learning of video object segmentation, video instance segmentation. And I know many people are working on this, and you have, in your channel, you have included many aspects of that, and I think this is very important. But the question is, how can you train a discriminative model in that case? That is really the tricky part.
Yeah, super excited. I'm guessing if you're excited about that, there's going to be some exciting work from you and your group in the future on that too. So in the interest of time, maybe we'll end the question there, because I don't see any questions on the chat. Wait, maybe just let me check in case there's something I missed. No, so there's no other interest in the chat, and we're a little bit over time already. So thank you very much for giving the talk.
Thank you for inviting me.
Yeah, no problem. It was excellent. Thank you. So next up, we have Andrew Gabau. I may be pronouncing your name wrong. Feel free to correct me after you start talking. Who is going to be presenting a 10-minute oral, which get the best paper runner-up for the paper submission track of this workshop. He's from UPC Catalonia, and the work is on multiple object tracking using mixed density networks for trajectory estimation. So I will hand it over to him.
I think I'm on it, right?
Yep, perfect. So all yours.
Okay, thank you, Jonathan. It's okay. Like many different cultures, like the names are not a little bit difficult. So hello, everyone, and thank you for being here. I will start my presentation. I'm Andreu Girbau, and I'm going to be presenting multiple object tracking using mixed density networks for trajectory estimation. This work is a joint effort of the Polytechnical University of Catalonia and Automatic TV from the Media Pro Group. Okay, to start, let me do a little introduction on multiple object tracking and trajectory forecasting. So in multiple object tracking, given a video sequence, we assign an ID to every object of interest and try to connect the objects through time. And the current dominant approach is tracking by detection, where first we detect objects and then link these objects through time, forming the final tracks. So essentially, the information of an object being tracked is an ID, the detection in the current time step, usually in the form of a bounding box, and the track usually represented as points. On the other hand, trajectory forecasting consists on reasoning about the future behavior of agents, and it works upon a stimuli, which can be past trajectories, pose, physical attributes, or other sensor data that is input into a prediction model that outputs the forecasted trajectory. The dominant approach in this field, in the trajectory forecasting, is data-driven, where the models are trained using the available data. We follow this approach with a recurrent neural network and assign an instance of a hidden state of the network to each object, so that in inference, each hidden state will be modified depending on the evolution of the trajectory of that object. So in this work, we present TRAGE, which is a simple trajectory estimator that uses mixed density networks and beam search to forecast trajectories. So given a track up to time t, we compute the offset between the current position of the object and the previous one and input it to a recurrent neural network. This network will output a distribution from where we will sample the next possible positions of the objects in the form of offsets. So the three main blocks in TRAGE are a mixed density network that generates a distribution from where we sample the possible displacement of an object. So these mixed density networks are quite used in trajectory forecasting. Then a beam search technique that generates this our trajectory hypothesis, and to avoid an exponential growth, we prune the number of possible trajectories and just keep the specified amount that corresponds to the beam width in beam search, which in this case, as an example, I put beam width 2. So this trajectory will be explored in two trajectories will be explored of a certain object. And finally, we propose an occlusion reconstruction step to incorporate the estimated trajectories to the object tracks with this estimated trajectory that we generated. So summarizing the contribution of this work, we built TRAGE, our simple trajectory estimator. We incorporated it to two trackers, which are center track and tractor, and proved that trajectory estimator estimation can be very useful for the multiple object tracking setting. Going into detail on the mixed density network block, our input is the offset position of the bounding box centroid of an object being tracked to a recurrent neural network directly from the 2D image coordinates. This network outputs parameters corresponding to a set of M Gaussians. And these parameters are the Gaussian weight, mean, variance, and correlation coefficient. Combining these Gaussians, we generate a Gaussian mixture model that represents the motion distribution of an object from one time instant to the next one. We have to take into account that to form a valid distribution, the Gaussian weights should be normalized to 1, which we do with softmax normalization, and that the elements of the variance have to be positive, and the correlation coefficient, well, in this case, we set it is set to -1 to 1. And we observed in our results that by directly sampling from this generated distribution, the generated trajectories were not ideal. I mean, they were good, but we thought that they could be better, and we think that this can be related to the huge amount of possible trajectories that an object can take during a sequence. So for this, we decided to bias the distribution toward more likely motions by modifying the weight of the Gaussians forming the distribution, and by changing the variance to sharpen the distribution by means of a bias factor. So we can sample more likely displacements of objects. As the next step from this constructed distribution, we sample a set of object displacements corresponding to the beam width, which is the amount of trajectory hypothesis that we are going to be propagating through time. And in the case the object is detected and associated to a track, this information is, the information of the object is updated, adding a new position to the track, and the hidden state is also updated to the one that generated this distribution from where we sampled the offset that led to this new detection. So this way we can keep the trajectory evolution per object embedded in this single feature vector. In the case the object is not detected, the offset samples are input again to the recurrent neural network, which will generate a set of new distributions depending on the input from where we are going to sample the next possible offsets. As previously commented, this leads to an exponential growth of the possible trajectories, so we prune them by using a maximum likelihood criteria, keeping a beam width amount of trajectory hypothesis per object. To generate this trajectory hypothesis, we defined 3 exploration strategies. The first one is the best mean, where we take the mean value of the Gaussian with the highest weights in the generated distribution. The next one is a greedy beam search, where we sample from the distribution and keep the most likely position at every time step. And the last one is a pure beam search, where we propagate all the samples to form a beam width amount of possible trajectories. We use the estimated trajectories to reconstruct the tags being occluded. So when an object being tracked is lost, we keep estimating its trajectory through time. And if this estimation leads to the track recovery, we check if the projected position is spatiotemporal coherent with the current detection by means of the intersection over union of the projected bounding box to the current time step and the current detection. And if it's above a certain threshold, we add this estimated trajectory to form this the object final track. So we incorporated Traje into two well-known trackers, which are center track and tractor, and observe a direct impact when using trajectories. Also, by adding the estimated trajectories after an occlusion occurs, its improvement is further achieved. So our take-home message from this presentation is that trajectories can be a great source of information, and we should take them more into account when doing this object tracking. So now I will show some visual examples of Traje's behavior. First, for the baseline tracker, we observe this kind of identity switches, which can be very common from this kit. Then when adding Traje through the tracker, the identity of this kit is maintained throughout the sequence. And furthermore, when adding the occlusion reconstruction, the estimated trajectory is added to the final track, reducing by a lot the false negatives. On a more dynamic example, when tracking these two people with this our baseline tracker, we see that, again, the identities are not maintained for all the sequence, especially when the occlusions get in the way. By using Traje, the estimated trajectory that Traje produces estimates to correctly identify each person and maintain the correct ID along the sequence. And finally, when using the occlusion reconstruction, this occlusion reconstruction, by using the estimated trajectory, the tracks during an occlusion are filled with the estimations. So what could go wrong with Traje? So here we show an example of the wrong behavior of Traje because the models are not perfect. So in this case, in the first case, the baseline correctly assigns different IDs to each person, but when using Traje, the same ID is incorrectly assigned. And when using the occlusion reconstruction, these errors are propagated along the track for generating some false positives. So that was my presentation. Thank you for your attention. I hope you liked it. And if you're interested in this work, we recently uploaded a more detailed version in archive. And if you want to further discuss, please come to the poster during the poster session. Thank you.
Awesome. Thank you very much for that talk. It's amazing. So yeah, that work recently, just to highlight again, it got second, so best paper runner-up for the submitted papers here. So that's why it wasn't oral. So there's going to be no questions for the oral sessions because we have a poster session. So instead, hold on to your questions, come to the poster session, ask your questions there. So we're going to move ahead straight away to the next keynote invited speaker, which is, I feel like I'm going to be pronouncing. Yeah, thank you very much. I feel like I'm going to be pronouncing names all wrong all day today, but I guess too bad. So VDZ is maybe how I pronounce it. Again, feel free to correct me. He's nodding, so that's good. So one of the last things the last keynote speaker said that he was excited about was self-supervised learning. So today Vedi is going to be talking about self-supervised representation learning. So he is a member of the University of Oxford at BGG. So you've got your screen sharing going. So when that's set up, handing it over to you and excited to hear your talk.
Hi, can you hear me?
Yes.
Great. Okay, yeah, thank you for having me today. So I'm going to talk about the self-supervised video representation learning, and mostly it's going to be the work we've been doing in the last two years-ish. So the first thing I'd like to emphasize is what is self-supervised learning. To me, it's still a form of unsupervised learning, and usually you define a proxy task, and the proxy task can be solved by the data itself. So meaning the data provides the supervision to your task. And there are basically two different paradigms, in my opinion. So the first one is you define the proxy task and you want the network to solve the proxy task. But the learned representation can't be used directly. So you need to train a classifier on top. And this branch of research typically are the SimClear or MoCo, these kind of things. So they all fall in the instance discrimination branch. So after training the model, you need to train the linear classifier on top. And the second paradigm, which I'm more interested, is you learn the representation, and the representation can be directly generalized to the downstream task. So meaning you need zero annotation for the model to be used. And you can do audiovisual localization, you can do tracking, and you can do segmentation in the videos. So basically, to summarize, the first one just learn some transferable features, and the second one just learn some applicable embeddings, in my opinion. In general, I'm interested in videos because I think videos is a superset of images because it's a sequence of images. So we all know that. And also videos are more interesting because you have a lot more information to play with. So here I show you some, so here I show you some a video clip. So you have the RGB frames, you have the motion, you have the audio, and sometimes you even have the narration, say in the instructional videos. So people will explain what they are doing. So you have that information for free. And I'm going to, in the following slides, I'm going to introduce some of the work we've been doing for using these informations. Okay. So the first work, this one is published in Europe 2020, and this follows the first paradigm, which meaning you have to train a model, and the model can't be used directly. You have to do fine-tuning on the model, or you do linear probing. This is for action recognition. So the first author is Tengda, and also with Andrew collaborated with Andrew in the paper. So the idea is simple. It's just using SimClear, let's say SimClear in videos. What you do is you have two video clips. You just do two augmentation for the video clip, and you encode them into a feature vector. And what you're going to do is you pull the features from the same video to be closer, and you push the features apart from different videos. So that's why it's called instance discrimination, because you can see each video clip now is just a class, or you discriminate based on the instance. And you train this model with contrast learning. So nowadays we use inference E, which is just this classification, basically. You classify the instances. And it works good for this case because, this is playing golf. This is another action. So when you train in this way, it's no problem. But if you train in this one, because during sampling the batch, you don't have the labels. So it's very possible to sample something like this. And you do two augmentation for the video clip, and you encode them to the vector, and then you do here. So you pull this together, that's okay, because that's from the same video clip. But you push them apart. That's not good, because semantically, they are the same action. So you can see you have some incorrect learning signal. And clearly here, there's something to do to improve that, which is just the sampling mechanism we can improve. Like I said, videos, you have so much signals to use or to play. So we can use other, the intuition is we can use other modality to improve the RGB, meaning these similar instances in the RGB stream, they might be naturally similar in the other modalities. So that's the intuition. And I'm going to show you why, because if you see these two video clips, there's no reason a RGB network can embed them together if you randomly initialize this RGB network, because the background are so different, and also the foreground, they clothe are very different. But if you look at the motion, because the camera is static in this case, and they are both playing golf, and a random network, float network, will naturally embed them together. So that's a good thing, because you can use this network to sample the positive pairs for the RGB network. And vice versa, you can use the RGB network to sample positive pairs for the flow, because you do have some cases, RGB are very close, but flow are different, which is along the same video. If the person doing things in the video, RGB will naturally be similar, but flow are very different. So you can co-train these two networks together. And that's exactly what we do. So in detail, it's going to be simple. You have the flow and the RGB for the same video clip, compute the feature for the flow, and you have the flow database. You compute the flow for all the data in your database, and you have RGB along with that. So using the flow vector, you take the top k nearest neighbor, and you compute the RGB features. Now you can train the RGB network, because they are positives. So you just train by pulling the distance together and kind of push them apart from the bottom of the list. And you just train with multi-instance contrast learning because you have top K, you have K positive samples now, and you can train this easily. And you can see now the optical flow helped the RGB to go beyond instance discrimination, because all the samples here, it won't be from the same video clip. It might be from other video clip, but they all playing golf. So it goes beyond the instance discrimination. And you can reverse this process. I mean, you can use the RGB to retrieve some clips and train the flow network. So you just do this, iteratively, and both network will improve themselves. Okay. And evaluation-wise, so x-axis is the amount of data for self-supervised training. So kinetics here is 400. That's one of the standard data set we use for action recognition. It's about a month, the data. So it's 10-second clip, and it has 200,000 clips about that. So if you compute that, it's about 28 days. And once you do self-supervised training on this kinetics, and you fine-tune on UCF 101, so that's the standard protocol in this community we are doing. And you can see CoClear is pretty good. It's 91-ish. So this S3D supervised, that's really the upper bound. Meaning in this model, you pre-train on connected 400 with labels. So it's supervised learning. And you fine-tune on UCF. So it's like setting the upper bound. So we are, catching up the supervised learning method. And this, like I said, this is NeurIPS 2020. So this community is moving really fast. And we have 2 papers in this CVPR as well. So one is from Google, one is from Facebook. So this table is from the Facebook one. So you can see CoClear was 91-ish here, but now this is Google paper and this is Facebook paper. So Facebook now, they can really match the supervised learning method. So like 96, which is really high. I mean, also this community is moving really fast to me. Okay, so this is for paradigm 1 for action recognition. How can you use flow? And now from here, I'm going to talk about paradigm 2, meaning when you pre-train your model, you don't need any fine-tuning. You can directly use it for your downstream task. Okay. So the first one I'm going to talk about is how can you use audios? So this is audiovisual representation learning in videos. It's going to be 2 papers, ICASP 2020 and CVPR this year. So the first author is Hong Lian, and also collaborated with Duffy, Asha, Andre, and Andrew. Audiovisual code supervision, I think people have done this quite a lot, so I don't need to describe too much in detail. But basically, the intuition is, given a video frame, the sound and the visual frames, most of the time, they are synchronized, and also they are semantically consistent. So when you look at these frames, you expect to hear some guitar sound, right? Then you can define 2 types of proxy tasks. So one is correspondence, and one is synchronization. So correspondence meaning you have video and audio, you say, are they from the same video or not? And synchronization meaning you have the visual part and the audio part, you say, are they from the same time step? So synchronization is clearly more difficult. But I'm going to focus on correspondence in this talk. So when you train the model, like I said, you have you train 2 branches. You have the image encoder and you have the audio encoder, and you just say, are they corresponding or not? If they are from the same video, yes, they are correspond. If from different video, no, they don't. So this has been published in ECCV 2017 and also ECCV 2018 by Relia and Andrew. And just intuitively, it looks like this: 2 video clip, and from the same video, positive, different, negative. Okay, you just train 2 networks, and visual you get feature vector, audio you get feature vector, concat them, you classify yes or no, as I explained. And once you train the model in this way, you can take the visual network and also the audio network for downstream tasks, for other tasks. So in our work, what we care about is, can we do something more fine-grained? Can we localize the sound? Meaning it's like this. So you have a video clip and you have video the sound. This sound, I won't play it, but really it's just the sound of the vacuum. So you can see, can we localize this? Where the sound come from? And also we want to know really which object. And also I need an uncertain region, meaning I'm not sure if the sound come from there. And also I need a background region, meaning I'm pretty sure the sound doesn't come from here. So I want to do this task. And the idea is simple. It's just you have the visual stream, you encode it to a feature map, and you have audio stream, you encode to a vector, and you do a dot product, which is the heat map. And you want this positive region, which is you set a very high threshold. About that threshold, that's positive region. So you can see here. And you set a low threshold. Below that, that's negative region. And something between that, that's uncertain region. I'm not going to penalize those. So we expect the network to learn, give the network freedom to learn within that region. Okay. And now you can do contrast learning. So you have the positive region, which is the score on this car, you can see here. And you have the negative, which are hard negative, meaning these regions in the same image. And you have easy negative, meaning from other video clip. So that's very easy for the network to distinguish. And now you can train the contrast learning just in the inference way I mentioned before. And we train this network on the VG sound dataset. So it's a large-scale audiovisual dataset. It has about 300 classes and 200,000 videos, and it's audiovisual data. So if people interested in this can try this dataset. It's published in ICASP 2020. And for the benchmark, we benchmark on, the standard one is the Flickr SoundNet. It has 250 image audio pairs. We also collect a new dataset called VG Sound Source. So it has 5K clips and very diverse. So it has 200 classes. And you can see these are the example of the annotation. So if a group of person making the sound, you can't tell, so you just annotate a big region. But if 1, 2, 3, 4, you have these, you can tell, you just annotate them separately. And on the right is the Flickr SoundNet results we benchmarked. So in this CVPR paper, we can outperform the previous state of the art by quite a margin. And also if you scale the data set up, so this is 10K, this is 140K, and you can get even better results. So this CIOU is just just IOU, so because it's consensus, because annotated by different people and take the agreement, but just understand that as IOU. Good. And this is VG Sound source dataset, so you can see the performance is not that good. It drops dramatically, and also shows this data is much more challenging, and there's quite a room for improvement. So here is just some example. I'm going to show you briefly. So, okay, you get the idea. So it was frame by frame, so you can see some jittering. Okay, just finished audio. Now I'm going to move to motion. How can you use motion in videos? This is a work we've been doing recently. It's called self-supervised video object segmentation by motion grouping. The first author is Tarik, and Hala, Erica, Andrew, and myself. So as this community, I think I don't need to mention the dataset. This is Davis 2016, clearly. And the goal is to find the foreground object, also clear for this community. And normally what we do is, firstly, we can do really well now. And what we do is you just train the model on a data set, on maybe Coco first pre-training, and you find YouTube viewers just for fine-tuning, something like that. It's working. But the problem is not all the objects are visually evident in the RGB stream. Like this one. If I tell you there's an object in this frame, maybe you can try hard to find where is it. But if I don't tell you, maybe it's very hard to find because the animals just blend into the environment. So when you look at this video, you just say, well, that's what nature gives these animals, right? But when the animal move, it's very clear they are here. So I just want to show sometimes RGB frame, if you treat the video as frame by frame, it's not enough. You have to treat frames as videos, and motion is an important cue. Okay, so in this work, we're going to consider by doing the segmentation by using motion, meaning still we want 0 manual annotation. And the proxy task is to do reconstruction of the flow. So flow is a default representation of the motion. And what we're going to do is do an autoencoder network, which is defined, but we don't predict it directly. We predict layers. So layer representation was originally proposed by MIT, in 1994. But the idea is simple. If you play Photoshop before, this idea is simple. It's you just predict, the foreground and the background, and also the alpha channel. So we reconstruct the input, just do a linear combination. So alpha times I plus alpha times I, just do this linear combination. Now you can supervise your model by doing reconstruction. And eventually these alpha masks will become the segmentation mask. So this idea works because this is really a trivial solution for the model to do reconstruction, because the background motion and the foreground motion, they are independent. So the background motion, if you think about that, is really the camera motion. So it depends on who's taking the camera, who's taking the video, and it's the cameraman's motion. But the foreground motion is the object itself. So they should be independent, well, at least most of the time. Although we know cameraman tends to track the person, but they should be almost independent. And if they are independent, then this is the trivial solution for this reconstruction, because the degree of freedom is really low. For the background, maybe just 2 degrees of freedom, because you just need the motion because it's homogeneous. Right? And since there's a talk in the afternoon about this, so I'm not going to say too much detail, but really it's a transformer architecture, and you just use the transformer to do grouping, and then you predict the layers. And we benchmark on 4 different data sets. So standard ones, SecTrack, FBMS, and Davis 2016. So these are standard for video segmentation. But we also benchmark on MoCA. So this is a data set we collected ourselves before in a previous paper. And this is an interesting data set because it's moving camouflage animals, meaning if you just use RGB information, it's not going to be enough for this data set. I'll show you later. It's very challenging. So you have 67 different categories of animals. They can hide themselves into the background, right? At least in the RGB stream. And I'm going to show you some results about this work we can achieve. So on Davis 2016, and this x-axis is how much annotation you need to train your model. So this is in the image scale. It's 10 to the power of 3 number of images. I'm not talking about how many pixels. And this is what we can achieve. You can see it's catching up. Right? And detail we can achieve, like Davis 2016, we can achieve 68, which is slightly better than some of the supervised already. But I think there's kind of potential to even better. And this is the interesting I want to mention a bit, because on MoCA, we are really matching the top supervised methods already. So MATNet is one of the top. We are matching their performance already. You can see 64 versus 63. And also interesting thing is COSNET. You can see here, again, it's one of the top. It's 80 for Davis, but it drops dramatically for MoCA. And one of the reasons is they don't use flow during training. And for MoCA, it's just not possible to solve the problem because it's so challenging if you don't use motion. And we only use flow, we can achieve really good results. I just want to say, motion is quite important in videos, especially for segmentation. Right? So these are the qualitative results. So we never use RGB, we just show it here for you to see what the sequence look like. So as you can see, even the motion is quite complex. We can still do segmentation quite well. You see it's deformable part, we can still do it. And this is the MoCA data set. That's the one I feel very interested, because if you look at individual frames for this fish and for these animals, it's just not possible to find where are they. But if you look at motions, they are just so obvious, right? And these are our predictions. So you can see it's unsupervised trained, so it's okay. And the last thing, I'm going to go quickly because I think time-wise I don't have too much. So it's about spatial temporal coherence, and it's about self-supervised tracking. So this is work we published last year, CVPR. It's a memory augmented self-supervised tracker. And it's Davis 2017 dataset. Again, I don't want to describe the data too much, because I imagine this community everybody knows. The problem setting is you have video clip, you have the first frame annotated, you want to track it. And normally for tracking, the naive way would be you just do correspondence. So for each pixel, if you know which pixel corresponds in the previous frame, just directly warp the mask, right? And we are not the first to do it. So the first one I realized in the recent literature was by Convolution, ECCV 2018, and CVPR 2019 and BMVC 2019. So this is by Berkeley, and this is by ourselves. And the proxy task is by reconstruction. So meaning you want to reconstruct your target frame by borrowing information from the reference frame. And transformer language, you just pass the target frame to get the query, pass the reference frame to get the key, and you compute this dot product, you softmax it, and you multiply with the reference frame because they are the values. Really, you are doing a linear combination of all the pixels to reconstruct your target frame. So once you train this, what you really want during testing time is this affinity matrix and also this thing. But this idea not always work, because we know things are occluded or disoccluded. So some of the pixels, you can't find them. So what you need is you just simple cache a memory band, put multiple frame here, and you just match all of them. When you do reconstruction, you use all of them. So you see, right? And during test time, like I said, you have frames, you just compute affinity, and you warp it, and you propagate the mask to the end of the video. Performance-wise, so Davis 2017 on the left, YouTube VOS on the right. Let's start from the Davis. So you can see these are the supervised learning method. Again, how much annotation they use to train the model. This is on images, not pixel level. So on pixel level, it's going to be a lot more. But this is self-supervised, meaning zero, really, just no training data at all, no annotations. So you can see we are catching up lots of them. And there are new works recently, so I think they can achieve like 70, which is even better. And I can still see some room for improvement for this task. And for YouTube VOS, again, this is the last year table. So I imagine this year the performance will be much higher. But again, the self-supervised learning methods, you can achieve like, among the top 3 roughly. And interesting thing to me is the unseen, because for tracking, you want the model to be generalized to unseen objects. So you can see for self-supervised learning, the seen and unseen, they're really similar performance. But for supervised learning, for some of them, you have very good results for seen objects, but it drops significantly for the unseen. That really worries me, because if your model doesn't generalize to unseen objects, so safety-wise, you can't trust it, especially for tracking. And these are the qualitative results. So I think I'm not going to show them. And to summarize, I think what we can do for video self-supervised learning is I just introduced how to use motion to do sampling, how to do fine-grained localization with audios, how to do video object segmentation with motions. And lastly, I talked about how to track the objects by using self-supervised learning. Okay, that's my talk. Thank you very much for your attention.
Awesome. Thank you very much for the talk. That was fantastic. This field is super interesting. So there's some questions. I'm going to start with some questions that have already been posted to the chat. So the first one is about your flow-based model. And the question is, how many consecutive frames do you use as input to the model? Is it every frame or every nth frame? The
motion segmentation one, you mean?
Yes.
It's just one pair of, so the flow is computed one pair of, from a pair of frame. So the pair of frame, the gap could be varies. It could be just 1 or 2. So Tarek will, describe in detail. But if the consecutive frames are too close, the motion will be very small, and you don't see the object. Sometimes don't see the object very clearly. And in that case, you just use 1 1/3 or 1 1/4 frame. Then the motion will be clear. But of course, the flow are easier to break. But that's okay. It's another community. It's a flow community. They are doing this.
So then a natural follow-up question would be, could you get more accurate segmentation if you could calculate some more accurate motion over more frames?
Definitely. I mean, some of the cases, failure case, I didn't have time to show, but I think Tarek will do that later. It's because of flow. Let's say for some of the fundamental reasons, flow doesn't work. Say water splashing. It's just, flow capture it. And also, slow motion flow tends to fail, and homogeneous region flow tends to fail because you don't have any correspondence.
There's another very related question about the same method, which is in videos where there's multiple objects, usually the flow can be quite noisy. Does the method work well in that kind of setting?
Yeah. Well, to me, multiple objects, that's the next thing we are going to be interested in, because one naive extension will be you use multiple layers. Say, can the model capture multiple objects? Because each object, they are independent. As long as they are independently moving, then you can separate them. But if they are correlated, they're moving together always, then you can't separate them. But as long as they are kind of independent, you can. And on the optical flow quality, I think flow, depth, and segmentation, these three things are very, very correlated. So ideally, you should be able to optimize them all together, and each of them will help each other. So the flow can be improved by segmentation. And flow, if you improve the flow will help to improve segmentation as well. So they are like help each other eventually, I think.
Super interesting. So if somebody else has a question, feel free to raise your hand. Wait, I need to check if there's any hands raised. How do I look? Okay, I can't see any. Or just jump in, actually, just turn your microphone on and say hello. Oh, there's a question from Bastian. So Bastian, do you want to say hello?
So hello, VOT. Thanks for the talk. I think it was really great, and also great to see the progress in unsupervised learning. Now, when I look at the field, there are methods that are fully based on known objects, and clearly they are insufficient to cover all cases. Then there is this very interesting development on purely unsupervised learning, and here the assumption is that we don't have any knowledge about the world. But probably the truth is somewhere in between, because we have a bunch of training data, we have knowledge about some classes, some dynamic classes, some background classes. So what is your view on this? What would be the best way to combine this static knowledge from from common training sets and still combine it with unsupervised learning?
I'll definitely agree with you, because I think the ideal case will be people use self-supervised training to pre-train your network, to warm up it, and you get very good performance already. But for some cases, it's just never possible to improve or to solve with self-supervised. And what you can do is use some small supervision, like very few samples, and improve your network to fine-tune it. Because I think the reason why we do self-supervised, purely self-supervised and purely supervised, is because for research community, it's very difficult to do comparison. If you say, well, I'm doing self-supervised and add some supervision on top, it improves a lot, then it's very hard to compare. Say, is it your self-supervised method is good, or your data annotation is good or useful? So that's why we control the variable on that. But really, if you want to use this sort of idea, I think mixture of them, like semi-supervised, that'll be ideal.
Okay, great. Thank you.
Thank you.
Awesome. So we're in the interest of time, I think we're going to continue. So that was an interesting discussion session. So I just want to point out for all the audience that Wade will be here for the panel session later. So check the schedule, and if you have more questions for him, come back with those questions in the panel session. So we're going to move on in the schedule. And the next thing we have is another oral talk. So this one is for the third place participant in the Rob Motz challenge, which I introduced earlier. So I think this is I think Zhongwan Ru. I'm probably pronouncing that again wrong. Are you ready here?
Okay. Can you hear me?
Yes, we can hear you.
Oh. Okay.
You should be able to share your screen, and then it's all over to you. Perfect. So Zhongwan Ru from SI Analytics got third place in the Rob Motz challenge, and he'll be presenting his method now in a 10-minute oral. So over to you.
Oh. Okay. Hello, everyone. I'm Zhongwan Liu, working as a research intern at SIA. I'll introduce simple re-identification feature association for robust multi-object tracking and segmentation. The presentation will proceed in the following order. The most challenge is instance segmentation and tracking for all COCO object categories to be robust and work well across all 8 benchmarks. As for the dataset, the following 8 datasets are included with various resolutions, frame rate, and viewpoint. To evaluate the performance, HOTA is used to measure detection, segmentation, as well as tracking quality. This is the overall framework of our method. The framework can be basically divided into 2 parts. The first part aims to train the re-identification from the provided detections and extract these re-ID features. The second part obtains the final result through object tracking using the re-ID feature. First, in the re-ID feature extraction part, training set images and annotations with ID labels, predefined detection and segmentation masks are used as input. Then we crop the bounding box images patch and apply the random erasing augmentation to address the occlusion problem and improve the generalization ability of re-ID models. The re-ID model and training process were used by adopting a strong baseline for deep person re-identification. In the inference stage, we extract the 2048 dimension feature after the BN layer as the re-ID feature of each detection. Here I show you our online object tracking process. First, we extract the re-ID feature from the given detection and obtain the appearance of finity matrix using the cosine similarity with the features of the previous frame track. This matrix is used in the Hungarian algorithm and get matched track, unmatched mask, and unmatched tracks. Then the matched tracks are updated and the unmatched detection is assigned to a new track and updated. Finally, unmatched tracks are deleted based on the missing age. We set max age to 12. Our proposed method achieved 3rd place on the most challenge with meaningful performance in overall benchmarks. Here is our tracker demo from static camera video on the most challenged dataset. And this is a demo in Kitty dataset. The tracking is still continuous in the scenes of turning. In the tau dataset, we can see that the tracker works well for zoom scenes as well. Finally, a demo from Davis challenge dataset. Thank you for listening to my presentation.
Awesome, thank you very much. So for those that just turned up, that was the third place method oral for the Rob Motts Challenge at this week's, this year's Rob Motts Challenge as part of this workshop. So we're not going to have questions for the orals because there's going to be a poster session later. So check the schedule, and if you have any questions, turn up to the poster session. So for now, we're going to move on to the next keynote talk, which is from Lorenzo Torresani. So he couldn't make it here live with us today, so he sent in a recorded talk. So there will be no opportunity for questions today, unfortunately. But I'm sure if you listen to the talk and have any questions, I'm sure he'll be interested in answering questions if you contact him somehow. Maybe he'll regret me saying that, but I'm sure he will appreciate hearing from people that are interested in his research. So I'm just going to set up the pre-recorded talk now. Second. Okay, so you should be able to see my screen. And here we go. So to introduce again, Lorenzo Torresani is a professor at Dartmouth and also a research scientist at Facebook. And today is going to be talking about memory modules for video understanding, video architectures, tracking and segmentation. So it's an exciting talk today. So without further ado, let's get into it.
Hello there. So today I'll be presenting video understanding models that interleave inference over the individual frames with temporal reasoning over the entire time span of the sequence. And I will demonstrate these space-time models on the problem of segmenting, tracking, and classifying object instances in video, as well as the traditional task of action recognition. I will begin by presenting mask prop, which applies temporal propagation of mask instances to jointly classify, segment, and track individual objects in video. Mask prop achieves state-of-the-art results on the challenging YouTube VIS benchmark. Then in the second part of my talk, I will introduce timesformer, which is architecture for video classification that is purely based on self-attention. It doesn't use any convolution. And I will show that timesformer achieves state-of-the-art results on several action recognition benchmarks. And it's a lot more efficient than popular 3D CNNs for the same number of parameters. But let me start first by presenting mask prop, which is joint work with Gedas Bertasius at Facebook AI. The problem we consider is object instance semantic segmentation in video. This is a task I assume most people attending this workshop are familiar with. It essentially requires segmenting all instances of a predefined set of classes in every frame, classifying these instances, and also track these segments over all the frames of the video. The performance measure is a modified version of the intersection over union from the still image domain, where the difference is that it also takes into account the temporal consistency of the segmentation by measuring the spatial temporal overlap of the segmentation with the ground truth. So this means that in order to do well on this task, the model must not only segment and classify accurately the instances in the individual frames of the sequence, but it must also track them and link them correctly through time. So in order to address this challenge, therefore, we must design a method that can establish these object instance correspondences across the frames of the video. And ideally, we want to do so by using a unified model that solves all three tasks: segmentation, classification, and tracking jointly so that we can optimize this model end-to-end with respect to a single loss. And we achieve this goal by means of mask propagation or mask prop. So mask prop takes as input a video clip of about 3 seconds in length. And we chose this length because it's a good compromise. On one hand, it's long enough to allow us to train the model to track object instances through occlusions, which are fairly common in YouTube VIS. But at the same time, the clip is short enough that we can fit the feature tensor of the entire clip into the GPU memory. So given as input a clip centered at an arbitrary frame t, the objective of mask prop is to produce temporally coherent segments for all object instances appearing in the middle frame of the clip, frame t. I will explain then how we can use these clip level segmentations and aggregate them to form video level segmentations, even for videos that are very long and that exceed the capacity of the GPU memory. But let's focus first on the task of clip level segmentation. So in other words, here we are focusing on the task of recovering coherent segmentations for all object instances appearing in the middle frame. To achieve this goal, we first extract feature maps from the individual frames of the clip using a single frame model that is also optimized end-to-end with respect to our single objective. Then, given the feature maps extracted from the middle frame, we compute instance segmentations for all objects appearing in the middle frame of the clip. Then the next goal is, for each individual instance detected at time t, we want to find the corresponding segments in the other frames of the clip so that we can effectively track that particular instance through the entire clip. To achieve this goal, we first mask the feature maps from the middle frame with the segmentation of each individual instance. So in this case, we obtain a masked feature map for instance I that zeroes out the values that are outside the segment of instance I. Then we take this feature map and we warp it to match as well as possible the feature maps in the other frames of the clip. And this is done to align the feature map computed from the middle frame to match as well as possible the other frames in the sequence in order to facilitate the task of checking the presence of that particular instance in the other frames of the sequence. So to perform this spatial warping, we use a deformable convolutional module, which is illustrated in the green box on the right. So this module takes as input the masked instance-specific feature map computed from time t, and the feature map computed from another frame of the clip, say time t plus 10. Then these two feature tensors are passed to an offset prediction layer, which outputs motion offsets that explain the relationship between the two frames. So these motion offsets essentially capture the spatial correspondences, defining the alignment between the two frames. Then we pass these motion offsets to a deformable convolution layer that warps the feature map computed from time t to match as well as possible the features of the frame at time t plus 10. Now, a very important point that I want to emphasize here is that this alignment module is trained without ground truth correspondences between the frames. Instead, it is implicitly optimized to maximize a differentiable version of the intersection over union that I presented earlier. So in other words, this module learns to align frames implicitly by maximizing a measure of intersection over union. Now, if the alignment is successful, then we are in business. because then we can simply take these spatially warped versions of frame T and compare them pixel by pixel with the corresponding features extracted from the individual frames of the clip. So this procedure is illustrated here, where at the top you see the feature maps extracted from the individual frames of the sequence without any form of alignment. And then in the bottom two rows, you see the result of spatially warping the feature maps computed just from the middle frame to match the other frames in the sequence. And note that obviously the alignment is instance specific. So for example, for instance I, you see the warping of the feature map computed from the middle frame to match the configuration of the hand in the other frames of the sequence. Whereas for instance J, we have a different type of alignment in order to match the lizard to the instances of lizards in the other frames of the sequence. So now that we have obtained these spatially warped feature maps from the middle frame, we can simply compare them pixel by pixel to the original features extracted from the individual frames. And a simple prediction layer then outputs for each instance a segmentation over the entire clip. So now that we have clip level segmentations, we can aggregate them to form video level segmentation. This is how it's done. We first compute clip level segmentations for all overlapping clips in the video. Then starting from the beginning of the sequence and moving forward in time, we merge segmentations. To do that, we consider overlapping clips. For every pair of overlapping clips, we try to match the instances of one clip to the instances of the other clip. So for example, in this case, we consider, say, instance J in the first clip, and we try to compare it to instance K in the second clip. And we measure this spatial overlap of the segmentation in the frames that are common between these two temporally overlapping clips. And so in this case, we see that there is a large overlap in the segmentations of these two instances for the two frames that are common. And this is a clear indication that these two segmentations are actually encoding the same object instance. And so we can simply merge them to form a segmentation that now spans the two clips. And we repeat this procedure moving forward in time. And this gives rise to segmentations that get longer and longer until at the end we have segmentations that span the entire video for each individual instance. So we trained and evaluated this approach on the YouTube VIS benchmark. And at the time of publication, we obtained the best results on this data set. Our model outperforms the second best system by 1.8% in mean average precision, despite using 1,000 fewer label images and 10,000 fewer bounding boxes. We also tried expanding the pre-training dataset of our model to include also the bounding boxes of open images, as done by the second best model. And in this case, the gain over the second best model elevates to 5.2% in mean average precision, even though we are still using orders of magnitude fewer labeled images. Now, the secret ingredient behind the strong performance of our model is the good alignment that we obtain from this deformable convolutional module. And this is illustrated in this ablation, where we replace that module with optical flow computed from FlowNet, or the alignment obtained by mask track, which is a competing method. And you see that these modified versions of our model with using these alternative alignment schemes perform much worse than mask prop using deformable convolution. Also, from the plot at the bottom, you see that if we reduce the length of the clip, the performance of the system degrades considerably. because the model is no longer capable of establishing this long-range object instance correspondences over the video. Here you see some qualitative results for some particularly challenging cases in YouTube VAS. For example, take a look at the lizard sequence. You can see that our model is capable of tracking through the occlusion. It's robust also to fairly extreme changes in appearance due to viewpoint variations or deformations, as well as large motions happening in the sequence. All right, let me now transition to the second project that I want to present today. This is also work with Gedas Bertasius, as well as Heng Wang from Facebook AI. And this is work that will be presented later this summer at ICML 2021. And the motivation behind this work stems from the observation that self-attention architecture, such as transformers, have emerged as the model of choice for pretty much all language tasks. Now, video and sentences in language share many commonalities. They're both fundamentally sequences. And this raises the natural question of whether this self-attention architecture may actually benefit also video understanding tasks. However, if we look at the state of the art in video classification today, we see that it is heavily dominated by 3D CNN models. And although 3D CNNs have obviously advanced the field, they still suffer from some inherent limitations. So first of all, they impose very strong inductive biases in the form of local connectivity and translation equivariance. And as training sets get bigger and bigger, it's not quite clear that we still benefit from these very hard assumptions. The second observation is that although 3D convolutions are great at capturing short-range spatial temporal patterns, they simply cannot model correlations that extend beyond the small receptive field of the kernels they use. And furthermore, training 3D CNNs is very costly, to the point that it's difficult to scale further the model capacity of these networks. If we look at self-attention architecture, however, we see that they don't suffer from these same limitations. First of all, they impose much less restrictive inductive biases. They're good at capturing both short-range as well as long-range dependencies. And especially in NLP, they have been shown to be quite efficient to train and test. And this has enabled the training of transformers of massive capacity. So based on these observations, we pose the question of whether it is possible to train an effective video understanding model where we replace all 3D convolutions with self-attention operations. And this led us to the design of Timesformer, which I'm going to present next. So our Timesformer is inspired by the Vision Transformer, or VIT, which is a model for still images introduced by Google. So the key idea behind VIT is to decompose the input image into a sequence of non-overlapping patches. These patches are flattened and linearly projected to an embedding space. And then these embedding vectors are passed in raster order to a transformer, which applies a bunch of self-attention blocks one after the other. The classification is done by taking the final embedding for a special token called the classification token, which is prepended to the entire sequence. And this final embedding is then passed to an MLP head that performs softmax classification. It's a very simple architecture. So we tried adapting VIT to video. To do that, we first of all changed the position and encoding of these patches to capture not only the location of the spatial location of each patch, but also the time instant of the patch. And then we had to answer the question, what is the right self-attention scheme for video? So one possibility is space-only attention, which is what the VIT model does. And this consists in comparing each query patch to all the patches in the same frame. And that's what we show on the figure on the left, where the blue colored patch is an arbitrary query patch, and the red patches are the patches it would be compared to under this self-attention scheme. However, the problem is that this scheme never compares patches belonging to different frames, and therefore is unable to capture temporal information. And this is a clear limitation in the context of video. On the other end of the extreme, we could say, let's compare each query patch to all the other patches in the video. This is joint space-time attention. And the problem is that, well, if the video is long, then the computational cost becomes prohibitive because if T is the number of frames in the video and N is the number of patches in the video, this would require T times N comparisons for every single query.
Sorry, I'm having a bit of a bad
We propose instead a more
it's a bit humid here. He had to go to it's a problem that you guys don't have. Every time I switch the camera on, it's kind of growing.
Is somebody saying hello? Hello. Is somebody saying something in the stream? Does somebody have their microphone on? Okay, it stopped. Thank you. We'll carry on.
And it consists in splitting the attention into two steps: temporal attention followed by spatial attention. So in the temporal attention step, we compare the query patch only to patches in the same spatial location, but in the other frames of the sequence. So these are the green patches in this figure, and there are only T of them if T is the number of frames. Then we take the embedding vectors produced by this temporal attention and use them for spatial attention. And again, this requires comparing the query patch to only the patches in the same frame. And so in total, we do only T plus N comparisons, where again, N is the number of patches in each frame, as opposed to the T times N comparisons of joint spacetime attention. Another benefit of divided spacetime attention is that because the temporal attention is separate from the space attention, we can actually use different training parameters for the two layers. We also propose a couple of other self-attention schemes, but I'm going to skip them in the interest of time. So we compared all of these different self-attention schemes by training and evaluating these variants on Kinetics 400 and something, starting from a VIT pre-trained on ImageNet 21K. So a few results that I want to highlight here are that, first of all, the space-only attention achieves quite good accuracy on the kinetics dataset, but it does really poorly on something. And this is understandable because something is a temporal dataset that requires thorough temporal analysis in order to achieve good accuracy. The scheme that does best for both datasets is divided spacetime attention, which produces 1% gain over space only on kinetics and a remarkable 23% gain on something. And this big gain again underscores the ability of this model to capture these long-range temporal dependencies. Divided spacetime attention is also a lot more efficient than joint spacetime attention, as illustrated in these two plots that report the inference cost as a function of spatial resolution on the left and number of frames in the clip on the right. Also, joint spacetime attention has a much smaller memory footprint compared to divided spacetime attention, and it allows us to train our model on clips of up to 96 frames and having resolutions of up to 560 pixels each side. So is space-time attention better than 3D convolution? Well, in order to answer this question, we compared our transformer to two popular 3D CNN architectures, i3D and slow-fast. And we evaluated it on Kinetics 400. And so from this table, I want to highlight a couple of results. The first is that compared to 3D CNNs, transformers has much lower inference cost, even when using many more parameters. So this is great because it means that we can increase the learning capacity and still have a very efficient model. One downside of our model that we discovered in these experiments is that it does require ImageNet pre-training in order to achieve top accuracy. And this is different from 3D CNNs that instead can be trained to top accuracies directly on Kinetics 400 from scratch without the use of ImageNet. However, one benefit of ImageNet pre-training is that it enables very efficient fine-tuning on video datasets, even with few GPUs. In fact, we found that Transformer achieves top accuracy on Kinetics 400 with only 15 epochs of fine-tuning starting from ImageNet. Whereas in the case of 3D CNNs, they require a much longer optimization, even when starting from ImageNet pre-training. And we in fact found that if we constrain these 3D CNNs to use the same training budget as Transformer, they actually produce much lower performance. And so this is a great benefit provided by Transformer because it enables really video model training, even for academic labs that may not have access to the hundreds of GPUs that are required for the long optimization of 3D CNNs. So what is space-time attention particularly useful for? Well, we found it to be particularly beneficial for modeling long videos. The scalability of our approach allows us to train over clips of up to 96 frames. And this is a big change compared to 3D CNNs, which instead are typically limited to training over, say, 16 frames or at most 32 frames. And in fact, we found that these long-range versions of Transformer produce excellent video level accuracy, outperforming the competition on Kinetics 400 as well as Kinetics 600. So a study that is particularly insightful is the set of experiments we carried out on how to 100 million. So this is a data set of long videos spanning 7 minutes each on average. And they show they're actually instructional videos where the humans in the videos demonstrate highly complex activities, typically consisting of execution of several steps in sequence. And recognizing these activities is challenging because it requires recognizing the individual steps demonstrated in the activity, but also the dependencies between the steps. And so it's a good benchmark to judge the ability to do long-term video modeling. So we trained Transformer on this data set as well as slow-fast, and we use several variants of both architectures, varying depending on the number of frames used in each clip, as well as the sampling rate. And we found that for the same setting, Transformer outperforms slow-fast by a very large margin of about 8% for every single setting. Furthermore, we found that Transformers trained on longer clips produce much higher video level classification. For example, the top performance is achieved with a Transformer that is trained on clips of 102 seconds. And so this is a clear indication that, well, when trained on long clips, the model really has the ability to capture these long range dependencies that represent the key steps of the complex activity. So to conclude, I've shown that Transformer has a larger learning capacity, but comparable or even lower inference cost compared to existing 3D CNNs. our method can be fine-tuned from image level pre-training very efficiently on video data. This enables training for academic training of video models for academic labs. And I've shown that it can handle much longer videos compared to 3D CNNs. Now, I mentioned that Transformer does require ImageNet pre-training. It turns out that in follow-up work that we just posted on arXiv, we introduced a self-supervised learning technique that effectively eliminates altogether this image level pre-training, and invite you to check this paper. And I'll conclude by mentioning that we have made available code and pre-trained models for Transformer at the URL listed here. And I do invite you to send me your questions via email. Thank you for your attention.
Awesome. So that was Lorenzo Torsani. I see some people have their hands up. Lorenzo isn't actually here. That was a pre-recorded talk. So unless your question is for me or somebody else, then you should probably ask it to him via his email. I'm sure, as he said, he'll be happy to answer your questions. So we're going to move on now to the next part of the schedule. So we have another oral talk, this time from the second place method in the Rob Motz challenge. So is Jianxing Tang from Alibaba there? If yes, then turn on your video. So we'll just give it a minute. Okay, good. So according to this, we are 10 minutes ahead of the schedule. So I think that's a good time for a 10-minute break. So let's have a 10-minute break, and in 9 minutes now, and in 9 minutes, so yeah, put a break in the schedule because it's going to be a long day. So let's come back in 9 minutes into the Zoom for the rest. Let me give an overview of what's coming up next. So we have the second place and first place orals, and in between them we have a invited talk from Philip Cramble, and then after that we'll have the spotlight session and poster session. So good.
So can you hear me?
Yes. So let's wait 5 minutes and let's start in 5 minutes. Yeah, because there's a break in the schedule,
sure.
so we keep up with the schedule. So now's the time to grab a coffee and get ready for the second half of the first half, the second quarter of this exciting schedule that we have today. So in the interest of the fact that we're probably going to miss a few minutes over the next schedule, let's start about 4 minutes ahead of schedule in about 1 to 1.5 minutes. So in about a minute we'll start. Okay, so let's begin again. So for those of you that have just joined, we've just had about a 5 or 6 minute break that was scheduled in because I was aware that usually these things accumulate slightly to being going over time, which did at the start, but we've managed to catch that back up. So actually we're on time. So we had a little break for coffee, so that's good. We're going to start again now. The first thing is we have a 10-minute oral presentation from the second place method in the Rob Mott's challenge. So I'm going to hand it over now to Jiangxing Tang. Probably like all day I'm pronouncing that wrong again, but I'll let him correct me, from Alibaba Group, presenting his method that got second place in the Rob Mott's challenge. So over to you.
Okay. Hi everyone, this is Jiangxing Tang from Alibaba Group, which is the first author of the second place entry SBT. As we already know, this challenge is to perform tracking and segmentation on 8 benchmark data sets and on all COCO 80 categories. So these requirements directly bring several challenges such as occlusion, camera motion, arrest scenes, as well as the unknown frame rate. Also, this year, the new and more balanced metric, quota, is used to evaluate the final results. So here we show the pipeline of our simple baseline. Since the detections are already provided by the organizer, we only focus on the feature representation and the tracking step. The core of our tracking procedure is the cascade association step. We directly use our appearance model in our last year's solution to TAO in ECCV. The model is trained with collections of datasets from the SOT domain. Over 300,000 IDs are obtained to train a ready model to try to represent anything. Here you can see the model and training details. Besides, two models are used in our solution. Besides the previous SOT model, we also fine-tuned this model with the challenge training dataset. It should be noted that we trained 2 specific models for person and car categories. The dataset details can be found, the training dataset details can be found in our report. Then with the appearance features, we come up with the cascade association procedure. First, the matching is applied on appearance and then matching with LU. Here is the algorithm procedure in detail. It should be noted that the smooth feature is used to perform matching. You can see in the line 19. Then this is the post-association step, the PA module in our framework. We can regard previous steps as box level matching, and this is the tracklet level matching. The motivation is that the tracklet is always broken when occlusion or any other close happen. Thus, this problem can be formulated as a MCPM problem. Minimum cost profit matching in general graph. So why it's a general graph? A GT tracklet can be broken into several pieces, like the example. this track is broken into 3 pieces. You can see the simple example and the solver I listed here. Finally, we show some selected experiments. First, this is a comparison of the 2 appearance models and the ensemble version. You can see the latter one is a little better, and the computation of the 2 models will get much better results. And then this is a matching protocols. You can see the best protocol is we first apply appearance features and then matching with mask LU and then adding post association and the feature smoothing part. You can reach, this is reported on the validation board. We can reach this number. And as a comparison, we can also match with mask LU first and then with appearance feature. You can see that this gain is a little small. So this is the final results. I think you already know it. So here's I also think we might be the best entry with the provided detections and ranked second over all entries. Thanks.
Awesome. Thank you very much for that talk. So that was the oral talk from Jiangsheng Tang from Alibaba Group, presenting the 2nd place solution in this year's WASP challenge. So like I said before, we're not going to have questions for the oral talks at the moment, but very shortly, in about an hour, there will be a poster session where you can ask your questions to all of the presenters of all the papers, all the orals, all the spotlights, and everyone. And also it will just be a general social as well. So turn up, I'll be there, we can have a chat. Hope lots of you come to that. That will be on Gatherly, linked through the CVPR. That's not yet, that's going to be in an hour. Before then, we have still some exciting things. So next up in the schedule, we have Philip Crambull. I'm probably also pronouncing your name wrong. I'm pronouncing every name wrong today, but I will learn next time to practice name pronouncing. Maybe I'll ask people how to pronounce the names for the next time I organize one of these things. So he's going to be talking, he's from the University of Texas at Austin, professor there, and he's going to be talking about point-based tracking in 2D and 3D. And I think we're again ahead of schedule, but I would suggest we just start and then we have more time for questions afterwards and discussion. So over to you, Philip, if you're ready.
All right, yeah, thanks for having me. Let me start up the screen sharing. All right. Yeah, today I'm going to talk mainly about tracking, mostly about 2D, a little bit about 3D. And when I started making these slides, I kind of realized on how sort of lucky we are nowadays, and how much fun tracking is nowadays compared to like when I was a PhD student. Because when I was a PhD student, tracking looked a lot like this, where you either had a very complicated machine learning model, such as multiple instance learning. You had to find or re-identify patterns going through kind of a video and figure out how these patterns change. Or you had some flow-based or graph-based optimizations. Or finally, kind of like back then, everybody's favorite graphical models, which were just like a page long of math. And it worked for some classes and it didn't work for others. Now, fast forward 5 to 10 years, and things changed a lot. And by far the most dominant theme in tracking is tracking by detection, where we first just use a very powerful object detector, and then we simply just associate these detections to each other. Now, the association can be as simple as just measuring the overlap between boxes, or maybe kind of advecting boxes through time using a Kalman filter and then measuring overlap. It can be as complicated as trying to use the detector itself to advect these boxes through time, and using sort of the bounding box regression of the detector to then help us track objects through time. And really, to me, the most appealing property of this tracking by detection pipeline is it sort of splits the problem into two. On one hand, we have object detection. This is very well defined. There's lots of papers on it. There's lots of nice data sets. And then on the other hand, we simply have association, which is kind of just matching boxes to one another, which again is not an overly complicated problem. Now, another appealing property of this is that every time object detectors get better, our trackers will get better. And for me, this is a really exciting property, because as detectors get better, the association step can actually get much simpler. And so we can kind of build up beefier and beefier detectors and use dumber and dumber association steps and get away with it. And so my hope is, in the long run, eventually we'll actually get to a point where we maybe don't even have to do association anymore. And I'll get to this at the very end of the talk on how I think we can maybe get away or get away from explicit association. Now, how is association done nowadays? I already alluded to one way of doing it, which is simply just using overlaps. And so this is more kind of a geometric association. I see there's a question in the chat, which I'll...
No, it was just me telling people to ask questions.
I see, okay, yes. Yes, if you have questions, please interrupt me at any time, and I'll answer. Yeah, so one way of associating sort of these boxes is a geometric way, which is just looking at the overlap of these boxes. Another way of looking at associations is to compute some sort of re-ID feature. And then simply just using the distance between two of these re-ID features as sort of an association score. All right. And so these are kind of the two most popular ways to associate objects to one another. Now, I'm going to present a third way of doing association by first switching out how we think about object detection. And then I'm going to show you that there's actually a very trivial way to do associations inside of a detector if you just switch the output of the detector around a little bit. And what we're going to do is, we're not going to detect objects as these rectangular boxes anymore. We're going to detect them as individual points. And so for each object, we'll just represent it by one single point that lies at the center of the bounding box of that object. Right? And we can build an object detector that produces these centers. The way we did this about 2 years ago was we simply just used the convolutional network and then produced a heat map where each peak in the heat map corresponds to one of these centers of objects. And then in addition to this, we also produced an additional 2-channel output that regressed to the width and the height of each object. And so with these heat maps, with these points and the width and the height of objects, we can now go and produce bounding boxes. Just a few months ago, we also showed how to incorporate this into kind of a longer 2-stage pipeline, where the first stage, kind of the point-based detections, are now actually something that's similar to object proposals. And then we can have second or cascade stages after that then will go and refine this these object proposals. And for about 13 days, this was state-of-the-art on Cocoa before it got beaten by transformers. Now, what's more exciting about the points in the context of this talk is points actually allow us to reason about tracking and the correspondence between objects in a different way. So let's look at 2 different detections here. one in frame t-1 and one in frame t. Now, what is kind of the correspondence, or what is the difference between these two detections if you think of objects as points? Well, the difference between them is just a vector. The difference between 2 points is simply just a vector in a metric space. And so in order to track objects through time, if we detect them as points, we can simply predict these kind of difference vectors, these offsets, and then just use the offsets to propagate the track backwards in time. So that's what we did for ECCV last year. There's a couple of steps involved in kind of taking a standard point-based detector and making it into a point-based tracker. The very first thing we do is, instead of just looking at the current frame when we do detection, we now also look at the previous frame. So we'll feed in 2 color images concatenated together. Now, in addition to this, we'll also feed in all the tracks or all the detections that we have from the previous frame as sort of heat maps that tell us just, hey, here are the locations of objects that we already know about. And then we feed this through a standard detector that again produces a heat map where a local optima, or kind of a little peak, corresponds to centers of objects. Now, the only thing we need to do if we want to track in this framework is we also need to predict an offset. And similar to how we regress to the size of the bounding box, we can again just regress to 2 values that tell us, hey, look there if you wanna figure out where the object came from. And then a simple nearest neighbor matching will give us tracklets. Right? So that's how you build a point-based detector and tracker. I hope I was able to show you that this is actually a very simple process. Once you have a detector that operates on points, it's just a matter of adding 2 more output channels to it to regress to this offset. This detector can now jointly reason about both detections and associations in one single network. And it actually benefits both in terms of detection and in terms of association. For detections, the benefit really comes from the fact that we see previous detections as an input to the network. Now, for association, these previous kind of detections or these previous tracks can also help us snap associations directly to individual points. And we do this, we train this network to actually, under some data augmentation, to always snap to kind of noisy perturbations of existing detections. Now, finally, the kind of, to me, one of the most fun properties of this tracker is that we can train it without any tracking data. So we can train it on just COCO images, on still images, by taking one image, then applying data augmentation, simply just scaling and shifting the image a little bit, and then also scaling and shifting the corresponding ground truth annotations, adding a little bit of noise to the ground truth annotations so we don't overfit, and then learn to regress to these kind of augmented and slightly perturbed ground truth annotations. And so that will allow us to train a tracker on just static images on the COCO dataset. Now, back then, ECCV already feels like a long, long time ago, but back then, our method performed quite well compared to the state of the art. It came in second on the MOT 16 challenge and first on the public MOT 17 challenge. And compared to the first place on the MOT 16, it was quite a bit faster. Now, in terms of runtime, ours here actually includes both detection and tracking. So this is done both together in kind of one forward pass through the network, while the prior work here only includes re-ID or tracking. It also works quite well on Kitty. Now here, I must say a disclaimer, the main gains we actually get are not really because of better association. The main gains are really because we have a better tracker, a better detector. Again, it's quite fast here, that 92 milliseconds are combined detection and tracking performance. And finally, I think one of the most exciting things is that we were able to train a kind of a COCO model and use the COCO model kind of to predict offsets and then track COCO objects. Now, this is a little bit messy here, and you see plenty of ID switches, but keep in mind that this model was trained on just static images. There has never seen any correspondences, has never seen any sort of motion during the training itself. Now, we also extended this framework, both the point-based detection and tracking framework, to LiDAR-based 3D detection. And for LiDAR-based 3D detection, the input is a sparse LiDAR point cloud, represented here, and the goal is to produce 3D boxes that correspond to kind of pedestrians, vehicles, or other obstacles on or along the road. Now, the way we build a 3D detector and tracker is we first project the LiDAR point cloud sort of into this overhead view. And so this overhead view is a metric map that just corresponds to actual distances in the real world. Then we go detect objects in this metric map, again as points, and we use kind of a very similar architecture to the previous image-based point-based detector, where the input this time is a LiDAR scan. It's actually not just one LiDAR scan, it's a bunch of LiDAR scans kind of overlaid on top of one another. And I'll get to why in a second. Then we use a sparse 3D convolutional backbone to get a map view feature map. And then from this feature map, we'll predict kind of where centers of objects are, again, just by predicting a heat map. We regress to all properties of these objects, kind of 3D box size, orientation, and also velocity of the vehicle. Now, the cool thing about the metric map is that the velocity of the vehicle here actually corresponds directly to where we have seen the vehicle last. So we can use this velocity estimate to do tracking. So the difference between two objects, or between the same object, between two time steps, is exactly its velocity, well, scaled by the temporal resolution. And to estimate this velocity, we need multiple scans of the LiDAR point cloud, because the LiDAR point cloud can tell us how fast objects move if we overlay multiple scans on top of one another. Now, this works quite well for 3D detection. So we won the New Scenes Challenge NeurIPS, and even now at time of publication, the method actually performs quite well. It's still competitive in the top. And on New Scenes, the majority of all methods actually build on this center-based detection framework now. On Waymo, we came in second at the Waymo Challenge at CVPR this year. And also for tracking, kind of it works much better than kind of standard alternatives such as common filter-based trackers. Plus, again, it's on top of detection, it's just blazingly fast. It's 1.3 milliseconds of additional computation once you have the 3D detections. And the simplicity is really what kind of sets center track and also is kind of center point apart from other trackers. All right. Now, I was hoping, I hope I was able to kind of show you that by just using very powerful detectors, we can dumb down association a lot and still get very good tracking results. Now, in kind of later parts of this talk, I'm going to show you some other benefits of how what I like about this tracking by detection framework and what other things that we can borrow from the object detection literature. And the one thing that I really like about this workshop and this talk is that it really went beyond just this one data set. And it pushes tracking towards kind of trying to track everything that exists. And so kind of one step in this direction that we took was trying to detect everything that we can find. And so one way you could do this is you can just go onto the model zoo of your favorite detection library and just download all sorts of models and start to run it on your favorite image. So this here is an image kind of a car that I took that is illegally parked close to an apartment we used to live. And I just tried to see, well, on this random image, how well do these detectors work? Now here I'm going to show you the MS COCO detector, and it already kind of gets like cars well, it gets pedestrians well, it gets kind of even gets kind of a motorcycle. It doesn't really get any of the signs. Even a Pascal detector already does quite well given current detection technologies. And an Elvis detector really starts to get into the nitty-gritty details of the scene. Now, the only thing that the Elvis detector in this scene actually didn't get is any of the pedestrians. So it didn't get the pedestrians or the people anywhere in the scene. And that kind of speaks to kind of sort of the shortcomings that each individual data set have. We currently in computer vision don't really have a detection data set that encompasses all objects that you would ever want to detect and later track. And so what we are interested in was trying to see, well, can we train a detector on more than one data set? Ideally, can we train a detector on all large data sets that we have available? And to kind of look at this problem in a bit more detail and to appreciate why this is actually quite difficult, let's look at how we train a detector on a single data set first. So on a single data set, we're given images and corresponding annotations. And we're going to ask a detector to just produce boxes that match these annotations. This is an overly simplified way of looking at it. But the important thing is, for each data set that we do this, we have a separate set of kind of a separate bag of tricks. So if you train a detector on MS COCO, this usually just uses default settings of the detector itself. If you switch to open images, you're going to use maybe class-aware sampling. You're going to change the loss function. If you go to Objects 365, again, different loss function, different sampling strategies. That's because each data set has a slightly different data distribution. And so if we just throw all of these data sets together, this is actually not going to give you a very good detector. Now, what we're able to show in a paper that is on arXiv now is that if you train this detector right, you can actually train one single detection model that works as well on all data sets as individual detectors work on individual data sets. And kind of the very simple trick is to treat each data set as kind of its own sort of thing or its own entity, use losses and best practices that we know for each data set, and then simply just share the detector. So we sort of train on all data sets together. But the only thing that these training loops share is kind of the forward and backward pass through the detector. And then we have a separate bag of tricks, separate losses, separate sampling strategies for all data sets. And then we do this by just sampling images from all data sets at kind of the same frequency so that the detector sees the same number of images from all data sets. And we keep the outputs of all detectors separate. And so that itself allows us, after a little bit longer training, to train a detector that works as well on all the data sets as each individual detector would on an individual data set. But if you think of kind of building a tracker out of this, there is one issue. And the issue is that we actually get duplicate detections. If you look at the outputs here, we now had outputs for each individual data set. And so now we start to produce boxes for each individual data set. Now, you could track within each individual data set and just say, okay, we'll just deal with the duplicate tracks or run some sort of non-maximum suppression, but that's not a very scalable or very attractive solution. what we want to do instead is we want to realize during training that cars, vehicles, and cars from other data sets are kind of the same thing, and we should merge this into a common taxonomy. And it turns out you can do this, again, quite efficiently by just looking at kind of co-occurrence or correlations between outputs, either on labeled data, where you just want to maximize some sort of accuracy measure, or on just a set of unlabeled images where you just want to make sure that outputs of different heads kind of that are similar somewhat grouped together. And you can do this in a very simple linear programming formulation that will then tell you which classes or which outputs to merge together. And so that allows you to build a detector and later a tracker that kind of reasons about a joint set of concepts across multiple different data sets without ever having to annotate or link up these data sets manually. This approach won the Robust Vision Challenge last year by a reasonably comfortable margin. And it also performs very well if you look at kind of zero-shot generalization to new data sets. And what we do in this experiment is we train this detector on 3 data sets, which is COCO, or actually 4 data sets, COCO, Objects 365, Open Images, and Mapillary. Then we compare this to an ensemble of these models, so just all of individual models just concatenated together. And then we have kind of one model that outputs all the outputs, and then a unified model down here. And you can see on this zero-shot generalization, without ever having seen a VOC, a Pascal image, we actually do better here with our unified model than if you would have trained on just Pascal. Now, this also holds, or we also get very close for cityscapes and kind of get into the ballpark for other data sets as well. And this is without ever having seen a single training data set, a single training image for any of these data sets. All right, so I hope by now I was able to show you that kind of putting a lot of weight in tracking by detection on detection is a very kind of interesting direction. Now, in the last few minutes of the talk, I kind of want to highlight some ideas we have to hopefully get rid of this association step altogether and kind of make everything just a variant of detection. And then in order to do this, I want to first take a step back. And what I want to do is I want to look at how does tracking by detection currently work. And then I'm going to give you a slightly different interpretation of what I think tracking by detection should look like. And so what tracking by detection does is it first extracts boxes, and then it looks at pairwise connections between these boxes. So we'll start to link up pairs of boxes, either in a greedy manner or through some global optimization. Now we do this sort of for all possible outputs. And then just kind of run either, again, Hungarian matching to get a one-to-one mapping, or just some simple greedy association. Now, a different way to look at tracking, especially when you look at global tracking, is instead of associating objects or boxes to one another, we can associate them to some sort of queries or prototypes. And so let's say I have some sort of prototype or query here. And instead of associating the boxes to each other, I'm just going to associate all boxes to this prototype. I'm going to do this for other boxes as well, or for other tracks as well. All right. And I'm going to just start enumerating these. And so you can think of these prototypes or these boxes as just tracks. So I'm going to associate boxes to tracks now. Now, if you look at this the other way around, if you look at this association in terms of associating a track to boxes, well, what this corresponds to is essentially picking a set of boxes that we think kind of correspond to one to the same object, right? Now, if we don't do the picking in kind of a hard association, but if you do it in a soft association, you can think of picking sort of a distribution over likely objects or likely boxes that correspond to an individual track. And this soft distribution is exactly the same as a tension in a transformer. And so what we can do is we can build kind of a global tracker by simply having queries, which in our case would just correspond to kind of generic trajectories. And each of these queries now picks a box from each frame. And it associates that box to that query. And that association now gives you kind of a global trajectory. Now, we don't just do this for one query, we produce multiple queries, similar to, for example, how Detter would produce multiple object queries, and can then kind of produce this global association as just a single layer in a deep network. We have some preliminary results on this on Tau, and there it works quite well. It doesn't reach the performance of the last year's challenge winner, but it outperforms the baseline by quite a large margin. Really, the fun thing here is that this now is just a single layer in a network. So there's no separate association step for global tracking. There's just one layer, boxes come in, and out come kind of these associations, these global associations. And another way to look at this is it's actually kind of a transformer style detector for tracking. And so instead of kind of detecting individual objects, individual boxes, now we detect entire tubes that kind of correspond to trajectories in a video. And I hope we'll have the archive of this ready by the end of the summer. But if you have any kind of intriguing questions about this, feel free to either ask me here or send me an email later. With this, I'm very happy to take some questions on kind of and start a discussion on how we can move maybe more towards detection in tracking. And I'm very happy, I understand this is going to be a very controversial topic, and I'm very happy to kind of start a nice little discussion if we should do more association or more detection. Thank you very much.
Awesome, thank you for your talk. We have definitely some time to have a good discussion, to have some questions. So I already see some hands, so I'm gonna open it up. Let's go for Christopher.
Yeah, thank you. Really enjoyed the talk, Philip. Thank you. One question, I believe that whenever you say detection, you really do mean detection and recognition are getting bundled together, because I presume that you're including the feature space or whatever you have to generate in order to be able to start to diminish the value or the need for association. Is that correct? And if so, how do you intend to, what do you intend to do with the re-ID component that's so critical to this?
Yeah. So I think, I mean, the one thing I didn't mention actually, there's a very neat connection between in the last part between the transformers and re-ID, and you can actually show that if you just had a transformer that's sort of one layer and that just does a dot product between your features, that is softmax loss for re-ID. And so yes, we do concatenate the feature that we get from the detector to as an input to the transformer, and just backpropagate through all of it. And that's how the association in this one transformer layer works. In the offset-based tracking for kind of center track, we don't have any features whatsoever. There are versions of it, that use re-ID features that actually work better than just an offset. If you look at the MOT data set, we found it was fine to get away without.
Awesome. Let's have Katarina next.
Thank you, Philip, for your talk. My question is, how long are those query trajectories? How many frames they span? And how does the decoder look like? Like, do we extract features at every individual frame? Do we run 3D convolutions and you associate the queries? Do you do it recurrently?
Yeah. So I completely glanced over all of these details. The first question: how long is the temporal window? I think we tried up to 64. Then the second question: where do the queries come from? This is by far the trickiest detail. So you can actually not use queries in the getter style where these are just free parameters. You have to use queries that correspond to boxes, like they correspond to box features. And what we do is we just use queries that correspond to kind of an arbitrary feature along a track. And then when we run for sequences that are longer than 64, we still have to have some sort of greedy association between these kind of longer trajectories.
Right, so then they don't incorporate global trajectory, motion, and shape. They incorporate maybe the appearance that we got from one frame by detecting an object, for example, right?
Yes, it's so, I mean, it's a bit hard to conclude what the transformer latches onto. It does have access to positional embedding. It doesn't seem super important as far as I understand, but it definitely uses something similar to re-ID features.
Great, thank you.
Awesome. Let's have Bastian next.
Yeah, so thank you very much, Philip. Great talk, very inspiring. Also, the outlook, I found that very interesting. This new perspective on more global tracking. We went in a similar direction with STEMSEC at last ECCV, where we looked at a small temporal window, so about 16 frames, and we performed basically a center voting to discover tracks, so where tracks were basically found as a grouping process, and this seemed to be quite effective. So I have much hopes for your work. I think that is on a very good track. It will work quite well.
Yeah, I mean, I really hope it's gonna work, and I'm very well aware that we're not the first ones to discover this. I think Lorenzo's work that he previously presented is also in a very similar spirit, and I like the fact that we're kind of getting more and more towards global tracking. I wish at some point it would just be just one thing.
Yeah, no, I didn't want to apply that. It's it's big idea space, and it's fascinating to explore that.
Yeah. Thank you.
Okay, next let's have Ali.
Hey, so yeah, thanks for the talk. So mine is just an open-ended question. So the way I see your upcoming work is that in the tracking pipeline, you're kind of offloading most of the tracking to the detection part of the paradigm, the tracking by detection paradigm. So what's your general opinion on doing sort of the opposite, as in that you don't use or use very little detection, but rather focus more on the association? And by this, what I mean is that you kind of treat individual pixels as entities and then just try to group those directly without having to go through the detection part of the pipeline. Yeah. And I guess this is something that was kind of popular back in the robotics community a while back, but yeah, I just wanted to hear your opinion on this.
Yeah, I think under the current metrics, this is an uphill battle. And I'm not sure if it's the metrics are to blame or if it really is just harder. I generally like to put more work on detection just because it's kind of, you can benefit a lot from the progress in that field. That's, I think, among with semantic segmentation, I think it's one of the most active fields in computer vision right now. And you see numbers on COCO just rise kind of within like 10 points within a year. So which is like insane. And so I feel like trying to keep up with this on kind of the low level association or sort of flow based association might be quite hard. Where low level association may be able to help is when you reason about objects that are not easy to detect or where we don't have large scale data sets. And I mean, I don't know what these objects might be, but there's definitely a niche in which objects are hard to detect and they might come out better with motion cues.
Awesome.
Okay,
So
thanks.
there's a few questions on YouTube, so I can ask those. The first one is from a Christian. It says, does the frequency of LiDAR influence the results of the 3D center point?
Yeah, so I think we haven't looked at the frequency as much as the actual number of lanes you get. So kind of different, like LiDAR sensors of different costs will produce different horizontal resolution. Different vertical resolution. And so that does make a big difference. And also in terms of methods, kind of second stage refinement on a LiDAR that doesn't have a high resolution actually doesn't work very well, while it works quite well if you have a higher resolution LiDAR input. But we haven't looked at the temporal resolution much.
Super. So I'm going to ask one more question from YouTube, and then we'll have Tobias's question, and then we'll move on. So first from YouTube, the question is, in terms of your transformer model, how does it work for partial or full occlusion?
Yes. Yeah, so that's one thing we're definitely still exploring. So it turned out, like, I mean, in theory, it should be able to handle it. In practice, that actually has been a major pain. Trying to kind of get it not to associate to some spurious detections when an object is not occluded. And it has to do with the fact that in the transformer model, we have the ability to say that we don't want to associate it to any box in the frame. So there's a special output for each trajectory in the association that says it does not want to be associated to anything in this frame. And so in theory, it can handle kind of occlusions or like detections that disappear and reappear. In practice, kind of trying to balance this has been a bit challenging.
Super fascinating. So let's have the last question from Tobias.
Yeah, so thanks for your talk. My question is about, so your center track model, what I particularly liked about it is that you have this tracking condition and detection as well. So the not only the tracking benefits from the detection, but the detection benefits also from the tracking. My question is, so you have input, the input to the transformer is also bounding boxes, right? So is there also a mechanism to benefit from the temporal information for the detection? So is there some infilling happening or anything?
The short answer is no, and I wish there would be. I think that's the very short answer. Yeah, I mean, we tried kind of trying to fill missing detections by just completing the tubes, but it hasn't worked that well yet.
Thanks.
Awesome. So thank you very much for your talk and the question session. Philip, are you going to be able to be around for the panel session later? Yes, awesome.
Yeah, I'll be here.
Philip will be around later for the panel session as well. So hold on to your questions. There'll be a long hour session of questions to all of the panelists then. So at the moment we have the final oral talk from the challenge participants. So the winner of the Rob Motz challenge will be presenting next. And after that, we'll have 10 minutes of short 1-minute spotlights. And then we will have a poster session / social. I highly recommend all of you that are here in the Zoom that have access to the CVPR attend that it'll be a good opportunity for casual discussion and talking with all of the different people presenting their work. So I highly recommend you stay around for that. But first, let's move on to the next oral talk. So Dongzhu Wei, are you here? You want to start sharing your screen?
Yeah. Can you hear me?
Yes, we can hear you. Fantastic. So let me introduce you while you start sharing your screen. So it's my honor to present the first place method for the RobMots challenge this year. Presenting their work will be Dongzhu Wei from I'm definitely pronouncing this wrong, Zhejiang University / also with the Alibaba Group. So feel free to correct my pronunciations yourself. So they'll be presenting a 10-minute oral on their winning method of the RobMots challenge. So over to you.
Okay. Sorry for my authority. I can't record my screen. I have to quit and reopen it. Wait me for a few minutes, please.
Yeah, no worries, no worries. We have some time, so it's okay because the spotlight session after this is scheduled for 20 minutes, but there's only 11 minutes of spotlight. So
okay, I'll be here a few minutes later.
Okay, so we're waiting a couple of minutes. Good. So I guess grab a coffee, and we'll be back in a minute.
Okay, I'm back. Can you hear me?
Yes, we can hear you. Can you manage to share your screen now? Is that working?
Yeah, maybe. Let me try. Okay.
Seems like it's working. Fantastic. So let me introduce you again, and then you can start. So it's my honor again to present the first place for the RobMots challenge this year. Dongzhu Wei from Zhejiang University. So take it away. There's a 10-minute oral presentation on the method that won the challenge.
So I begin. Hi everyone, I'm Dongzhu Wei from Zhejiang University. Today I'm going to talk about our recent work, RobTrack, a robust tracker baseline towards real-world robustness in multi-object tracking and segmentation, which is the first place solution in RobMots challenge. This work is done during my internship at Alibaba. Given an input video, the goal of multi-object tracking and segmentation is to segment all the objects and assign consistent IDs to them throughout the video, which has a wide range of applications in autonomous driving and safety monitoring. For example, in this figure, we should detect pixel level masks for objects in all the frames and identify them in different frames consistently as shown in consistent colors. However, most existing MOS benchmarks focus on tracking a small number of categories, such as persons and vehicle, in specific scenarios like driving and monitoring, which can reflect tracking performance in full set real-world scenarios. Therefore, the RobMots challenge made higher demand that trackers should segment and track objects belonging to 80 COCO classes for 8 MOS benchmarks in total. In the meanwhile, bias to one specific class or one specific benchmark is not allowed. Apparently, this extremely raises the demand of tracking robustness, which I believe is also the essential intention of holding this challenge. To achieve the real-world robustness, we divide the task into robust detection and robust association so that we can optimize the tracking robustness from two aspects. Specifically, given input video frames, our robust detection predicts masks for all the objects in the video, where we apply massive instance augmentation during training to improve generalization ability and apply patch-based mask refinement during inference to improve mask details. Then we divide the detected objects into two supercategories, common objects and general objects, to enable separate and optimal association for both of them. So in our robust association, we designed an example 4-category tracker, which consists of 2 expert trackers for common objects and general objects separately, to track different objects in different ways. Then we merge checklists from different trackers and feed them into our offline relinking module to fix broken trajectories and obtain our final tracking results. So now let me introduce the details. First is our robust detection. During training of our detector, we apply massive instance augmentation. The implementation followed the paper of copy-paste, which is a work of CVPR 2021. Particularly, the augmentation contains 5 steps. Step 1 is to randomly select 2 images from the training set. Step 2 and 3 is to randomly apply scale jittering and horizontal flipping to the 2 images. So now we have a series of randomly generated images. So the step 4 and 5 is to select a random subset of objects from one of the images and paste them onto the other image. Such augmentation greatly enriches training samples for detection. Besides, these generated unseen and diverse object combinations significantly improve the generalization ability of our detector, and thus further improve the detection robustness. Here we show an example to see the difference between with and without the augmentation. As shown in this figure, if we train our detector without augmentation, we can detect all of the 5 selected objects. However, if we train our detector without augmentation, this occluded person and this small backpack were missed, which shows the effectiveness of MI in improving detection robustness. After obtaining coarse object marks, we further apply patch-based mask refinement during inference to improve mask details. The implementation followed the paper of boundary patch refinement, which is also a work of CVPR 2021. Specifically, the refinement contains 4 steps. Step 1 is to crop patches along the mask boundary to obtain patch proposals. Then step 2 is to filter out overlap patches based on non-maximum suppression to decrease proposal numbers. After that, we refine boundaries for each patch and reassemble them to construct the full mask in step 3 and 4. Such refinement can further improve our mask details. For example, in this figure, with this refinement, we can obtain masks with precise boundaries with no object overlap. In contrast, without refinement, the boundaries are very coarse and the overlap exists between the person and the baseball bat. This is our then is our robust association. First, let me introduce our example 4-category tracker. This tracker consists of 2 expert trackers, a common tracker and a general tracker. So the first is our common tracker. Therefore, different supercategories. Specifically, the common tracker follows spirit of QD track, while we remove the detection part and reserve the re-ID part of its joint detection and embedding framework. We claim that this design has 3 advantages. The first advantage, this design uses RY pooling or RY align to extract re-ID features, thus can share one global feature among different instances, which serves our conjecture that common objects like person and vehicle require more contextual information for re-ID. The second advantage, this design enables us to utilize the coincidence re-ID sampling presented in QD-Track, which can create much more re-ID samples than sparse re-ID sampling. This can be seen from the difference between these two figures. Sparse sampling only uses ground truths to create instant matching pairs, which provides few re-ID samples. In contrast, coincidence sampling uses dense region proposals to create instant matching pairs, which provides massive re-ID samples. The third advantage, with such strong re-ID features, we can utilize bi-directional softmax matching to associate objects only based on appearance clues. To establish connections between objects in different frames, it requires the appearance similarity is the maximum for both sides. In our experiments, we observed that this expert tracker can enable robust detection association for common objects. Then for general objects, we simply follow deep sort and remove its common filter part to achieve appearance-only matching. The re-ID model is trained on extra SOT datasets with more than 100,000 of instances, which enables robust re-ID. Additionally, we apply IO matching after appearance-based matching to improve the association recall. By merging the tracklist from the two expert trackers, we can obtain the full online tracking results. After the above online tracking, we further apply our offline relinking strategy to fix broken trajectories. This is also appearance only. For example, both of the two checklists above belong to the same luggage, and both of the two checklists below belong to the same person. To relink these broken trajectories, we first compute all of their global appearance features averaged over all the frames. Then we relink any two of them as the same ID if their appearance similarity is large enough. Experimentally, this offline strategy further improves our association robustness. In our experiments, we conduct extensive ablation studies to demonstrate the effectiveness of our major components. As shown in this figure, the massive instant augmentation improves HOTA by 1.8%. The patch-based mask refinement improves HOTA by 0.5%. The offline relinking strategy improves HOTA by 0.3%. The ensemble tracker surpasses the two single trackers by 0.9 and 1.4% respectively. These improvements show that both detection and association matter in robust tracking. Comparison with other methods also demonstrates the significance of our method in robust tracking, making us achieve the first place in this challenge. And that's all. Thank you for listening.
Awesome. Thank you very much for that presentation. Fantastic. So that was the first place for the RobMops challenge. So for the next thing in the schedule, we have 1 minute 1 minute spotlight presentations for all of the 7 papers accepted to the workshop as paper submissions, plus 4 papers accepted as challenge entries. So there'll be 11 1-minute orals. So we'll have the 11-minute pre-recorded spotlights, playing now, and then afterwards we will move to the poster session on Gatherly. So let me start the spotlights. Give me a second. Okay. Here we go. So without further ado, the 11 spotlight presentations will play one after another, presenting the 7 accepted papers plus the 4 accepted challenge entries. So I'll let them speak for themselves for 11 minutes.
Hi, my name is Anirudh, and I will be presenting a paper titled Object Propagation via Interframe Attentions for Temporally Stable Video Instance Segmentation. done as a part of my internship at Harvard University. In this work, we identify and alleviate the problem of temporal instability in video instance segmentation. Temporal instability results in missing detections and poor quality segmentation masks, which harms the performance in video instance segmentation methods. To this end, we leverage an interframe attention mechanism to propagate the missing instances. An attention mask is propagated using the cross-frame affinity from the frame history if the object is not detected at the current frame. The attention map is then applied to the backbone features, and a mask head predicts the corresponding object segmentation mask. We demonstrate state-of-the-art performance using the mask RCNN pipeline on ResNet 50 backbone with a simple instance filling approach. We look forward to discussing this work with you at the poster sessions.
Hello everyone, my name is Manuel Sarmiento. I am the author of this paper, Spatiotemporal Context for Action Recognition. This work has been done by me and my colleagues, David Baras and Elisenda Bou from Moto. What we wanted to do in this work is to use non-aggregated temporal information as well as spatial information to improve the modeling of factor relations. To do so, we employ slow-fast as our backbone network, and we temporally pull the feature from the slow pathway to obtain our spatial context. And consequently, we spatially pull the fast pathway to create the temporal context. Then, following common state-of-the-art approaches, we use a royal line and precomputed detection to extract actor features. We conserve the spatial dimension of these features to better model the actor interaction with its context. To enrich these actor features with the scene information, we use two cross-attention blocks. As our experiments show, there is relevant information in the usage of temporal feature for modeling actor interactions. Thank you very much.
Foreground segmentation is a major computer vision task that detects changes in image sequences. The premier methods are based on a final supervised fine-tuning step, achieving excellent results, which are superior to more general systems that do not undergo fine-tuning the specific scene. Because manual tagging is expensive, this paper proposes substituting the unlabeled data needed for the premier supervised method with an automatically created artificial database. It is based on an unsupervised Wix foreground segmenter that extracts good objects from the training images and randomly inserts these objects back in their original position into a background image. It is especially pertinent to static cameras, as the objects found are automatically in the right location, being in the right size, color, and shape, and in the right lighting condition. We showed that in this way there is a marked improvement in results on scenes from change detection 2014 dataset, especially since in our method the foreground objects are taken from the scene itself and placed in places that suit them. Thank you.
Hi, this is higher order multiple object tracking for crowded scenes, which is the joint work of Andrea Hornakova, Timo Kaiser, Bodo Rosenhahn, Paul Svoboda, and Roberto Henschel. The lifted disjoint paths formulation is a powerful model for multiple object tracking, achieving state-of-the-art results because it integrates higher order information. But due to its NP hardness, it was not applicable for large video sequences, especially in crowded scenes. To tackle this problem, we introduced a novel approximate LDP solver and integrate it into a tracking framework. For a given detection set, we first create lightweight features to classify if detections belong to the same trajectory or not. Based on this, we create sparse LDP graphs. And finally, this is the highlight, we solve the problem with our novel approximate LDP solver based on a dual decomposition framework. The solver achieves nearly the same tracking results than an optimal LDP solver, but with a highly improved runtime and is scalable to large crowded sequences such as MOT20.
MoveX is an object detection technique that combines motion vectors present in H.264 encoded video with parallel processing in order to reduce detection latency in any off-the-shelf object detector. In modern keyframe-based approaches, the object detector dictates the lowest latency possible, creating a bottleneck. However, through the use of our novel optimistic sparse detection propagation algorithm, the latency of object detection and the latency of detection propagation have been decoupled from one another using parallel processing. In our evaluations on MOT20, we found that using this approach resulted in 10 times faster object detection when compared with the original model. When latency isn't a problem, high resolution inputs the object detector gave a nice boost in accuracy, and it can all be run on low-cost hardware. Check out our paper for more.
In this work, we propose to use trajectory forecasting on top of multiple object tracking methods to improve their performance. Given an object being tracked, we use a mixed density network to estimate its next position, in combination with beam search technique for trajectory exploration. Mixed density networks output parameters corresponding to a set of Gaussians, with which we build a Gaussian mixture model. From such a distribution, we sample the offset corresponding to the motion of an object and build several trajectory hypotheses by using beam search. We propose to reconstruct the track information of an object being occluded by doing a spatiotemporal match between a forecasted trajectory and a new detection assigned to an existing track. We use TrackHe on top of 2 existing trackers and show very interesting results on how trajectories could help the multiple object tracking. For more information, stay tuned to the oral presentation and come to the poster session.
Hi, today I am presenting self-supervised video object segmentation by motion grouping. In this paper, we consider self-supervised segmentation by using only motions, which means no manual annotations and no RGB information is required. To achieve this, we adopt an autoencoder framework that decomposes input optical flow into layers, implicitly learning a segmentation mask. The architecture involves an encoder, an iterative binding module, and a decoder. Our method achieves the state-of-the-art results in both Davis 2016 and Moving Camouflage Animals dataset on Mocha in comparison to self-supervised approaches, closing the gap with supervised methods. Lastly, we show the qualitative results. Note that RGB information is not required and is only shown for illustration. Thank you.
Hi, we participated in the robot challenge with a tracker named Mantos. It is based on 3 main steps. First, detection of all objects of interest as masks, followed by a short-term data association of segmentation masks in consecutive frames to form tracklets, and then a greedy long-term data association of tracklets using a space-time memory network. We took the 4th rank in the challenge. Let's focus on the long-term data association. Here, to compute an association score between 2 tracklets A and B, we use the space-time memory network to propagate some keyframe of tracklet into the past for B and the future for A to obtain heat maps. The score is then the average cosine similarity between the actual mask and the predicted heat maps. Finally, tracklets are merged in a greedy manner such that they don't temporarily overlap. Check out our paper for more details.
Hi, I'm Jong-won Yu, and this paper is about simple re-identification feature association for robust multi-object tracking and segmentation. One most challenging is instant segmentation and tracking for all COCO object categories. And a tracker should be robust and works well across all A benchmarks. The datasets and evaluation metrics are as follows. We adopt a strong REID baseline and train with predefined boundary boxes and segmentation masks. And tracking is performed based on the REID feature. Our proposed SIA achieves 3rd place in the most challenges. The qualitative results show that our method performs robustly well. Thank you for listening to my presentation.
Hello everyone, I'm here to introduce our solution to the RobMOTS challenge in this year's CVPR. We firstly prove the strength of our strategy on training anything appearance model, just like we firstly proposed in our solution last year's ECCV talk. And then we adopt a simple cascade association pipeline corresponding with these appearance models. And then we reformulate the post-association module as a MCPM problem in general graphs. And finally, we achieve the 2nd place in this competition with the provided detections. The core component of our solution is the appearance model. It's trained with collections of various SOT datasets And the cascade association method pipeline firstly use the embedding as a protocol and then use LU to improve the association recall. And finally, feature smoothing and post-association is applied to refine the results. We ranked second on both the validation and the test.
Hi, this is a spotlight video of RobTrack, which is the first place solution of Rob MOTS challenge in CVPR 2021. Here is an overview. We divide the tasks into detection and association and optimize both of them to improve the robustness of the whole tracking system. Specifically, given input frames, our detector predicts math for all the objects in the video, where we apply MI augmentation during training and PBMR refinement during inference to improve robustness. Then we divide the detected objects into common and general supercategories so that our EFC tracker can enable optimized association for both of them. Then we merge the two checklists and feed them into our offline relinking module to further fix the trajectories. Extensive experiments demonstrate the effectiveness of our major components and our superiority to other methods in robust tracking. Thank you.
Awesome. So that was the 11 spotlight, 1-minute spotlight presentations from the 7 accepted papers and from the paper submission track and the 4 accepted papers from the challenge track. So what we're going to do now is we're going to move to the poster session and the social. So before we go, I'm going to give you some instructions. So the poster session is in Gatherly. So you need to use the Gatherly link in the CVPR portal. So unfortunately, you have to be registered for CVPR to attend the poster session. You have to have that Gatherly link. But there's currently about 70 of you in the Zoom session, so you all must have access to that. So I hope to see you all there. So in the poster session, all of the 11 authors of those papers will be there, plus me, plus probably lots of other people. So it's going to be a chance to ask questions of the authors. It's going to be a chance to have a little bit of a social. It's scheduled for an hour. It can be on that long, but I recommend that people stay for at least the first half an hour. And then I think the schedule says that we're going to come back here to Zoom. And let me check, I think in 1.5 hours from now. Yes, so we'll come back to Zoom in 1.5 hours from now. So there'll be first 1 hour on Gatherly, and then a half an hour break for lunch or whatever time zone it is for you to have a half an hour break before we come back, and for me in particular. I'm not sure I said this already, but the poster sessions will be presented as kind of a screen share. So when you go to Gatherly, there will be kind of first instructions on how it works. If I describe it, it will probably be confusing to you if you don't know Gatherly, but basically there's an elevator and that will direct you towards the floor for this workshop. And there's a bunch of poster boards set up. So the presenters, they're not assigned to you any particular number. So just go to a number and then you'll see an option, I think there should be, to share your screen, and then you should share your poster on your screen. And then basically it's going to be a spatial alignment to move around and click to move your little character towards different people for chatting with them, talking about their work, having a general social and a general discussion about robust video understanding, tracking, and segmentation. So I'm going to put this up on here for the people on the YouTube link to see that we are currently in the poster session. And then I'm going to go and open Gatherly now and see you all there. So see you all on Gatherly.
you. Yes, thanks. I'm trying to find one, but oh, yes, I can find it. Yeah, yeah. Yes, yes, okay. Yeah, okay. I found it. It should go to, yes, is this visible? Okay, great. Thank you. Yes, thanks. I hear an echo for self. I'm trying, but oh, yes, I can find it. Yeah, yeah. Yes, yes, okay. Yeah, I found it now. Oh. Yes, is this visible? Okay, great. Thank you. Yes, thanks. I hear an echo for self. I'm trying, but oh, yes, I can find it. Yeah. Thank you. I'm very pleased. And yeah, thanks for organizing this. And hi, Jack. It's been a while since you left Oxford, I assume. For both of you, actually.
Sorry?
Yeah, it's been a while since. Like, when was the last time you came to Oxford?
Oh yeah, 2018, I think. Yeah. Are you a PhD student there?
Yeah, I just started this year, so really
Nice.
still getting used to it. But
Congrats.
yeah, thanks. Yeah. I see. So I think one thing that we kind of like wanted to do but didn't get quite to do it because the deadline's looming is the fact that we only use optical flow, and then we kind of like talk about how other methods fail because they only use RGB. And this is kind of like a inverse problem, right? Because like our methods fail in the cases where like RGB looks so easy, whereas like the object is just not moving enough to actually give us information on the flow. So that's kind of like what like it has been a low hanging fruit for like a long time. Yeah. 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 I see. So I think the talk would be pretty much around the same. So the idea was that he'll talk about more towards a higher level idea, and I'll talk a bit into detail in terms of like how exactly is the reconstruction works, like what or like the architecture itself, which I think Wady just glanced through, and he left it for me to actually talk about it, which will be a bit more interesting and a bit more intuition towards like how this is meant to work. As in, like it is quite obvious in terms of the layered representation of the model, but there's this other things that we haven't really talked about. So that will be kind of like the focus of the talk later.
Would you mind giving like a run through of the like an overview of the method? We have some feedback, do we?
Yeah. Oh, sorry. I should get my headphones. I would actually be back in like a few seconds. Hello, are you
Hi, Jonathan. I'm good. Can you maybe give me a quick introduction how I can share our poster? Ah, okay, yes, thank you. Mm-hmm. Exactly. Okay, I see. Okay. So you should see also, alright. Mm. Sorry, the microphone is bad. Sorry, Jonathan. Oh, it's really bad. I can't hear. It's very high latency.
Oh, Joe, glad to see you. Mhm. Right. Sorry? You mean share the screen? Okay, so this is the first time I use Gateway. I need to give some the. Yeah, I see, but I need to restart the page.
Hey, Jonathan, a quick question. How do you see the list of folks that are showing their posters in this floor? I just see a map that says 1, 2, 3, 4, 5, 6, etc. Ah, okay. Yeah. 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 I see. Yeah. Random. Yeah. Yeah. Makes sense. I don't have a poster. gladly listen in.
And then the presenter has to share it specifically.
Yeah. I think it's Jonathan.
Yeah,
we jumped to the same one. Yeah, I've yeah. Is Lorenzo here in one of these, or? Yeah. Ah, I see.
Okay, so I can give you a brief overview of what we've done. So what we've done is like actually kind of simple from a methodical point of view. So I'll just go through this figure here first. So this is a shot from video, YouTube VIS. So there's this person who's dancing and turning. So because the motion is large and like the detections tend to go missing, and this is a problem we've observed, especially when the objects tend to jitter or make sudden large movements. And I would imagine this is because of the low frame rate during video capture of the YouTube BIS. So because of this, we observe several such cases where the instance just goes missing. And so to that end, what we thought is, how do we fill these missing proposals, or even better, fill the segmentation mask directly? And if we get the mask directly, we can just generate a bounding box around it. So so that was the main idea of our work. So this is the network, what we do. So I'll talk to you about what happens during the inference time. During inference time, what we have is that we have a like a memory of storing the predictions of all the bounding box instances predicted until frame t, and now we're at frame t, and we use mask RCNN to generate the instances which it detects at the current frame t, and then now we go back to the memory and check whether some instances are present in the memory which we haven't detected at the current frame. So if that's the case, then what we do is we use this as a propagation mechanism to propagate those instances onto the current frame. So how we do that is first we compute the cross-frame affinity between. So yeah, another thing is like we store last 4 frames. We do this basically one by one from each of the last 24 frames until the current frame, and then the propagated mass is basically the mean of all those 24 propagated frames. So say we have picked a frame t minus delta from one of the 24 previous frames in the history. We use the ResNet 50 backbone to generate these FTN features, and then we compute the correlation, which is the interframe affinity between the two. And also we use the instance specific bounding box as a binary object map. So using this binary object map, which locates where the instance is, we propagate it using this interframe affinity. So now we get this coarse attention map. So this gives us a brief idea of where the object may be in the current frame. So then, like I guess Lorenzo also mentioned in maskprop, this serves as we apply this attention map to the backbone features, and this serves as an instance specific features, and kind of inspired from there. And this mask head is similar to mask RCNN. So applying this instance, using these instance specific features, we use the mask head to generate this higher quality segmentation mask. So the difference in quality is visible. Like initially, our plan was we could just use this use this propagated attention map as a mask itself, but you can see that the quality isn't the best. So we had to add another module on top of it. So what I'd like to essentially highlight is like this approach is kind of scalable in the sense that we can use any detector or any mechanism, but all we need is just a memory, and we can propagate any missing instance. So in that way, it's a very simple approach, but we're able to get like a 5-point improvement over mass track RCNN using just this one instance filling mechanism, as we call it. Yeah. Yeah, it does add a bit of overhead, especially because we're using like 24 previous frames. So we did try some experiments, but like the best performance we observed was with 24 previous frames, but like 6, 12, and 18 frames or something we tried, and it wasn't too bad, like maybe 1 MAP off or something. So like if you want to optimize that overhead performance trade-off, using less number of frames wouldn't be the worst idea. Yeah, sorry about that. So one, I would say, failure case, because we haven't been able to figure out why it doesn't work. Like it seems like sometimes mask RCNN generates a low quality segmentation mask. So we would imagine that using the temporal history and using some kind of mask blending, that would be like a good way to improve the quality and resolution of the masks. But whatever we do, that doesn't seem to work at all. So that's something like we want to figure out how to get that going, because it seems very intuitive. Why do you only want to propagate those instances which are missing? You can, in this way, you're kind of using the 3D information without using a 3D convolution. So that's I think something which can be adapted.
Hi again. Yes, I can hear you. It's laggy, but I think it will be okay. Maybe if I close my camera screen, it will be a bit better. Yes, you're right. The key point of this paper was the introduction of this approximate solver here. And we adapted the work with the optimal reality solver and before. Question, can you hear me now? Is it quite okay? So, question, mic still bad. Sorry, I really appreciate this, but I'll try to explain it a bit slower. Maybe, hopefully, you will get the main key points. And yes, okay. My colleague Andrea Hornakova, she reduced the complexity from exponentials to polynomial complexity for the solver. And she did this by a dual decomposition framework. So she split the whole problem into some subproblems, and then we applied message passing, and this leads to very fast and accurate results. Not still on this poster, but as you may notice, we have an iteratively also iteratively, and we get some quite accurate results after some iterations. And as we're going to the optimum, of course, the results getting better with respect to the tracking metrics. But in comparison to the optimal solver, which is shown in the reference 1 here on our poster, it was on some large sequences faster with what was it, times 100. So really a nice application for solving LLP in crowded sequences here. Exactly. Yeah, sorry for the sound. I can hear you as well. May yeah, hopefully we can discuss this later with better quality. Exactly.
Hello, I can. Can you hear me? I'm not sure I can because I'm not a presenter. I don't have an imposter. Yeah. In fact, I'm an industrial, so I belong to. I'm working for the system, which is a CAD company, and we are mainly focused on 3D geometric deep learning. So there is a bunch of nice talk and nice presentation on this subject. So yeah, really nice to be here at the CVPR. Yep. So it is quite unusual for me to experiment such as events such as CVPR virtually, but it's cool also. It's really nice. Okay. Thank you. Have a nice day.
Yeah, pero yo creo. Hello, Jonathan.
I'm trying to, but my screen is green.
So yeah, he's having technical difficulties.
Okay. No. Can you see something? Or
Green.
Green. But green like all green or?
Green like I don't know if I can share my screen to show to you. Let me take
I will take. Yes.
I don't know what's going on really. It's yeah. Okay.
I can. I am not, unfortunately. I only managed to, I fell off of the deadline for IEEE this year, but at least for a CVPR. Yeah, I definitely heard some interesting content from both, obviously, Philip was amazing and a lot of the other speakers, and just looking to try and get some follow-up on, models that seem to do well, but it wasn't clear to me how they would do it with domain adaptation, especially for some of the supervised models, and that I wanted to check in on some of those models for how they would do with, or if they've tried anything with the cloth changing data sets, which we saw a few presentations on that, which I was happy to see for re-ID. And I was curious to see pushing that towards actual, like some of the MOT data sets, where generally it's like monocameral, and typically you don't have things like that happening as far as I know. Maybe you know of a data set that I don't, where it's monocameral, like one of the MOT data sets essentially, except it has clothing changes occurring potentially over the course of the tracker. And I don't think I've seen that other than maybe a really teeny, lab data set from Berkeley or something. So yeah, I'm trying to bridge those two things, because I do see that as a gap in general. Yeah, we are actually working on that right now. And so I was trying to, I did see I have to look it up, but there was the one great paper that addressed this specifically. And they had a really nice masking technique, which helped to deal with pose estimation and dealing with just like a lot of the typical issues you have with like some of the simpler masks. I can find the author I'm thinking of, but anyhow, yeah, that was Hong, fine grained shape appearance, mutual learning. So that's a re-ID paper, but a lot of the principles I saw in, I thought could be translated over for sure. And so we're working on that right now. Yeah. So. Yeah, for sure. Because to be honest, I love multi-object tracking, and the motchallenge.net site is amazing. I definitely have made big use of it. When I talked with Laura, I know that there is no multi-cameral data set there. And I think that's a key problem that we're unfortunately not really fully addressing. I also know like the Duke MTMC dataset dropped off as no longer being valid for use. I know I've seen people who are still squeezing that in at this conference, but once that goes away and we have what, Market 1500, I'm just worried that we're not going to have any multi-camera MOT ground truth data sets or benchmark data sets we can be using for our work. And I do think it's a critical area. So we are working on it, but it's not a lift. Yeah, super cool. I really appreciate that. We will, yeah, like I said, motchallenge.net, I've definitely made use of some of the stuff you put on Git, the track eval and everything else. So we're looking at, yeah, I cloned it off, and now we're just looking at getting these data sets that I'm describing, and hopefully we can make them available. So that would be good fun. Yeah, so we're a small startup. We're on the East Coast. Re-ID is definitely, bread and butter for us, but we do a lot of various object detection, data fusion, and other methods to get towards being able to do re-ID. So, but for we are we have some government partnerships, and we have some potential commercial partnerships or customers as well. So this is year 3 of the company, and we're growing really well, which is nice, but trying to transition into having more customer applications. I know that we've got, just looking at sports is definitely an open area for this. And I know I cannot remember the names of the presenter from this past Sunday, but there was a MOT presenter, maybe from StatQuest or something, who was focused strictly on, tracking sports athletes, and then even adding a layer of sort of the equivalent of Moneyball, predicting, based on MOT and additional back-end metrics, what will these athletes do? What are they suited for, and so on. Yeah. So anyhow, that's the interest. But I was in government for quite a while, and I want to get back to academia, but figure try out a little bit of every area and see what happens. It's been hard. I look forward to when we go back to in-person conferences, and I actually hope that they keep, they could have just cameras in the backs of the rooms where the presentations are happening, and for like students that are, low budget, or for people that can't afford to go to the conference, it may not be a bad idea to give them something of like, insight into the actual conference. I wouldn't want to come back to this kind of format though, if we can avoid it. And no offense, obviously, I think what you did was great. It's just, it's trickier this way, for dynamic. A little old-fashioned whiteboarding, blackboarding would be very nice. Yeah. So, yeah. Appreciate that. Yeah, will do. Sounds good. Yeah, appreciate that, Jonathan.
Yeah, right. I'm trying. Yes, I'm finding which screen is the poster. Yeah, yeah, but as you can see, is it right? Yeah. Yeah. So can you see this screen? So can you see the poster? Okay, so wait a minute. And this time? Oh no. This time. All right. Okay. It's so hard. So I think the challenge is very good, but as you know, I've been taking the challenges for these 2 years. Last year's, for example, last year's CVPR, the first MOTS challenge and the ECCV power challenge. Both my team joined this challenge. But I find the time, especially the time, is not very suitable. So, for example, not only talk, but also this robot multi-US challenge. So the time is very limited. So I also noticed that there will be a new challenge. I forgot the name in this year's ECCV, right? So, but I say that the term is also. It seems that it's already delayed. Mhm. I know it's very hard. Yes, I know it's very hard. Okay, cool, cool. Mhm. Yes, yes, right. And I also want to know just a personal question. So will the hotel be default for the MOT benchmark, MOT challenge benchmark, right? Okay. I see. I see. Mhm. But you don't know the time, right? But you don't know the time, right? Mhm. Yeah, I like it very much. Yeah, I think very good. So, I think MOTA is not a good metric for the MOT domain because it's really more on detection. But for example, in this year's challenge, we didn't focus more on the detections. We just use the provided detections. So I think hotel can separate detection and association well compared with MOTA. Yeah. Mhm. Mhm. Yeah. Maybe they still need time for maybe for 2 or 3 conferences to there there must be more paper use hotel as the default metric to compare their methods. Mhm. Okay.
How's Laura? I thought. Sorry. No. I was just asking about Laura because I thought she would be here, but she's not. But anyway, it was just chit chat. I know. Yeah, I think so. Yeah, I mean, I kind of like I wrote my thesis like last year, and I saw Jota, and I like it quite much. I mean, I have to say because before we had this problem with MOTA and IDF1, which you didn't quite know how it like. For instance, MOTA, like this object association and all that stuff was a little bit I don't know, but yeah, I like it. Jota, I think it will be the standard. So, did you work on Jota? So good job. So yeah, I don't know why I had Aljosa there in Jota, but maybe That's how it works. That's how it works. No, it's okay. It's okay. Could you, I don't know if I will pronounce this right, Tang Jia Sheng.
Okay, right. You can just call me Tang.
Tang, could you do me a pitch, please? Because I arrived a little bit late. So if you could explain me a little bit how, like your poster.
Okay, yeah. So
Yes,
I think in a nutshell, our solution to this year's challenge is nothing new with compared with the solution to last year ECCV talk. So almost the core component is to train anything appearance model with the ReID model. You know, we collected almost 300,000 IDs from the SOT domain. We treat the checklist as a training pair to train this model to learn anything appearance. And besides the others category, we call the categories without person and car and others. So we also train the models on person and car with the specific subdomain data size. For example, I listed here the person ReID model is we use I didn't count, maybe 10 or 11 data sets to train the person ReID model, and for car ReID model we use a very well data set. So these are our appearance models, and then the call association pipeline is a cascade association. So the baseline directly use LU for matching, and we just use appearance for first with a relatively tight threshold. So with this threshold, we can achieve a better association accuracy. And then with LU, we can recall more objects. And there are additional two components. The first, in this cascade association pipeline, the feature should be smoothed by this formula. It's very important, as you can see.
Yeah, it's updating it, right, somehow. Yeah,
right. And also, we also come up with, we called it a PA module. In last year's CVPR, we already come up with this module, as well as in ECCV talk. Last year, we formulated it as a MCPM problem, but we directly use the greedy algorithm to match these subtractlists. So the short checklist, we use the mean ReID feature as to represent the short checklist, and then the cosine distance can be calculated among those checklists to form a long track. So
well, one question. So this smooth feature, so you're doing, okay, so you're having the track in time t equals the previous position, I guess, of the object. And okay.
Variant of copy paste is a work of CVPR. It's just a data augmentation technique, data augmentation method. It actually randomly select 2 images from the dataset and do some scale jittering or horizontal flipping, and just paste objects of one image to the other image, to create these training samples. They are unseen and diverse compared to the original COCO dataset, so you can kind of improve the generalization ability. Yeah.
Okay. So did you try any other augmentation techniques or something apart from this?
Actually, it's a bag of data. It's a bag of many data augmentations. You can see that it contains scale jittering and horizontal flipping. And actually, we also add the random crop and the random resize to into it. So it's a bag of many augmentations.
Okay. And what was the performance boost which you got by just adding this augmentation technique?
This technique is can improve the HOTA by a large margin. Actually, you can see that the first row is the performance without MIA, and with IMA we can directly improve HOTA by nearly 1.8% HOTA.
Yeah.
So it's so I said that HOTA emphasis on improving association, but detection is still a very important role to build a stronger tracker, I think. And so all of this space is a strong detector.
Yeah. So in your opinion, like what more like are you thinking of adding or something, like something which would have worked in theory?
I didn't hear it. I'm not good at listening. Can you say that again?
So what are you looking at, like as your future work or something, like which is a failure case which you want to improve upon?
Well, do you mean our future work? How will we're not planning to continue on this work.
Okay.
Maybe maybe we'll move to another. Yeah.
Okay, sure, got it.
Yeah.
Thanks.
So, okay, thanks. Yeah, you can call me like that. It's okay. It's okay. You mean how can I achieve such good performance? Well. Oh well, I think I still insist on the opinion that a better detector is required, because I observed that on OVIS dataset and TAO dataset, the original detections you provide is a little bad, not that good actually. And so I think in the next year you can provide computers with more accurate detections to make them focus more on association, I think. And then I think for the association, I think it's better to build a tracker that no matter for which category you can let me think how to say that. You should balance the you should address the imbalance of training samples for different categories to achieve the robustness in open world tracking, because in COCO and the RobMods data sets, there exists an imbalance between different categories. So I think it's very important to address this imbalance, I think. In our method, we just use 2 expert trackers for different super categories, and it achieves direct performance improvement. So I think it's very important to address the imbalance. Yeah. And sorry for my poor speaking. Yeah.
No.
Okay. Thank you. Yeah. 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 Maybe. Yeah. The long tail problem is very. Yeah. You're right. Yeah. So how to address the long tail problem is a very promising future direction. Yeah, for people to address. Yeah. And like. Yeah. You say. You go. You go first. Yeah. 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 So the last year ECCV challenge on tau, the first place solution uses a strong detector, and they achieved much better performance than the baseline. Yeah. So the point is that they use many techniques to address long tail detection on LVIS dataset. Yeah, I think. Yeah. 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 Actually, I think it's very interesting that the point that you point out on the challenge homepage, you said you can create more synthesized images, like using GANs or any other image synthesis techniques to create more samples on tail classes. Yeah, I think it's very promising, but but in this challenge, in this year challenge, nobody used that. Maybe it's a little more time consuming, and maybe it's hard for the track community to start to study on image synthesis techniques. Yeah, but I think it's very promising because 1 year before I was focused. My main research interest is about image synthesis, and so I think it's very promising to combine these two communities to create to make more progress. Yeah. I do that. I do copy paste augmentation just on Cocoa actually. Yeah. Yeah, on just on Cocoa, just to build the detector. Yeah. Yeah. And maybe you can use more. Yeah, you go. Yes, I think it's very promising to use self-supervised techniques like Wei Xie, Dr. Xie of Oxford. Like he said, we can use more self-supervised techniques to uh, to avoid the to avoid us from relying on the more annotated data. We can use unannotated data to train stronger models for association. Yeah, maybe. Yeah. Yeah. Actually, I just find that the challenge has been delayed many times. I think maybe next year you should plan earlier, yeah, to prepare the data sets. Yeah, I wonder why you delay the challenge. What's the reason? I'm a little curious. Uh, yeah, okay, I got it. Okay, I got it. I got it. Okay, I got it. Yeah. Yeah. I think many new papers will evaluate the method on this combined robust benchmark, because I think existing single benchmark are too focused on one specific category, but robust benchmark contains a very large scale categories to to evaluate to enable evaluation more well, closer to real world scenarios, yeah, to real world tracking. I think it's good. Maybe in the next year, more papers will be evaluated on this benchmark. I think it's very hopeful. Yeah, maybe that next year challenge will attract more people to participate. Yeah. Yeah, yeah. Yeah. I really appreciate that. I really appreciate this benchmark. It's very hopeful. Yeah. Yeah. Okay. Okay. Yeah. Okay.
Hi. Sorry about earlier. My parents turned off my Wi-Fi at home. Yeah, I'm staying with my. Yeah. Yeah. This was part of my internship. This part of my internship at Harvard. So I just finished my undergrad, and so during my undergrad I had to do a thesis. So this was my thesis. So now we're looking at a transformer-based propagation approach. So that's something which is currently ongoing. So we're getting decent results. So I'm not sure if you've heard of the CVPR 2021 paper called WISP-TR. I'm not sure if that's how you pronounce it, but like it's a end-to-end video segmentation using transformer networks. So the one problem we found in that is like they load the entire video sequence of 36 frames at once and do one straight 3D convolution. So that's something we can't get to fit in our memory at all. So that's something that won't work for us. So we're looking at something similar, like can we propagate or do something which is not exactly 3D, but like kind of corresponds to using 3D information, I guess. Yeah. So I'm going to work over the summer, and then I'm going to Pittsburgh for my master's around August or something, like at the end of August. So I'll be working till then. For master's, I'm going for my master's. Yeah. Oh, yeah. Where are you going? Like, are you going for a postdoc? Oh, cool. So, Mine is like this MSCV program. It's a new program, so it's like a professional master's kind of. So it's more course oriented towards computer vision. So there's no advisor attached as such. It's just like a lot of computer vision courses. Who do you plan to work with? Oh, cool. I'd like to join his. He does really cool work. Yeah. I also like wanted to say I'm a huge fan of your work. So I saw the HOTA paper earlier, and I've been generally just following your work. I had written to you earlier the year as well about TM. So I had written to you like a while back about TMOTS data set as well. Like that was probably 6-7 months back. So I've been following your work for a long time now. It was really cool to meet you. Yeah. Yeah, sure. Hmm. Yeah. So it's like jam packed, like session after session after session. Yeah, that's true. So what do you plan to work on in your next year at CMU? Hmm. Hmm. Are you looking at recently released that paper on streaming perception? So is that something you're going to work on, like maybe for videos? Yeah. Okay. So what do you think about the field in general, like the MOTS and BIS? Where's this heading in terms of maybe benchmarks or like in terms? Yeah, can you hear me now? So should I turn off my video? Maybe that's using up the bandwidth. Yeah. I was saying, what do you think where the field is headed, like tracking, segmentation, all these tasks which we have in the workshop? Where do you think this field is headed in terms of, say, approaches and like even as terms of benchmarks or something? Hmm. Yeah. Hmm. Hmm. Yeah.
结束了吗？你睡呗，你先。你帮我把这个毛巾。
Oh shit.
Mhm. Yeah. The one concern with 3D convolutions and stuff I had is like it's too expensive, right? Like maybe there's some alternative or something. Yeah. Mhm. Yeah. Yeah. I agree. Yeah. Cool. Yeah, sure. I have to get my dinner as well, and then I'll join the Zoom call. But it was it was really nice to meet you. Like I couldn't imagine. That's really cool. Yeah, definitely. I'll get in touch maybe when I reach there. We can just meet over coffee or something. And also, like this workshop was really good, and thank you for organizing. Like this we submitted it because it was hosted by a lab and also Laura's lab, so it was really here in addition to our ICCV submission. So that I really appreciated. Yeah, yeah, and yeah, yeah. See you. You can have a breather now, and we can join the Zoom link later. Yeah, cool. Yeah, yeah, definitely. I like this as well. Nice meeting you. Yeah.
Can you wait for a minute? I have a question. Uh, it's late night here in China. Do I have to wait until the award? Do I have to attend to Zoom in Flash to? Okay, okay. So I can just go to sleep. Oh, okay, okay, okay. Thank you, thank you. Okay, 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 okay. So goodbye, goodbye. Best wishes.
Bye. Nice to meet you guys.
Bye, 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 bye.
Bye. See you, Jonathan.
Okay, hello everyone. We're going to start up again in about 1 minute. So just letting you all know that we're just prepping to start for the second session. So in the interest of being punctual, I am going to begin. My clock says 6 o'clock on the dot. I assume that you can all hear me. Yes, I'm unmuted. Good. Perfect. So I'm going to just very quickly go through some of the slides, just introducing the workshop again, because I'm aware that we have a bunch of different time zones. And so a lot of people might be joining us now that weren't here in the morning. So I'm just going to talk about it very quickly, probably about 5 minutes, and then I'll introduce our first keynote invited speaker for this session. So welcome to all of those that were here before and all of those that are new here to the Robust Video Scene Understanding CVPR workshop. It's great to have you all here. So like I said this morning, the topics are in general of this workshop are in general robust understanding of video in general and scenes in general, but with a specific focus on tracking and video segmentation. In general, computer vision has got good at understanding images, but video has a long way to go. So with this workshop, we really wanted to focus on video and how we can address the problems that are inherent in video. So I listed a few such problems, such as video data is really huge. It's really difficult to label it all. Motion is difficult to deal with. Making predictions consistent across frames is really difficult, and many more problems with video that don't occur in static images. So that's one of the reasons we want to focus on this in this workshop. And another reason is that video has immense opportunity: robotics, self-driving, AR, VR, video editing, content creation, optimization for industrial applications or monitoring for industrial applications. There's a lot of opportunity for dealing with video. So why a specific focus on tracking and video segmentation? Well, tracking and video segmentation is the dense understanding of objects in video, and objects are one of the most interesting things because they move, they cause interesting things to happen. And so densely understanding where they are, how they're moving, what they are is this task of tracking and video segmentation, and that's super interesting. We can deal with these difficulties in video like motion, consistency across frames. And if we can create good solutions for tracking and video segmentation, it will open up wide opportunities for other types of video understanding. And like I said before, there are many applications that are just waiting to change the world. So big focus on robust. So we put robust in bold because many current methods are very handcrafted, very overfit, very specific to the domain they're working on and designed for. So we really want to make sure that methods are robust across different domains, across different problems, because that's going to make them work well in the real world and going to cause meaningful progress. So that's one of the focuses of this workshop, this term robust. So this field is exploding. There's more and more interest. There's more and more investment. You can see there was Kitty in 2012 and Mott Challenge in 2015, and slowly there's been more and more data sets and benchmarks focused on this. Davis in 2016, YouTube VOS 18, Mott's 19, and in 2020, all of a sudden there's Waymo, BDD, and Tau. Now in 2021, we already have OVIS, Open World Tracking Benchmark, unidentified video objects, segmenting and tracking every pixel. And that's just kind of the multi-object tracking kind of flavor. So there's also much more on data sets where the first frame is given for 3D tracking, 3D bounding boxes like new scenes and Argoverse. this field is exploding and there's so much work going on. So that's fantastic. It's awesome that there's so much interest and so much investment and so much research, but it does come with the downside. So having so many different benchmarks really fragments the community, really splits it up, and that shouldn't be the case. The video solutions, solutions that understand video, that do tracking and segmentation, if they work on like BDD, they should also work on YouTube this. You know, video is video and understanding it is understanding it. But having different benchmarks, this isn't the case. Methods are overfitting to the specific benchmark that they're trained on. So that's why we started this workshop and started this challenge that was presented at this workshop to bring together the fragmented community, video understanding and tracking, video segmentation community together into one place here today on this workshop, online on Zoom. Thank you all for coming, and work towards solving these problems together. So yeah, and then with this challenge specifically that I'm about to talk about, we wanted to create robust algorithms that work across all of the different domains and work well in the real world. So that's why I reached out to the organizers of these 8 different benchmarks and said, okay, there's 8 different benchmarks kind of evaluating the same thing. Let's all come together and create a benchmark and this workshop and come together and try and push robust progress together as a community. And so we did that, and that's what this workshop is here today. Specifically on this challenge, so we had the results of the challenge presented this morning. We had the top 3 methods given oral. We had 12 submissions to the val set, 10 to the test set, 6 speed out baseline, and 4 accepted to submit a paper. And we used the novel HOTA metrics for evaluating progress, which I've just had a lot of feedback on in the poster session, that people said that was really good, and that really does enable better analysis of how well trackers are performing by separating out different components of tracking. So that's some good progress already in measuring progress in this field. So again, we had the talks this morning, but congratulations to all of those that did well in the challenge, the scores, and they already presented their orals this morning. So we also accepted some papers. They presented in a spotlight session earlier this morning as well as a poster session. But we'll have 2 more orals this afternoon session for a best paper and one of the best paper runner-ups. So we awarded a best paper award to Charag Yang et al. From the University of Oxford for self-supervised video object segmentation by motion grouping, and 2 best paper runner-ups. So Andre Gabau for multiple object tracking using mixed density networks for trajectory estimation, and Julian True for motion vector extrapolation for video object detection. So one of those gave an oral this morning, and 2 of them will give an oral this evening. We had 4 further accepted papers. So now the most exciting part of the workshop for a lot of people, I think, are the invited talks. So we already had the 4 on the left in the morning session, so now we have the 4 on the right. So I'm really excited for these talks. So first up, when I stop talking in about 1 or 2 minutes, Judy Hoffman is going to give a talk about lessons from domain adaptation for robust video understanding. And a little while after that, Chris Katani and his student will talk about future prediction. Sanya Fidler will talk a little bit later about simulation for understanding scenes. And Katrina Frakiadaki will talk about understanding 3D scenes and how tracking can emerge self-supervised from 3D representations. So a really exciting lineup of talks. I chose all of the talkers based on going through 8 different topics that I thought that our audience would be interested in hearing about, and thinking of who was the person in the world that could give the most interesting talk about that topic. And then I approached all the speakers and said, hey, our audience would really like to hear about this topic. Would you like to give a talk? And everyone I approached said yes. So I'm really thankful to all of our speakers for giving talks here today. And we're really excited to hear the rest of the 4 talks that are still coming. So here's the full schedule. Please view it on the website. We've had basically the whole left plus the top 2. We've had the post session, and now I'm giving a little spiel. And in 1 minute, Judy will start talking. So last 2 slides. Thank you also to all of my co-organizers. There's a lot of you involved in all of the different benchmarks that put together this challenge. So thank you all for everything. And a huge thanks to all of the sponsors, without which this workshop would have been much more difficult. So I'm going to stop sharing my screen. And so I see that Judy has turned on her camera. So it's my great honor to introduce our first keynote invited speaker for the second session, for the second half of this robust video segmentation workshop today, which is Judy Hoffman, professor at Georgia Tech. And she's going to be talking about lessons from domain adaptation for robust video understanding. So without further ado, take it away, Judy. We're excited to hear your talk.
Great, thank you. And thanks for inviting me to come to this workshop. So this talk is going to be a little bit different than probably the majority of the talks that you're going to hear today, because we're going to be focusing mostly on this topic of robustness and how it might impact what you're doing in terms of your understanding in dynamic scenes and video more broadly. So to get started, we can just think about some of the classic large-scale benchmark challenges that we've seen in the visual recognition community. ImageNet is probably the most canonical example here, and not only did performance increase in ImageNet over time through to different advancements in terms of compute and architecture design, but because of this, a lot of people just start off their recognition pipelines by taking one of these large-scale ResNet models that have already been trained on ImageNet and then just repurposing it, using it as a starting initialization point for training for some new task, in particular something like video. So this is really, really standard. A lot of us do this. And if we think about what kind of assumptions we're making here, of course, when you take a model that was performing really well on ImageNet, you kind of start to think that this model is just general purpose and reusable in some ways. But ImageNet, of course, has recognition capabilities on 1,000 different categories, including things like recognizing many different species of dogs. And if we wanted to think about what's the differences between the data that we saw in ImageNet and that we use for those initial weight representations of our model, and how reusable is that across different circumstances, it might be natural to just ask, well, how well does this model work out of the box on perhaps a similar set of images, in the sense that it comprises the same categories that we saw in ImageNet, but maybe collected or curated in a different medium. So instead of still images that people wanted to share with one another, maybe it was dynamic scenes that people wanted to share. So this is a video that I took from YouTube, and I just took a ResNet model and tried to see on the still frames of this video, how well did that ResNet model work out of the box to recognize the dog. And it turned out that the dog wasn't recognized at all in any of the frames that I showed you here. So it's natural to then ask, why would this happen? Why would it fail on what seems to be such a similar domain to ImageNet? It's still kind of nice. Mostly the subject is in the center of the frame, and but for some reason it's not being recognized. And to understand that, we have to delve deeper into the data that was used to train that initial model. So the data that was used to train ImageNet was scraped from static sharing sites like Flickr. Here are some example images from the ImageNet dataset for this category of dog. And what you'll notice is that because people chose to curate the images they decided to share with one another, there's an inherent bias to the types of images that are shared. So in particular, most images of dog are going to have the face visible. Most of the time, they're going to make sure that the subject, in this case, the dog, is in the center of the frame. You're going to have nice resolution, nice lighting, probably a limited amount of blurring artifacts, because if you did take a photo and it was blurry, you'd probably take a second photo and choose to upload that one to Flickr and not that first one. But when you think about somebody uploading a video of their dog running or doing something fun to YouTube, you don't have that same level of control where you can curate every individual frame. And so now when you start thinking about recognizing each frame, you realize that you have to deal with the fact that, well, there's so much data in a video, so many frames, that probably people are not uploading the same resolution as they were in the still images. You're going to have to deal with motion blur, just because in this case, things are happening in the world on the fly, and a wider variety of poses than you saw in that still image database. Nobody's going to take any of these still images and upload them to a site like Flickr to share with their friends and family because they're not individually interesting. It's really just the video altogether that's interesting. And so it's important to think about these kind of key differences. And when we make the choice to take a model that was trained in one circumstance as use it in order to leverage and learn faster in a new domain, that can work well. And of course, there've been lots of examples where that's working very well. But it's important to remember the underlying biases that are included in that original model. And so we don't overrepresent what we think that model will do in practice. And one way in which we can further leverage a model even across these different imaging domains. So different imaging domains could be between still images and video, or it could be between other situations like simulation to real world. But in either case, if you have access to an initial model or lots of data from some sort of highly labeled large imaging domain, it would be natural to want to reuse that for some other circumstance where you don't have access to as many labeled examples. And you should. But the key is not to just use it out of the box, but instead to consider how best to transfer the knowledge from that original domain to a new setting. And really just accepting the fact that there are differences and instead trying to add additional learning objectives to make sure that you can overcome those differences. And one classic paradigm that's been used in domain adaptation is called domain adversarial learning. And in this setting, what you do is you say, okay, I have an initial model that was trained on my large labeled source data set. And because it's labeled well, I can use it to train a strong task prediction model. And then, of course, the issue that we're trying to overcome is the fact that you now have a new setting that has limited or no labels. And we call this the target setting. And because it has limited or no labels, you need to introduce an auxiliary learning objective that doesn't require labels in order to really transfer the information from that large source model to this target situation. And in domain adversarial learning, the way that this works is you start by training a domain classifier to tell the difference between the source and target domains. Intuitively, if you can tell the difference between the source and target, it means that the distributions, at least in this learned representation space, are far apart. And so then we update the underlying representation so as to confuse this domain classifier. If you've worked with GANs or any other type of adversarial learning, it's very, very similar. The difference here is that we're not trying to align a real and a fake distribution. We're instead trying to align two real distributions, but one of them is well labeled and one of them is not. And so we're creating a feature representation that renders the two domains indistinguishable. This imposes an alignment objective and doesn't require labels in this target domain. And so, of course, in many different scenarios, you're going to be in a situation where it's hard to acquire labels. In video, maybe you only have labels for a few keyframes rather than all of your frames. If the task is particularly expensive, like this task of semantic segmentation, then of course you're going to be limited because each individual frame is highly expensive. And you're in the situation where a lot of your frames and a lot of what you're going to be looking at over time can really vary. So even if you have lots and lots of data, you probably are still not capturing the entire world that you're going to see at test time. In the case of self-driving application, this can be due to changes in weather, changes in the city that you're operating in, time of year, and just what car is being used to capture or what sensors are being used to capture. And of course, there's all kinds of dynamics that change throughout the scene at any given point in time. And so clearly there's an issue where you have the need for a diverse set of labeled data in order to solve this problem. And perhaps that's too expensive or even intractable to really collect that data and to annotate it all to train an entirely supervised learning. And so what people try to do is they try to work a lot in developing simulators. And the idea, or the key goal here, of course, is to be able to generate the scenes of interest and all of the different diversity that might be experienced in the real world for a particular application. But the problem arises that the images that you render are not going to match exactly the images that you see in the real world. So while this can be used to augment and generate lots and lots of extra label data, there's still a gap in terms of the models that are trained in a simulated environment and the models that need to be deployed to work well in the real world. So here's one example that people look at, which is training on images that are taken from the Grand Theft Auto game. This is a synthetic rendered data set, but it's reasonably realistic looking. So it's not like you're going from box-like shapes to the real world. There's some texture, there's some of the details that you would see in the real world. And then on the right-hand side, we have an example image from the Cityscapes driving data set. And of course, you all know that the Cityscapes data set, even if you did use all of the annotations that are available, there's a lot more video data that's available that is not fully annotated. It's just going to be a few key frames that are annotated here. But in this example, we're going to imagine that we're just transferring from synthetic data to real world without any annotations in the real world. So basically, how can you take this model that was trained in simulation and deploy it in the real world as fast as possible? If you have labels, you can probably improve further, but we want to know how well we can work out of the box. So to do that, the first thing we're going to do is apply this domain adversarial learning, but applied to the imaging distributions. And what that means is it's essentially akin to doing a image-to-image translation task, where we'd like to be able to take our images from the synthetic domain and render them to look more like images from the real domain. So this is an image again from the Grand Theft Auto game. And once we apply this domain adversarial learning on the pixel space, we're able to produce an output that looks more like an image from the Cityscapes driving dataset. And you can do this across many frames and images, and this work is actually on the older side now, in the sense that there have been, even at this conference, a lot of really amazing image-to-image translation techniques that leverage temporal information to improve the stability of these renderings. And so I'm sure that that would improve this even further. But even with this work that was based off of CycleGAN from 2018, what we could do is we're able to improve the predictive performance on the real world by first doing image space adaptation and then doing feature space alignment, both using an domain adversarial learning objective, but applying it at these two different representation levels simultaneously. And once we do this, we're able to take an image that before adaptation was not able to recognize, let's say, this pedestrian in the foreground, and we're able to help recover observation of the street sign in the background, as well as improvements on the road itself. So this is an example of being able to leverage a simulator, in this case, to help us to augment our training set, our labeled data set, to train a model and improve it through adaptation for deployment in these real imaging conditions. This is clearly not a perfect output on the after adaptation, but this is what you can achieve without using any labels in the real images. If you then include real labels, you can improve further. Another task where you might want to use adaptation is one where, again, the standard protocol, let's say you're trying to do action recognition in these small videos. I believe these are example videos from the UCF dataset. A really standard thing that people do is they start with using an ImageNet pre-trained model and then fine-tune using whatever auxiliary learning objectives are developed in a particular algorithm, whatever architectural details. But you're still leveraging an initial source model from object recognition in the still image data set. And as I mentioned before, this this is really ignoring the fact that there are some huge variances between the imaging statistics of the still image database and the action recognition database. So what we did in this work was we thought about, well, especially in the scenario where we don't have a lot of labeled data in the video, or we don't have a lot of videos that are labeled overall, we'd like to be able to leverage this extra source of labeled data from the still images and reuse it for our downstream task, in this case, action recognition. And one thing that we can do, instead of just taking the source model out of the box and using it in kind of this weak form of transfer through fine tuning, is we can explicitly apply a domain adversarial learning objective on top of this source model. And in that way, we're still continuing to refine our initial model. Rather than just taking the model that worked best for ImageNet, we can instead adapt it to extract information that's more likely to be reusable in the video domain. And together with this, what we included, because this was a semi-supervised learning problem, was the ability to use a entropy minimization loss, which is a really classic semi-supervised learning technique. I won't go into the details of this particular work of how we set that up, but it's a self-training style of approach to be able to leverage the unlabeled data together with the labeled data in this domain, this action recognition domain, so that you're effectively using all pieces of information, the source labeled data with refinement through adaptation, and the unlabeled video data with self-training by leveraging the weak, maybe slightly overfitted model that was trained on the labeled data. And in doing this, we could improve our few-shot recognition performance on this particular task. Now, the actual numbers there are not so important, but the important thing to consider is the fact that we were leveraging a self-training loss in that particular work. And this is something that's done over and over again, especially, I suspect, in the video setting where you have a few keyframes that are labeled or a few videos that are labeled. Then you're going to be able to train a model to solve different recognition tasks. And you'd love to be able to leverage the remaining sources of data that don't necessarily have supervision provided. But I want to point out one thing that has to do with that really arises in self-training, and especially in self-training when you're considering a domain gap. So in standard self-training, what you would do is you would imagine you had some amount of labeled data. When you're talking about using self-supervised learning together with a domain gap, meaning that the labeled data comes from a different imaging distribution than the unlabeled data, you'll start by training a model on the labeled data. And this will, again, work well because this is a supervised learning problem, and we know how to solve that. The problem then arises when our unlabeled data is maybe drawn from a slightly different distribution. This could be because they're from different videos, captured at different times, any number of reasons why it might be a different imaging distribution. But because of that, the images on the videos frames that we'll see from this unlabeled domain may be misaligned to that original source recognition model. And now if we consider applying learning objectives like self-training, what we'll find is that we'll end up reinforcing errors that are present in that initial model. So a self-training objective might do something like, say, according to the model as is, well, how well does my model perform on my different unlabeled images or frames, and what labels does it currently predict? Let's make sure that the model becomes more confident with those predictions. That could be done either with a pseudo label loss or an entropy minimization loss, both of which are very standard. But if you're using those and the model is incorrect to begin with, you're just going to keep training the model to become more and more confident in its incorrect predictions. So that's not really what we want to do, because it will just have the end effect of really just clustering things further according to those mispredictions. So one thing that we thought about recently in this work called Sentry was, is there a way in which we can detect reliable unlabeled instances and only include those in a self-training objective? And so in this way, we'd like to minimize the dangers of self-training and reduce the chance that we're going to be accumulating errors over time. And so the way that this particular work was introduced was that we had this kind of key idea that we would use predictive consistency, which has been used across a number of different avenues before, but use it in this case on our unlabeled data in a semi-supervised learning context to identify instances that we deem reliable under the current model. And so once we've identified those instances, we can then apply a self-training objective only on those. And some prior works have looked at identifying these instances using just model confidence, but unfortunately, especially in a domain adaptive setting, the instances, their model confidence is known to be miscalibrated, and so it's not always a trustworthy objective. So instead, we're going to use this predictive consistency that I'll explain in a second in order to identify these reliable instances. And then we're going to only impose a self-training objective on those instances, which is going to look like increasing the model's confidence only on these consistent instances. And we're actually going to also reduce the confidence on the inconsistent instances. So that should hopefully provide us an alignment that is more true to the underlying task labels. So overall, the model looks something like this. We start by having a large labeled data set, and we're going to train a model on that large labeled data set. We then have new images or new frames that come from a different imaging distribution. Here, it's kind of depicted as this sketch to real world images, but it could be simulation to real world, and it could be looking at just taken from different cities or different video captures. In whatever is the case, you have labels in the red source domain and you don't have labels in this blue target domain. But we can, of course, apply our model to the unlabeled data and we can produce an output, and maybe it'll be correct, like in this example, producing bear. But what we'd like to do is we'd like to be able to identify or give ourselves some sort of information as to whether or not we deem that this actual model is incorrect. And the way that we're going to do that is we're going to produce random label preserving augmentations, which are going to be able to be used to extract auxiliary output predictions. And through looking at all of these ensemble of output predictions, we're going to estimate whether or not we deem this sample to be reliable. And we do that quite simply. We have a consistency checker, and you could use any number of different voting strategy, majority, unanimous. We've tried a number of different things in the paper. And if it's deemed to be consistent, well, then you can just operate as normal. You can use a self-training objective like minimizing the entropy, optimizing to increase the confidence on this particular sample, because you have some sort of sense that this might be a reliable sample. But if it's inconsistent, we don't want to minimize the entropy here. We don't want to increase the model confidence. In fact, we're going to try to maximize the entropy, or in other words, decrease model confidence. So we're going to say that we don't necessarily know what this sample is, and so we're going to operate with a uniform prior. So once we do this, I'm going to show you just a couple example results today. And these, again, are not on videos, unfortunately, but they're on some standard domain adaptation data sets. One data set is called the mini domain net data set. It has a number of different imaging domains as well as 40 categories. And if you look at any domain to another, the label distribution, the number of samples from one domain to the other are not necessarily aligned. So it's not a perfectly balanced training problem. And in the paper, we go into a lot of depth actually on how to handle the situation where you have a label imbalance problem. So overall, if you average results across all the different 12 source to target shifts in this data set and the 40 categories, a model that doesn't do any adaptation could achieve about 66% performance on this task, just for reference. And if we wanted to look at baseline approaches that do just simple distribution matching, they can achieve as high as 74. A label shift approach, an approach that just tries to model the actual label distribution shift from source to target, completely fails here. Those approaches that both model the fact that the data is shifting and the label distribution is shifting. So this is something that is oftentimes ignored in domain adaptation, the fact that this label distribution can change from source to target, but really appears frequently in practice. These approaches do a bit better, including one that's a relaxed domain matching based approach, or distribution matching rather, an approach that uses self-training but relies on confidence based off of the pseudo label themselves, and an approach that uses many different recent objectives, including entropy minimization, contrastive loss, and a mix-up loss. And then we have this work, which is a pretty simple work in the sense that all it's really doing is using a very standard self-training objective. In fact, there are more sophisticated self-training objectives than minimizing the entropy. But the key difference here is that we don't indiscriminately minimize entropy. We actually have an attempt to discover or predict which instances are deemed to be reliable before we apply self-training objectives. And that ends up being very helpful in avoiding divergence. The training with this approach is a lot more stable than competing methods that we tried, and also outperform them across a number of different benchmark scenarios. So overall, this workshop is really focusing, of course, on video recognition, robust video recognition and tracking. And my takeaway message is just to say that this problem of domain adaptation arises all the time in video recognition, not least of which was me pointing out the fact that if you're leveraging any kind of pre-trained model, you are actually dealing with this situation of shifting domains from still image to video, but also just within your video, you very frequently are going to be dealing with the fact that you have labels in one video and not in another, and there's some differences between those. If you're doing any kind of self-training, because you only have keyframes labeled, you need to make sure that you're not going to be overfitting to the current correct predictions and just reinforcing the errors that already exist in the model. And one last tidbit is that something I haven't worked on, but I think would be really interesting, is in terms of trying to predict which instances are consistent. If you have access to video, there's of course tons of temporal information that could be leveraged to really improve. So instead of only generating random augmentations, there's different ways that you could leverage these frame-to-frame consistencies to judge whether or not you deem an instance to be predicted reliably. And I think that should be very effective. So with that, I want to thank my group who has all participated in this work, and many of which have really led the work, including Viraj, who was the lead on the Sentry paper. And I believe we have a few minutes for questions if anybody has any. Thank you.
Awesome. Thank you very much for the talk. That was fascinating. Kind of touched on also some of the stuff we were just talking about in the poster session beforehand. So I think this work is going to be very relevant going forward for making methods better. So for the audience, if you have any questions, my recommendation would be to raise your hand and turn your camera on, and it will look really obvious that you want to talk. But until somebody does that, or if they're too nervous, feel free to write the question in the chat, either here or on YouTube, and I'll ask it. But until then, I have lots of questions. So I could ask questions all day, but let's start with one. So your method relies on predicting the consistency of the prediction, and then for those that are inconsistent, it maximizes the entropy and tries to make that a uniform loss. Have you investigated how sensitive it is to say false positives in that? If it's really should be consistent, it's correct, but you get that wrong, how much does that hurt, or is that kind of irrelevant and it's fine? Have you investigated that? That would be very interesting.
Yeah, well, what we've done is we've investigated the precision of these they're essentially classification objectives, finding consistent or inconsistent. And we found that in terms of consistency, it has a precision around 80% all throughout training, actually. It doesn't really go down throughout training, but the precision of predicting that something is inconsistent, basically implying that it's incorrect, that one starts a little lower at about 60. So actually we're having more of the issue where we miss some samples that were actually labeled correct, but we deem them to be inconsistent, and so we are not leveraging that labeled data. Fortunately, that increases over time and plateaus about at that 80% as well. And so as you're learning, you start incorporating more samples that you missed in that first those first few epochs of training. And so it actually kind of creates a little bit of an implicit curriculum. It's not designed that way, but that's the way it ends up working out.
So your question was really, your wording was really interesting there, because you said that it kind of ignores that data. So the question is, when it doesn't include those examples that it should for training, is that implying that it's ignoring that data effectively as an ignore and no harm, or is actually putting that maximum entropy on that harmful to the model? Like, would it be better to not maximize the entropy for those that are wrong? Wrongly.
We looked at that. We tried many different variants. There's quite a large appendix if you're interested, but we found that maximizing the entropy was overall more helpful than doing nothing. But what I would say, that something that we haven't looked into and I suspect would be true, is that there's probably some instances for which doing nothing is better. I think that we only explored one of the two choices. So either doing, you basically minimized or maximized. And I think that there would be space to have something in between, where there are some instances, if you're just very unsure whether they're consistent or inconsistent, then you could just do nothing. But overall, even incorporating that data with entropy maximization objective allows you to see that data incorporated into learning pieces of the model that don't necessarily relate to the auxiliary objective, things like batch norm parameters and stuff like that. And I suspect that at least including it in that part of the learning is necessary, just to make sure that you're not ignoring parts of the data overall.
So have you tried the extreme where you maximize the entropy for all data points and see if it harms or hurts the learning? For all of the
I mean, that would definitely hurt the learning, because you wouldn't be able to learn anything in that case. This method is not learning on like on the target examples. You need to be able to be predicting something at the end of the day. So if you only optimize according to this entropy maximization objective, you're basically going to be destroying information. You're just optimizing with a uniform prior, so you're not learning to predict anything in that case.
Okay, awesome. So in the interest of time, we're going to move on, but you're going to be here for the panel session later, right?
Right.
Awesome. So if anybody else has any questions, hold on to them. And thank you again for the fantastic talk, Judy. It was extremely interesting. I think this is an extremely important topic for us to know about and to look into and to put into this work. Like you said, all our models are adapted from ImageNet usually, so it's important to think about that. So let's move on to the next part of the schedule. So next we have an oral talk, so 10-minute oral talk from Julian True from Ryerson University. And this is there was 2 best paper runner-ups, and this is the oral talk for one of the best paper runner-ups. So second best paper for the submitted paper track of the workshop. And he's going to give a talk on motion vector extrapolation for video object detection. So this will be a 10-minute oral talk. So when you're ready, Julian, feel free to share your screen and begin. Hope that's all working for you.
Absolutely. Thank you for the introduction. So just let me know, is that coming through okay?
Yep, can see that perfectly.
Awesome, thanks. All right, so hi everyone. I'm Julian True. I'm a master's student at Ryerson University in Toronto, and I'll be speaking today about our work on motion vector extrapolation for video object detection. That's a mouthful, so I'm going to call it MoveX from now on. So there's been a lot of research done that we've seen in order to attempt to break the existence of this speed accuracy trade-off in object detection, where models and approaches tend to trade off some accuracy in order to gain speed, because it's all fine and dandy to have the most accurate model in town, but if it takes a whole data center to use it, it's not particularly fast. But it actually goes a bit deeper than that. Once again, if you have a whole data center, you can probably have your speed and accuracy and have your cake and eat it too. But really, if you want the trifecta of low cost compute, accuracy, and speed, you're kind of up the creek without the paddle so far. So existing approaches to try and remedy this have been kind of taking the shape of this sparse keyframe detection mixed with propagation. And what this really means is, you can run this big expensive object detector DNN, and then you can use a lightweight propagation function that usually incorporates optical flow or feature tracking in order to essentially perturb these detections around across many frames. There's quite a few pieces of work that do that. The problem with this approach is, you're still bottlenecked by the existence of these really expensive object detection approaches. So we actually started our approach from a paper called Deep Feature Flow, which we've just linked to there. And in Deep Feature Flow, they used the FlowNet architecture in order to generate optical flow and then perturb these detections, as to the diagram I had on the last slide. Problem with this approach is you're still running on just a second expensive DNN in order to perturb these detections and compute the optical flow. And so that's really, I guess, the nice segue into our approach here is we do away with the optical flow calculation entirely, and we kind of steal it. We steal it from the H.264 encoded video itself. So what you're seeing on the screen here is actually these macro block translations in between the frames that get just encoded natively when you have video encoded with an H.264 codec. There are other codecs that also do this. We chose H.264 because it's clearly the most prevalent. Doing it this way seems to approximate optical flow fairly well, which we'll show in a second. So with this propagation method that I mentioned before, when you have a detection from an object detector, you can crop out all these motion vectors from the encoder. And if you take the median of it, you can actually get a decent perturb in terms of moving the bounding box around. The reason you'd want to use the median here is because, going back to this slide, these aren't perfect optical flow approximations. They are quite noisy, particularly in areas where there's not much going on, say the flat floor area. That's very clearly not moving, but there's a lot of noise there. So the median is really critical to get rid of that extra noise. So in addition to that, we also introduced this really cool two-worker parallelism model, where worker one is entirely responsible for propagating detections and also maintaining state, which means a couple of things, which we'll come back to. And then worker two just runs object detection all day, every day, as fast as it can. So I'll walk you through an example of what this actually looks like. Just know this approach is called optimistic sparse detection propagation. And so, as I said, worker two starts off by running object detection because that's its whole job. And so once we have those detections, worker one updates the state. So now we have these bounding boxes that we keep track of, and we could start perturbing them with motion vectors. Simultaneously, because this is a parallel algorithm, worker two just starts running object detection again, just right away, next frame. So this continues
several times until worker 2 finishes object detection again. Several propagation steps take place in the amount of time it takes to actually run object detection. So this is where the main speed up comes from here. And so once again, these detections can be merged together and worker 1 can continue to propagate those detections. Now, you might see it already. Worker 2 is producing detections for frame 2, but worker 1 is at frame 7. There's this huge gap now, and for high latency models, you know, this gap would be huge. It could be 10, 20 frames. So it's naive to think that you can just continue to propagate these new detections. So what happens here? Thankfully, worker 1 checks off more than just keeping track of the detection state. It also keeps track of all the motion that's happened throughout the video. And so when it comes time to update the state with this older information, those detections can be repropagated using the exact same algorithm that I just described to bring it up to the current frame. And then it just repeats indefinitely. So is it any good? We tested on the MOT20 data set specifically. For those of you who don't know, but you're at this workshop, so I'm assuming you do know, MOT20 is very dense. And the reason why we chose MOT20 specifically is that update prior step is quadratic to the number of people who are in the frame. So you might already see that this is a giant smoke test for this approach. Like if there's just too many people, does it crash and take forever? Well, we'll see. We also use 2 different object detectors because this approach is object detector agnostic. So we use faster RCNN and YOLO v4 in order to see if our guess at the H.264 motion vectors being a decent approximation of optical flow. We evaluated against FlowNet v2 as well, so the latest and greatest. We used 2 different input resolutions to the YOLO v4 model, which is a neat little trick I'll get into in a minute. And we used 2 different pieces of hardware, one non-specialized CPU and the best GPU ever fabbed, the 1080 Ti. So results, let's get right into it. So as I said, this is a bit of a smoke test and we pass. We get this nice 10x speed up from comparing against just the default object detector. And we only concede 0.5 AP in order to gain that additional speed. So if that trade-off is in your budget, that's a pretty solid deal in my opinion. Similarly, with the high resolution YOLO model, we see a 6.8 x speed up and only 0.1 accuracy loss. But it's more interesting to look at the high resolution YOLO model with MoveX on it compared to the default resolution of the YOLO model, because when you look at it that way, when latency isn't a problem, you can actually get a huge accuracy increase. So here we get a 14.3 AP increase when we use this higher resolution model with MoveX, and it's still faster than the original YOLO model, which is a really interesting kind of like, that line just snaps in half on the speed accuracy trade-off line because there's no trade-off there. You've maximized both of them. And then lastly, if if your wallet's hurting, which it is for some of us these days, if you can't afford the best GPU ever created and you need to use a CPU, well, you can expect a really nice 25x speed up while only sacrificing 0.4 AP. So that is quite remarkable. And I just wanted to point out here, because I realized I've completely forgot to highlight the FlowNet and H.264 approach. But if you take a look just in the second and third row there, FlowNet does do marginally better than using just straight H.264 motion vectors. However, the latency is just blown right out of the water as soon as you introduce 2 separate neural networks. So future work. Unfortunately, this is not really the forum to display everything about this. This is like a whirlwind introduction to MoveX, but occlusion is a big challenge for this approach. As you see here, when you just have motion and nothing additional smart going on here, the front 2 people seem to just take the detections with them as they walk by, which is obviously not ideal. Additionally, it's worth to point out that this approach is we believed to be dependent on the encoding quality. So an ablation study would definitely be in order for that. Thankfully, we've already done that. And so you can expect that in an upcoming paper, as well as some other ablations to demonstrate how robust this technique actually is. And then last but not least, the future work on the open source package is definitely a requirement. Because the inputs to this approach are so interchangeable, making this easy to use and easy to integrate in future work is a paramount priority. The open source package right now is just designed to run experiments when really it should be designed to be used. And with that, I'll just put that up there so everyone gets credit where credit is due. And thanks for your time, everyone.
Thank you, Julian. That was a fantastic oral, and congratulations on being the runner-up for the Best Paper Award for this workshop.
Thanks so much.
No problem. So let's move along in the schedule. So next up, we have a keynote talk with two speakers. So we have Chris Katani, professor at Carnegie Mellon University, and his, I believe, PhD student, Jinzhou Wang. I hope I'm pronouncing that okay. And they're going to be together talking today about the interaction between future trajectory, I always pronounce that funny, future trajectory prediction and tracking. So without further ado, I'm going to hand over to them to begin their talk.
Great. So thanks for the introduction. So we'll get started. So we kind of changed the title a little bit. So this is a new perspective on perception and the prediction pipeline for autonomous driving. All right, so let's get started. So as we all know, perception and prediction are a really important part of the autonomous driving stack. Okay. And this is what the standard pipeline and the standard perception and prediction pipeline looks like in autonomous driving and really also for like any kind of autonomous system, right? So there's like a sensor data that's coming in, which depends on your sensor suite. There's a perception block, and then it's usually followed by a prediction block. Okay. So let's kind of talk about each of these blocks just as review. So in autonomous driving, it's going to be really common to have LiDAR or RGB as input. You could also have radar. Then that data is going to get passed to our perception algorithm, right? So this would go to 3D object detection. And then once you've detected your 3D objects, you're going to pass this on to 3D object tracking. Okay, and of course, in parallel to all of this, we didn't really write this here, but there's state estimation that's happening. So you're going to be using LiDAR, vision, GPS to localize yourself. Okay. And so that's going to contextualize the 3D objects and 3D tracks. And then once you do that, we're going to we're going to forecast trajectory. So we want to know how each of the agents, so cars and peoples and bikes, motorcycles, how are they going to move into the future? And then all of this is going to get passed on to a planning and control part of the pipeline, right? That actually controls the car, comes up with a plan that the car should take. Okay. So what we've been thinking about is this pipeline optimal, right? This is pretty standard. Is there some type of update that we can make to this pipeline that maybe will help us to solve the problem in a different way or maybe in a better way? So most of us in perception have been working, I think, on each of these blocks, right? So improving the sensor, the detection, the tracking, or the forecasting. And for the most part, the optimization has been happening kind of separately, right, in the different subfields. And then, there's good reason for that because we hope we could just plug it back into the pipeline and the whole pipeline will get better. All right, so let's think about this pipeline and kind of poke some holes at it and see if we can open up some new research directions. So if you think of maybe going from the sensor data to the 3D object detection, a lot of what exists now, at least in computer vision, depends on predefined object categories, right? So for our kind of benchmarks, we want to find cars, we want to find people, and we want to find cyclists. What about objects that, what about objects that you've never seen before, or some kind of novel obstacle? How are we going to deal with that? The next one is dealing with uncertainty, right? So you could have uncertainty at the sensor level. You could have uncertainty at the object detection level. At any of these modules, you could have uncertainty. And it's really not clear how to propagate that uncertainty, even within the perception task. But if you think about the full autonomy stack, we don't really know how we should take uncertainty in our sensor measurements and then propagate that all the way into planning and control, like end to end, right? So that's kind of an open question. I guess the next point here, limited evaluation based on downstream tasks. I kind of mentioned that already. Most of the perception that we do is evaluated on benchmarks just for that one block that we're focusing on. But how much does, 5% improvement in tracking, how much is that going to actually affect planning or control? We don't know. And then another problem with any kind of pipeline is that because this is a sequential process, we're going to be propagating errors throughout. So this is kind of related to the idea of uncertainty, but how do we take care of that? How do we model that? How do we evaluate that? And then the next part, which the talk is going to kind of focus on is, is there a different order that we could be using? Does it really have to be this sequence? So if we wanted to do trajectory forecasting, does it have to happen after we do object detection and object tracking? Right. Go to the next slide. What if we moved this trajectory forecasting to somewhere else? Like, can we move it right after the 3D object detection, so no tracking? Or can we move the prediction to right after the sensor data? Can we do it there? And then what's that pipeline going to look like? Right, next slide. So what we're going to do is explain some of our first tries at kind of messing around with this data processing pipeline and see if we can't come up with a different kind of paradigm. So I'm going to hand it off to Shincho, who's been doing a lot of great work in this area in our lab, and we'll cover these two topics. Okay, Shincho, go ahead, take it away.
Okay, thanks, Chris, for the motivation. Yeah, so next I'm going to talk about two pipelines that we have been playing around for a year, more than a year in the lab. The first is a forecast and track pipeline. It's kind of like lies in an intersection between forecasting and tracking, right? And the second one is a little bit different. It's parallelized tracking and prediction, still like trying to understand the relationship between tracking and prediction. How should we do them in a different order or different paradigm? Okay, I'm going to jump right into it. First, the forecast, then track pipeline. Okay. So again, we show here the standard pipeline, but in a more compact way, which is track, then forecast, or detect, then track, then forecast, right? We have detection and tracking and forecasting, as Chris just mentioned. And in our pipeline, which is a little bit different, where we do forecasting at the first step, and then apply detection and tracking, right? But because we do forecasting upfront, then it's forecasting the sensor data rather than forecasting trajectory or objects, right? Because now we don't have objects detected already. So then once we forecast the point clouds into the future, we apply detection and tracking on top of it to get the fellow trajectory. So that's equivalent to what you can get in the standard pipeline. And the difference I just mentioned, we move forecasting upfront and we forecasted the sensor data, the point cloud, not object positions. Okay. And to give you a sense of what we're really doing or what we can do after we train the model, this is the results or some simple demo. The frame rate is a little bit low due to the online video conferencing, but you can see that our forecasted point cloud and also the trajectories on top of the forecasted point cloud both can be demonstrated here. And the conclusion is that our pipeline, the SP square, sequential point cloud forecasting for sequential post forecasting, right? So this pipeline can really provide stable object trajectory prediction, even though we are forecasting the point cloud. And the forecasting point clouds can preserve the object information, this kind of bumps or blobs in the point clouds, where the detection and tracking algorithm can really find those objects, even though they don't really look like a real-world, realistic object point cloud. but they can find it. So that's fine. Okay. So this is like the simple demo to give you a sense of what we are doing. And next, I'm going to talk about the core advantage of this new pipeline, right? So the main thing is that we can do performance scaling with more point cloud data. Why is that? So first of all, because we are doing forecasting on the point cloud, right? It's essentially a self-supervised learning paradigm, or we don't really need human annotation for object labels, right? Because we only need to have sensor data in the training and testing. And we already know that point cloud data is prevalent in all of these data sets like NewScenes, Waymo, Argo, Verse, whatsoever. There are so many data sets, so we can leverage all of those enabled data to kind of improve the point cloud forecasting module. And all of these advantages actually in the core, just one advantage which we don't need training data, which we don't need human annotation for training, is benefiting from this new task, sequential point cloud forecasting we're proposing here. Okay, so one simple experiment we did before is on Kitty, where we just simply demonstrate that if we withhold different amount of training data, but evaluate on the same set of test data, then we can get higher performance as shown on this figure where the errors goes down by adding more kind of training, by adding more amount of training data, right? So you have more training data and the error goes down. So that simply demonstrates our performance scaling property with these point cloud forecasting task. Okay. Next, we're going to show a kind of overview how or what exactly this task is going to about. So as I talked before, the goal is very clear. It's trying to predict a sequence of future clouds based on a sequence of past clouds, right? And the key difference compared to the trajectory forecasting we had before is that we're predicting the entire scene, not just these foreground objects, but also including background. And another challenge is that we're dealing with very large scale point cloud sequence, right? It's like at every single frame, we have 115,000 points. And then over a sequence, let's say 10 frames, we have 1.5 million of points. That is much larger than the indoor object point cloud normally with a few thousand points, right? For chair, desk, and etc. Okay. So how can we deal with this challenge, right? How can we learn representation from large-scale point cloud sequences? We really build a very simple baseline in our first work, which is based on 1D stream autoencoder. That is essentially having first a frame-wise point cloud encoder that encodes point cloud at every time step in the past, and then use our STM or other recurrent units to propagate the temporal information. And then we do decoding for the future frame to get the point cloud at each individual frame. And we optimize the predictive point cloud. So that's the first baseline we have built. And it's really efficient because we are using very compressed representation to deal with this large scale point cloud data. Okay. And here are some more results we have on the point cloud sequence generation. We have, if you look at this result, we have all of the objects predicted along the sidewalk for those parked cars, and also some cars that are moving. We can also capture them. Again, the frame rate seems to be a little bit low. So if you want to see more results, we have it on our website. Okay. And then again, we are doing some downstream tasks on top of it. For example, we can apply detector on top of the forecasted point cloud. Right here, we simply demonstrate how the detected objects on our point cloud compared to the ground truth objects bounding boxes. Right, the ground truth is showing yellow, and our detected box on our forecasted point cloud is showing green. If they are matching well, then that means our forecasted point cloud preserve information for objects, and our detector can really find those objects, right? Okay. And after detection, we have tracking, basically trying to associate the detected objects across frame. That will give you some trajectories of each objects on top of our forecasted point cloud. Again, the Nuke temporally consistent on our visualization, although the forecasted point cloud kind of not really super realistic. Okay, so we have some recent work on further improving the point cloud forecasting and then downstream on top of it, but it's not super relevant to this workshop because it's more about tracking. So we're not going to talk about that. And next, I'm going to briefly mention another pipeline we have, which investigates the relationship between track and prediction, which we do in parallel. So we call it parallelized track and prediction, or PTP in brief. Okay. So here we motivate this design. It's by saying, again, that we have this sequential pipeline, right? Is it going to have some problem, right? We have a lot of problem, like as Chris suggested before. And one of the main things is that they are sequential in terms of the each module is each downstream is taking inputs from the upstream output, right? If the upstream has some errors, then that will definitely affect the downstream. And here we show a very simple demonstration here, right? So here we have the solid lines demonstrating the path trajectory, for example, obtained from tracking, and dotted lines represent the predicted trajectories given by the prediction module. But if we look at the figure on the left, if we have these two objects moving toward each other and the tracking is done perfectly, and we have the predicted trajectory fine, looks fine. But if there is an identity switch or data association error happening in the last frame of the tracking, then that can completely mess up the velocity of two objects and make the prediction module predict some kind of weird direction that the object is going to move, right? So that's something we need to take care about. So the key question is that can we move beyond this sequential pipeline? Okay. So kind of to inspire our design, here we look again about this sequential pipeline, but more in a more detailed manner, right? So in the tracking, we find that we normally have this feature extraction and the matching module. And in the prediction, again, we have feature extraction and trajectory decoder module, right? So they have kind of similar components that try to learn motion and sometimes appearance for tracking, but mostly motion for trajectory prediction, right? So they're kind of sharing similar components here. And in the meantime, they have module-specific components like the trajectory decoder and also matching for tracking, right? So based on those observations, we can design something more smart that we think here is that we're kind of combining or sharing the feature learning process in a unified manner for both branches. And then we move the module-specific components to each individual head for tracking and the prediction, right? So that kind of makes it in parallel like this. So that's why we call it PTP, parallelized tracking and prediction. And this work is present at ICRA, but here we show a simple demo. On the left, we have this 3D tracking only results, which is from our previous work that's only done tracking. But it's kind of similar to what we do here in the PTP, but only in the one branch of it, right? But on the right, when we have this PTP framework, we have tracking and prediction that's happening at the same time. We can have the corner box represent the identity from tracking, and we have the predicted trajectory for each object. Okay. So that's basically demonstrating what we're doing. Next, I'm going to briefly talk about how we do it. So first, the reason that we are kind of coming up with this pipeline is that we think we can reduce error propagation from tracking and prediction. And the second is that we hope this shared feature learning can make the entire pipeline more efficient and improve performance. And here's the overview of the pipeline. We have this shared feature learning process as just introduced, and then we have multi-object tracking head and trajectory forecasting head. And they're separate. They're separately processed in parallel. Okay. And each individual module is actually very straightforward. For example, for the shared feature learning, we have this standard temporal and social feature encoding, right? The temporal, we have LSTM. And for bounding box at a single frame, we use multilinear perceptron to encode location information. And to encode the spatial or the social interaction information, we use graph neural networks. Both are very standard way of encoding the feature from the past information. And then for the 3D multi-object tracking, we are trying to learn this association or affinity matrix and supervise it with ground truth. As we know, the binary ground truth affinity matrix, the 0 and 1, which object should match to which in the ground truth, right? And at testing, we are just feeding these affinity matrix to standard Hungarian algorithm to obtain the phylum tracks. And what's more involved here is this trajectory prediction head. So first of all, we are using very standard conditional variational autoencoder, right? We have these sampling, and then we have this trajectory decoder stage. But something different here is that we're also adding a diversity sampling function. The reason is that we're trying to increase the trajectory sample diversity. So here, let's look at like why we're doing this, or like what's the limitation of this PDP framework, right? So, but before that, I would like to just briefly mention we have done some experiment and ablation, which shown that it's indeed helpful to do these two modules in parallel at the same time, rather than like doing one module at a time. But I'm not going to show boring numbers. You can find all of this ablation in the paper. So here I'm going to talk about two recent work we have done. It's still ongoing, but we have demonstrated very promising performance. So the first work that we're trying to address is this posterior collapse problem in the trajectory prediction. And the second is loss of information in feature encoding. Okay, so first of all, this posterior collapse problem. So again, we have this CVE framework, right? So it's very simple. We have the data distribution looks here. Given the past feature, we're kind of predict future. And normally we have different kind of modes. Some modes has larger likelihood, some has lower. And we're trying to learn this generative model, like conditional variational autoencoder. And we are trying to recover this latent space with different modes. And then we are going to do random sampling from the modes from the latent space, and each sample corresponds to each trajectory, right? So these are all very standard. But this pipeline had this low sample efficiency issue is that because the blue mode here has the most data, the data is always imbalanced. So most likely we are sampling more trajectory or more latent codes from this blue mode, kind of ignoring other small modes, unless we're sampling a large number of samples, right? So that's why we're kind of have this low sample efficiency issue. So the simple solution here we're offering is this diversity sampling function. Again, everything looks very similar. We are adding an additional function here, and we're sampling codes, the latent codes, and each code corresponds to trajectory. But the key difference lies in here, right? So once we have the trajectory sampled here, we kind of want to push them away and to make them cover different modes. So that's by maximizing their distance, right? So this trajectory will be pushed away and cover different modes. And accordingly, if you look at the latent space, each of these latent codes will be pushed away as well, because the entire pipeline is differentiable. For example, the diversity sample function is differentiable. Okay, so that's for the first work we had. Let's try to address the posterior collapse problem. And the next work is this. Is trying to address this problem, which we call loss of information in feature encoding. So what does this mean is that, again, if we look at this PTB framework, we're encoding the features in two stages. First, temporal, and then social, right? This is very standard, use LSTM, and then use graph neural networks. However, like one of the standard issue in LSTM, like many people know, is that at the end of the day, oh, sorry. My bottle just falls down. Yeah, so at the end of the LSTM module here, we have this one-dimensional feature that we hope can encode the feature of all past historical information. But normally it's not, right? It's kind of, it will forget some level of information of past or the historical time steps, right? So that's something we don't want, because that will leads to loss of information in the social feature encoding stage, because agent cannot see other agents' past information to some extent. Okay, to address that problem, we are proposing a very simple solution using transformer. So again, on the top, we show this standard temporal then social paradigm, right? But on the bottom, what we're doing something different here is that we're putting all information, like all agents, all time steps information together into a single model that is trying to model these both temporal and social information in 2 dimensions jointly, right? So this is something simple, but we're using transformer to encode this property. And as a result, we are having this nice property of allowing an agent state at one time to directly interact with another agent's states at any time stripe, either the future or the past. So that's something good. Okay, so I think this slide summarizes like the second part of the talk, the parallelized tracking and prediction. Like by combining all of the techniques that we just introduced, the newest model we have, the Agent Informer, that's really reached the state-of-the-art performance on standard trajectory forecasting benchmarks like ETH, UCY, and new things. And the one thing we're kind of proud of is that we're also beating Trajectron++, which is really a very strong trajectory forecasting algorithm to the best of our knowledge, and it's also open source. But we're kind of beating it even it has a little bit higher performance. And our paper is on arXiv. Okay, so at last, we would like to advertise another one of our work that is on autonomous driving, basically an all-inclusive perception data set. And we have all of these annotations for mainstream perception tasks, detection, tracking, segmentation, video, panoptic, like in all dimensions. And we have comprehensive sensor modalities. Something kind of novel is that we have SPAD LiDAR and also high density long-range LiDAR is kind of like even denser than standard Velodyne 64 LiDAR. And we have diverse environmental variations like out of distribution data like car crash or highway pileup. This dataset is built on top of Carla. It's a state-of-the-art high-fidelity simulator. So that's why we are kind of having all these slides property. But we're trying to use this data to benchmark progress on all of our works and other public works for the autonomous driving. And we hope it's useful to multi-sensor, multitask perception system because we basically have everything here, very comprehensive data set. Okay. Thank you all for listening. I hope you enjoyed the talk, and thanks for the organizer. Chris, you want to add something?
No, that's good. Thank you, everybody.
Hi, Jonathan. I think you are muted or your microphone has some problem. I can't hear you. Chris, can you hear him? Or no?
No, I don't hear you. I can't hear you.
Oh, yeah, now? It works. Yes? It works. Yeah.
Okay. Yeah, there was a button that needed to be pressed. So let's have 4 minutes of questions. So I don't see anybody jumping up to ask some questions. So I guess I can go ahead. Let me check YouTube first. Okay, there's a question on YouTube. So the question says, let me just read it and paraphrase it for a second. So the question is, like what does each point in a trajectory represent, and how many past points are used to predict the future trajectory?
I think that's a question for the point cloud forecasting, right? How many points are used to predict future trajectories? I mean, in the standard LiDAR point cloud we use from the Velodyne 64, it's about 150K points. So it's still sparse, right? People normally see point clouds, LiDAR point clouds are sparse, but it's very large scale in terms of the data, I think, because you have 10 frames of the point cloud. And I think that's the second part of the question. It's I forget the first part.
Yeah, I think you answered the question. I think that's good. So we have another question from Tobias. So you're up, Tobias.
Right. So my question would be about the PTP model. If you could go back to the slide of the overview of the architecture. Yeah, here. So the features for the past frames, do they get updated in the graph neural network over time?
So here we're only using a 2-frame graph neural networks. So basically, past frame and current frame. The past frame encodes the 10 past frames. We're kind of moving compress them into a single latent feature. We hope it can encode all 10 pass frame of information, but as I introduced later in the newer work, it's not, right? So we only have 2-frame graph. So like this kind of tracking and prediction pipeline is like when we do testing, we are moving them 1 frame by 1 frame incrementally. So the graph doesn't need to update, but the data is kind of coming in the streaming manners, and we kind of update data and feed different data to the model.
Because in the slide before, I think in the visualization of the forecasting, it's at the intersection. It always looks like all the cars want to go left, right? Which I would assume is when you aggregate the features over the last time steps would not happen, because then it knows the car is going to go straight, most likely due to its velocity and the path. So have you visualized maybe then in the newer work with Transformer, if this still happens, if the cars still want to turn left?
Yeah, actually in this work, probably this image visualization is not so good. I mean, in the LiDAR one, it's a little bit more, like the bird eye view visualization is a little bit more clear, where actually we're having a lot of trajectory turning left, but we also have trajectory moving straight. So they're kind of disappear and appear across frame to frame. So I think the kind of observation that's keeping a possible trajectory turning left is making sense, because we're using the diversity sampling function. Sometimes even we have this U-turn predict trajectory, which is almost not possible, but we have that data. We have that trajectory predicted in our model, because that data has been seen in the training. Although it's very rare to happen, but it's possible to be predicted because of the diversity sampling function. But if we have a better model like the Transformer one, I think we didn't do direct comparison, because that model we evaluated on ETH UCY and the new things, not on the KD anymore, because I mean KD normally people don't use for trajectory forecasting benchmark. But since this work we're doing tracking as well, so that's why we use these KD data sets as kind of a demonstration. Because ETH UCY I don't think many people are using for tracking, I think, for example. Yeah.
No, of course. Yeah.
Okay, so thank you very much, Chris and Xinshao. Hope I pronounced that right.
Thank you.
So Chris will be around for the panel session later, that's correct?
Yep, that's right.
Awesome. So if you have any more questions for Chris, he'll be around. Xinshao won't be around, unfortunately. But then she has something else she has to do, but Chris will be around. So keep your questions and we'll have a chance for more discussion later. So let's move on to the next event. So next we have the Best Paper Award oral for the Best Paper Award. So the Best Paper Award for submitted paper this year goes to Charag Yang from the University of Oxford for his work and his collaborators, of course, but he's giving the presentation for his work on self-supervised video object segmentation by motion grouping. So take it away for the 10-minute oral presentation for the Best Paper Award.
Cool. Can you hear me and can you see my screen?
Yes and yes.
Okay. Thank you for the introduction, Jonathan. Hi, everyone. My name is Charag Yang. Today, I'm presenting self-supervised video object segmentation by motion grouping. This work is in collaboration with Hela Lamdor, Erica Liu, Andrew Zisman, and Wei Xie at VGG, University of Oxford. Over the past years, we have seen so much progress in object segmentation. Current systems work great and are capable of segmenting things from cars to humans with good accuracy. And this is true in many cases, including the example in the top row, where visual appearance cues of the cyclist and the bicycle are quite obvious. Even so, training a segmentation model this way requires a lot of manual annotations, with each labeled frame taking up to an hour. Labeling thousands, if not tens of thousands of these is simply not scalable. Moreover, in the natural world, there exist cases where relying on appearance alone is not enough. For example, if you look at the photo in the bottom row, it is quite difficult to identify the fish in the photo, as it is almost the same as the background. And this poses a challenge to current RGB-based segmentation systems. Therefore, in this paper, we aim to solve both problems by doing segmentation using motions in a self-supervised manner, which means without using any manual annotations. To achieve this, we adopt an autoencoder framework which decomposes the input optical flow into layers. Each layer contains an optical flow and an alpha channel. This alpha channel ranges from 0 being completely transparent to 1 being completely opaque, and sums to 1 across all the layers. Intuitively, the reason why this layered representation works is that the foreground movement, which is caused by the subject in the video, is independent from the background, which is caused by camera motion. Hence, the easiest solution for this model is for each layer to represent a homogeneous field, with discontinuity only appearing in between layers. The alpha channels end up as the segmentation mask after training. To train this model in a self-supervised manner, we reconstruct the input optical flow using linear composition of the layers using the alpha channels. We then simply train the model using a pixel-wise regression loss. The architecture of this model consists of 3 parts. First, the encoder, which encodes the input optical flow into a feature map. Next, the iterative binding module, which groups pixels of similar motion together with a transformer variant called slot attention. More details about slot attention can be found in the reference paper, but in a sense, it is performing a similar role to a soft k-means clustering using transformers. This is done by having multiple query vectors and a softmax applied along the query axis, which forces the query vectors to compete to explain part of the input. After the iterative refinement, each pixel is then assigned to one of the queries. Lastly, the decoder, which decodes each query vector into a full resolution mask and optical flow. This involves a broadcasting operation, followed by a series of lightweight transpose convolutions. During training, these layers can then be composed and trained using the framework explained previously. During inference, these alpha channels end up as the segmentation mask. One of the challenges in this framework is that when the object undergoes similar motion to the camera, as shown in the picture below, it violates our assumption that object movement has no correlation with the camera motion. Hence, object will not be clearly visible in the flow field. To overcome this problem, we compute flows with different frame gaps, both positive and negative in time, and force consistency on the inferred alpha channels. This is based on the intuition that the object has to remain the same, no matter the time gap between the frames that we compute the optical flow with. This consistency comes in the form of a pixel-wise regression loss between the mask. Note that layers are commutative, so the loss is permutation invariant. The full architecture is shown in the figure below. In essence, for a reference frame, we randomly sample 2 neighboring frames and use the optical flow between the reference frame and each of those frames as input. We pass the optical flow pairs into the model and impose a reconstruction loss onto the output. We also impose a consistency loss between the 2 alpha channels. Note that during inference time, only a single model or half of this figure is required. We evaluate our model against 4 different datasets: SegTrack v2, FBMS 59, Davis 2016, and Moving Camouflage Animals, or MoCA. For the first 3 datasets, we report the Jaggard score, or the mean IOU between the predicted and ground truth segmentation mask. For the MoCA dataset, as only bounding boxes are provided, we additionally report the detection success rate, where the bounding box IOU overlap is above a certain threshold. On the Davis 2016 video object segmentation benchmark, which I believe you all should be quite familiar with, we show that the gap between self-supervised and supervised approaches has been largely minimized. Our model is also at least an order of magnitude faster than other previous works, at over 80 frames per second, as we do not use any post-processing in our model. On the MoCA dataset, what we can observe is that supervised methods that solely rely on appearance, such as COSNET, can perform among the top methods on Davis, but struggle to perform on MoCA. Our method, on the other hand, is competitive with the top supervised approaches that use both RGB and flow information. And this highlights the importance of using motion cues in doing segmentation, especially in natural scenes. Here are some qualitative results on the Davis 2016 dataset. Note that RGB is not used in our model and is only provided for illustration. Here are some more results on the MoCA dataset, where it is significantly more challenging to perform segmentation by visual appearance cues alone. In this slide, we show some cases where our model fails. As our model only takes optical flow as input, if the optical flow is wrong or not informative, it will fail. Optical flow is a field that is under active research, and we expect optical flow to be improved in time to come. Lastly, we think that there are a few potential directions to develop this work. First, we can generalize the model towards having multiple objects with more layers than 2. And second, we can also employ some heuristics, such as temporal smoothness, into the model to account for the cases where the flow fails. Thank you for listening. The full paper and the code are available on the website. Thank you.
Thank you very much, Charik. Awesome oral. So that was the paper that was awarded the Best Paper Award for the submission track of our workshop. So now we're going to move on to what is, at least for me, the most exciting part of the schedule, which is the panel session. So it would be great if all of our panelists could turn on their video if they're willing, and yeah, I'm excited. So we have about an hour here. So I'll go through and introduce the panelists, maybe one at a time, and maybe we'll go through with an introductory question for each of the panelists as I introduce you real quick. So I want to start. So maybe real quick, we have Chris Catani, who just gave a talk from CMU, Judy Hoffman, who gave a talk before that and she's a professor at Georgia Tech. Vaidi Shi, who is in Oxford and at the University of Oxford, and he gave an invited talk this morning. Philip Cramble at University of Texas in Austin, who also gave an invited talk this morning. And the fifth member of the panel is Sanya Fidler, and she will be here a little bit later in about 20 minutes. She had something else come up, but she will arrive and then give an invited talk after this. So for now, there is 4 of you. I'm going to start by asking some questions. And we have an hour, so I highly recommend that all of the people, all of the rest of the people in the Zoom link, if they have any questions, get involved and ask their questions of all the speakers. It's a rare opportunity to have an hour to sit down and talk about whatever we want to talk about, so I'm very excited. And if you're watching on YouTube, also feel free to write questions there, and I'll try and check it every so often and get your feedback. So my initial question for all of you, we're going to go through one at a time just to kind of kickstart the conversation, is I want to look at something that we don't talk about too often, which is kind of long-term horizon for research on kind of the topic of this workshop. So video understanding, maybe particularly tracking and segmentation, but maybe not. So the question I'm going to go through one at a time, and I want you, I mean, I'm putting you on the spot, but I guess that's the point of the panel, is to tell me something that you're excited about. One of the things you're most excited about that's you expect to be about 5 years from now. So long-term horizon, what's something that you're super excited about that's coming up, but not immediately, but it's coming up soon. So we're gonna go in the order that I can see it on the screen. So I have Chris first.
Sure. Okay. So I did talk about this a little bit at the beginning of our talk, but one of the trends that I see, or maybe one of the trends that I'm following, or trends that I'm trying to set, is that I think perception algorithms. So it could be segmentation, it could be tracking, it could be forecasting. A lot of these are eventually going to be used in some kind of autonomous system, right? So it might be autonomous driving, it might be humanoid robot, domestic robot, it might be unmanned aerial vehicles. There are a lot of different kinds of applications, and I think it's going to be important to understand how changes in perception algorithms have an impact on the final action that your autonomous agent is going to take. So I would say in 5 years from now, I would expect there to be a lot more work that's trying to do end-to-end learning of perception in the context of kind of a bigger task. So like I said, it might be autonomous driving, it might be planning, it might be control, it might be human-robot interaction. But I think that's going to give us a new perspective on perception and maybe give us some new discoveries about what we actually need, right? So yeah, that's my perspective.
Yeah, super awesome. So that sounds like something we should definitely come back to later. But for now, let's go through all the speakers and hear what they have to say. So Judy, you're next on my screen.
Yeah, I share a lot of the same thoughts as Chris. I think that we're seeing a lot of new works coming out that are combining multiple sources of information together. It could be through embodied tasks where an environment provides additional sources of information. It could be through multimodal. When you're working with video, you frequently also have audio. I've seen a lot of really interesting things leveraging the co-occurrence of information in that space. But and then of course, just broadly in the learning community, there's been this explosion of contrastive learning and other forms of self-supervised learning. So as soon as you have multiple pieces of information that are coming at the same time, again, through any of these sources, I think it opens up opportunities to create more forms of unsupervised learning that we'll see over the next few years.
Awesome. Thank you very much. And Wei.
Oh, can you hear me?
Yes, excellent.
Yeah. Well, I think the most thing I feel excited is really, well, several things. So the first thing would be self-supervised learning. Of course, that's why I'm doing this research. And I think once we get self-supervised learning done, like to a certain level, like the object-centric representation, we can represent objects. I mean, we can represent images in SPAT with respect to objects, not in pixels. Then we can train, something like what language people are doing. You can train really just train predictive model, or you can train something like BERT or these kind of thing, because like languages, things are already pre-segmented for you. And I think that's the thing I'm interested. And whenever we get there, we can do long-term video understanding, because really I want to understand videos like 2 hours, but now we can't do that because you process images or frames, it's just hopeless. And also that's one thing I'm interested in. And the other thing would be the open set problem. Again, similar to what I just described. If you can get object-centric representation, then we can train big models, and you can represent things you never have supervision. And I think that's important, because otherwise we can never collect a same data set as the world distributed. So we need open set. Yeah, that's what I feel I'm going to do maybe long-termly. Yeah.
Awesome. Let's go for Philip.
All right. Yeah. Maybe let me say that for applications, I mean, I completely agree that like there's many exciting applications that we should look at and that should inform what we do. I would maybe add that there's probably more than just robotics applications that can guide tracking. Video understanding is one of them. I think Facebook has a strong interest in understanding what you're watching, so does TikTok, so that it can serve you better ads, and that will always be a driving factor, if we like it or not. And I think there's many applications like these that we shouldn't forget about. And the other thing I'm really excited about is like scaling this up to kind of either through self-supervised methods or through just using all the supervision that we have, scaling it up to kind of number of classes that we couldn't scale things up before, to essentially try to track everything that we could ever track. Yeah.
Okay, awesome. So now that we've heard from the four panelists that we have here at the moment, I've kind of got everyone hopefully should have a good little overview of what everyone's excited about. So we're gonna deep dive into some topics and get everyone's opinion about it. And at any point, anyone else in the Zoom, feel free to ask some questions. So the more viewpoints we have, the more it's just less me asking questions all the time. So more than happy to have people jumping in with questions. But let's start with scaling this up. So I mentioned this at the very start of my talk, introducing this workshop, is that computer vision works reasonably well for images. I mean, there's lots of problems, but it's working better and better. But video is much harder to scale up. because it's much more data, because it's harder to annotate. So one way to scale this up, like you said, is self-supervised learning. But yeah, so the question is like, how exactly do you think that we're going to scale it up? What do you think is the most promising thing that we can do today, rather than 5 years from now, that we can do, tomorrow in 6 months for the next thing? What's the most promising thing that we can work on now for really scaling this up and really making it work robustly? So let's start with the same order and go for Chris for now.
There's like other people could jump into. I think we'd have to go in alphabetical order, but let's see. So I think one of the things, this is something I think Serge Boulanger kind of brought up at some point, is right now in computer vision, we're in this paradigm where we have like these closed data sets, and we need them for evaluation. We train on one, test on another one. But probably the paradigm that we're aiming for, or which is kind of like an ideal, is this streaming data set, right? So it can be images, it can be language, it could be video, whatever. But it's just this never-ending stream of video. And that's kind of the extreme case of what you're talking about, I think, Jonathan, is, the data sets are getting bigger and bigger and bigger, but just imagine in the end, they're going to be infinite, just continually coming at you. And then so what kind of algorithms do we need to develop if that is like kind of the scenario that we're building up to, or maybe one day we'll have to encounter? So I think a part of machine learning that's maybe like a little overlooked in the computer vision community is this idea of online learning. So not just incremental learning, but the I guess the idea of online learning theory, right? Is, can you come up with algorithms that could do a single pass over the data, but then you have some kind of like theoretical guarantees on their performance with respect to some algorithm parameters if you had all of the data, at once. So I would expect that as we have to deal with bigger and bigger pieces of data, sorry, I think we're gonna need to dive into that area of machine learning a little bit more. I think a lot of it is theoretical right now, but I think there's a lot of practical benefits of online learning theory. So I would expect that 5 years from now, maybe 10 years from now, I would hope to see more of that intersection of computer vision and that area of machine learning. But I think even in the short term, the algorithms are pretty simple. It's mostly like the theoretical analysis, which is a little bit more complex, but I think there's a lot of low-hanging fruit in that area with respect to dealing with lots of data. Yeah.
Does anyone else want to jump in and talk about that?
I can say a little something, though I suspect Phil has a lot to say about it since he brought it up. But just to add to the online learning comment real quick, I think that the way that we're training models right now, especially in a supervised fashion, is a little bit at odds with online learning. So there needs to be, especially if you're using any kind of forced choice, cross entropy style learning objectives. And so there really needs to be advances in how we can integrate new information over time in a scalable way. But that's about category scalability. I suspect the comment before was more about just like the massive amounts of data as well. And I would be curious to hear other panelists' thoughts about that.
Maybe since my name was mentioned, I'll jump in. So yeah, I mean, I think I completely agree with you, Judy. So I think there is these two different aspects. One is scaling up classes or making it essentially agnostic to the sets of classes we reason over. And that is definitely something that is fascinating, and I think we will jump into in the next few years. I mean, we've already seen more and more interest in open set problems. And I think there's a lot of energy building up around this topic. Now, the other aspect, do we need online learning in terms of just the data, the raw data? I'm not fully convinced yet. Maybe that will be a little discussion between Chris and me, because I see our current models, at least with the data augmentation we have, are not really overfitting. They're actually underfitting, slightly under the data augmentation that we use. So I don't quite see what the benefit would be from never looking at the same data twice if we're not yet overfitting to it. Yeah.
Yeah, so I think a lot of it has to do with what is it, like the bounds that you could put on your training and test set. So if you already know what your training or test set space is going to look like, I mean, it's not humongous, then you don't need. Well, there might be other reasons to use online learning, but you don't need to constrain yourself where you only look at the data once, right? You can look at the data many times, and I think that's the regime that we're working in right now, right? Is we have some like reasonable bounds on our test and training distribution, so we can afford to look at the data multiple times. But I think we'll reach a point, since we're talking about the future, where it's going to be open set, and then I think we're going to be at a point where we're even going to be able to struggle to compute basic statistics on data because the data is so big. Like what's the average? What's the max? What's the min? Well, I guess you could do that with a single pass, but that's what I'm kind of thinking in the future. But right, if it's more close set, maybe it online learning is, we don't need to use that.
I mean, in defense of the online learning comment, I think you can probably do both, right? We want to make as strong progress as possible in that first pass, so that if you have a real-time application, you can affect change in the model based off of that first pass, but then hopefully do some offline processing later to further improve.
Yeah. I think so. And then I think Chris Suffer brought up a good point too about this idea of like non-stationarity. So I think that's another one. So I guess we have addressed it in different ways in the computer vision community, but like, yeah, how do we have models that can deal with non-stationary data distributions over time? Like pretty extreme changes. I think that seems like a pretty interesting problem. And if you think about like lifelong learning, things like that could happen. Like you can, again, I'm kind of gravitating back to robotics because I have a bunch of robotics people around me. But, if your robot, starts in some field and then it starts to wander into some metropolitan area, like just all the things that you're beginning to see are totally changing. Both the perception, the terrain, everything about your control. So, how do you deal with that? There's different ways you can deal with it. You could try to learn as you go, or you can try to think in advance of all the things that could happen, and you make a data set and try to cover that as best as possible. But I think that's going to be another challenge. Yeah, 5 years from now, non-stationarity. How do you deal with that? And I guess to a degree, like the domain adaptation and knowledge transfer, those things are actually kind of already starting to address that. Maybe just not in the terms of non-stationarity, but we have like the technology to do that, I think.
Yeah, it's still in its infancy when you're talking about continuous adaptation, though. Most of the time, it's still pretty static assumptions of a fixed, like single transfer, not necessarily data changing seamlessly over time. And actually, I think it's an opportunity for integration with the video recognition community there, because some of the difficulties in studying continuous adaptation just stem from the fact that if you want a reproducible test bed, you're basically creating another data set. And so at least if it was within a cohesive group of types of videos or something like that, then you might be able to kind of evolve over time, but still be integrating in this more natural version of a continuous adaptation.
And maybe to add to this, I think it would be a service if somebody would nicely and concisely define the problem and nicely and concisely provide the data to actually explore it. And that's definitely something that should happen.
Yeah, it would be cool to have like, and I think some of this kind of already exists in terms of like weather cameras and things like that. But you could imagine some person or some agent or something just having a camera on all the time, just recording continuously. And then that would be our benchmark task is, how well can you do on object detection or trajectory forecasting or video segmentation. You just have to start at some point in history and just go forward in time. And then you get evaluated on that.
Yeah, but at the same time, I actually would also be curious what happens if you had thousands of agents that do all of this at the same time and share their data. Would it then mean that adaptation is still needed if you had this at scale? Or is it so that all of them would just cover the span of whatever is possible, right?
Yeah, I think that's a really cool problem. I think that's another thing that we haven't looked up too much into is like this idea of like multi-agent perception learning, right? Is what you're describing is you have tons of agents. So, the straightforward thing to do would you just aggregate all of the data, train on it, and then send your parameters back to all of your agents, and you just like kind of repeat that. But then there are probably like modified versions of that where, the way an agent learns in one space helps another agent, and then you could combine that information and it makes the third agent learn perception better. And there's like more efficient ways to learn. So, sorry, that kind of goes on a different tangent on like multi-agent perception learning. But what were you saying? The original idea of, if you could just have access to more data at once, just huge waterfall of data, do you really need to deal with non-stationarity? Maybe not. I mean, I guess you need a huge computer to put all of that into memory, and then you have to learn from all of that, in batches. But yeah, there's always that trade-off.
We already do that, right? I mean, we already put huge data in computers and train in batches.
Yeah, I mean, but I'm thinking the data that we're going to be dealing with pretty soon is like, it's going to be so huge. I mean, we're going to have issues just even downloading it, like, 5 years from now, maybe. So
also, if you think about it, whenever we train models now, the augmentation, you never see the same data twice. And that's one thing. It's always like slightly different anyway. And also, if you think about how human learns, I don't think learning from the same data, it's a problem, honestly, because we see the same things every day. Like we sit in the same office, on the same desk, use the same mark, and we learn from this. So it's like instance thing, right? Just you see the same instances every day, and you say from different perspectives, different views, and that's why you build very strong visual systems. So I think learning from the same data, to me, it's okay. It's not a bad idea, actually.
So I think you probably. Oh, go ahead, Judy.
Oh, I was just going to comment on that. Do you think that we process all data equally, though? When we see examples repeatedly, I would suspect that we do some sort of selective learning, which is not necessarily the way that it works now, except for implicitly through like reduced loss functions and smaller gradient. But it seems like we should be more active in how we decide when and what to learn from data.
Yeah, well, I definitely agree with that. I mean, there's something like curiosity-driven learning, right? So some theory or some research say we learn things based on our curiosity, like the kid. So if they play the toy, they play today, they are excited, they play a day, but tomorrow they get tired. They don't want to play anymore, and they learn everything about the toy. So I think definitely we need some efficient algorithm decide what to learn and what we can learn at this stage. What we just like calculus for the kids, it's not possible. And what we can't learn at this stage and gradually build the representation. I think that's important. And that also help to do efficient learning, especially now the self-supervised learning is very, very slow. So let's say you train 1,000 epochs, 1 million epochs, and the representation keeps improving. And for some reason, this is not right. We want to be more efficient than that.
I'll respond to this question I see in the, I didn't see the first one. So the second one from Farouk, the question about, if you have multi-agent perception learning, then does that go against like this single agent learning? And there's an example of like human babies and how they learn. So What I was thinking was that it just, the multi-agent perception, I guess we're kind of making up this idea as we go, but the way I see it is, you can share information, right? And so instead of having like one baby learn at a time, you have like multiple babies, but the babies can like optimize and share information with each other so they can learn faster. So I don't think the idea goes out the window. It just enables like a different kind of paradigm that we don't have as humans. I mean, maybe the closest thing we have is we have adults that can teach us, this is like the semantics of an object, right? Or this is dangerous. This is you can play with this. So I think it's kind of similar to that, where somebody teaches us. So maybe multi-agent perception kind of enables that kind of paradigm.
And I mean, to be fair, I mean, the way kids learn is very different from the way our vision systems learn. And I mean, having kids, I mean, I realized that they're born with much more than our networks that are random initialized are born with. And I feel like just making comparisons is somewhat, I don't know, not the most productive way to think about research.
Too much of a gap.
Yeah, exactly. I feel like thinking of it more as an engineering problem actually helps. And as an engineering problem, kind of more data is definitely seems like it doesn't hurt.
Awesome. So that was some great discussion. So let me open up the next can of worms that I'm interested in, which is something. So most of this discussion was kind of like what should we learn a little bit, like should we go into open set recognition, etc. But one interesting question is like, how can we learn this? In particular, what kind of representations do we need? So for example, for tracking, often we've tracked bounding boxes, and now we've moved on to segmentation masks, but they have limitations. Do we really need 3D representations? Some kind of implicit neural representations? What kind of representations do we need to represent the world? Can we represent the world as a single world? Do we really need objects as separate entities in our representation? So maybe to start off with, let's have Wei D, because he mentioned something like this before, and then we'll let the conversation flow.
Yeah, well, because my research experience is limited, so I can only kind of list what I understand this problem, why we do object-centric representation. And to me, that motivates me is it's more efficient to do videos, because now you just represent the objects as a, let's say, single vector, or you represent the attributes, the property, the position, and these things, but you can represent as single vector. But if you represent pixels, that's going to be a lot more data. And when we come to reasoning, for example, and I know this is ill-defined as well, but let's say VQA, just ask question, answer the question, and some of the question will be multi-hop, so you can't give an answer immediately. You want to go back to your memory, which could be 2 hours or 2 days. So if you represent each frame there, it just you can't save that much information. But if you save the objects, get all the objects as entities, and then that's much more efficient. So that's what I think why we do object-centric kind of representation, just do segmentation or track them and save for further process. And for the 3D thing, I think definitely we want to go to 3D, because lots of the tracking problem, you have occlusion, disocclusion, and if you have the depth, then these problems will be much easier to solve, I think. But of course, the 3D, from 2D projection, go back to 3D itself, it's going to be challenging as well.
Yeah, I was going to say something similar. Oh, sorry, Philip. Yeah, I was going to say, I'll be short. I was going to say, I really think that we should be moving to 3D. I think learning representations in 2D for things of projections of things moving in 3D makes the problem a lot harder, the representation problem harder, because we have to learn this representation that's in this like weird like projected folded space, right, when things are actually moving in 3D. So I'll stop there and then I can come back to it.
Yeah, I was just going to say, I think that I know what the representation is not going to be. It's not going to be fixed size. I mean, it makes absolutely no sense to me that we would use a fixed size representation for a video, because when I can take a video of a blank wall and I need 1 bit to represent this video and to understand it, right? Or maybe more than 1 bit, but like, on the other hand, I can have a crowded scene with lots going on, and I would need to really think hard about kind of how do you represent everything that's going on in the scene. So I think it's definitely going to be a representation that somehow adapts to the content. And I often like to think about it just should be a very compact representation that adapts to the content, and objects is one of them. 3D is too. And like every year I try to convince a student of mine to work on 3D and to kind of represent videos in 3D, and every year we fail. And so I'm not, like, the empirical evidence I see right now is not necessarily on 3D side. Also, if you think of kind of the way we represent videos, the most compact way we know to represent videos in our video codecs is just block motion. And I mean, it's sort of sad, but I mean, I don't understand why 3D doesn't help as much as it should, and if it is ever going to help.
You have a question, Bastian?
No, a comment. Maybe it is because we need a slightly different notion of 3D, not fully metric global 3D where everything lives in the same coordinate frame, but more like local 3D frames. So there are some people interacting, and for those, the relative arrangement makes sense. And in order to interpret the motion, we need to infer it, but it doesn't make a real difference if another group of people that is far enough away is now 5 or 6 meters away. So maybe that can be more of a key, a mixture of qualitative and quantitative 3D.
Yeah, I would say I definitely agree with that, and I mean, I actually really liked the binary TTC work that kind of went from optical flow to just binary predictions. And if there's something like this for motion and 3D reasoning on kind of a compact object representation, that would be, I mean, that might be a way out of the current state of 3D prediction.
So good. Just kind of going back to what Bastian was saying, it also kind of depends. So the original question was about representation. It also depends on what your final task is. So, you know, if it's video compression, it might be one thing. If it's, you know, understanding social interactions, it's another thing. If you want to like interact with the environment, you want to do planning and control, that could be, you know, different. Like you actually need to know in metric space where the object is, right, if you want to grab it. So I think representation depends a lot on what the final task is. So kind of going back to my first question about, you know, what I see happening in 5 years is, I think the representations that we're going to need to build in computer vision, as computer vision becomes more useful, those representations, I think, are going to have to contain information to do other tasks, right? So other than just the perception. So maybe it's like a control, or maybe it's, you know, a prediction. Maybe it's like some kind of like language interaction or something. So I think that those representations, I think we're going to be, you know, next 5 years stretched to like get more juice, you know, out of those representations. Yep, that's it.
Cool. So back to me to drop a topic into the mix. So so for the next one, so at the moment, in all of computer vision and all of anything that's called AI, you know, deep learning is that thing, and deep learning has taken over everything. So kind of the question is, do we need more than deep learning? Is deep learning enough? if there's something else that we need, what is it? Is there a complete paradigm shift? In order to make real progress, do we maybe need to drop deep learning? So anyone with any takes on that?
I think deep learning, in the sense that what that means is just an end-to-end learnable function without a lot of constraints or specifications in the intermediate representation. I think we're already seeing that going away a little bit and starting to see some progress when people impose some amount of intermediate control, especially in, I'm thinking of certain tasks that used to be these like massive behemoth of models, like a image-to-image translation type thing, where it had this huge discriminator and generators and lots of parameters and almost no specifications beyond output pixel distances. And people are finding that it works a lot better if you maybe do a little bit of off-the-shelf Fourier processing of the image, or maybe if you are working with people doing a little bit of pose prediction as an intermediate task and doing image-to-image translation in the pose space or things like that. And so be more and more of these hybrid type solutions where you still get the benefit of end-to-end learning systems, but add a little bit of modularity, or at least like implicit modularity to the models.
Maybe to add to this, I think the beauty of the term deep learning is that it absorbs everything else around it. And so whenever there's something else coming, it's probably not going to be drastically different. And so it will still be partially deep learning, and the term will just grow. I mean, we didn't stop saying that non-end-to-end trained systems are not deep learning. It just now all just grows and grows and grows.
Maybe one answer here. I think from the learning paradigm, a lot has become possible. I don't think we are quite at the end yet. But one thing that I see coming is that as systems will get more and more complex, we will get away from the current mode of having fixed training phase, then a dedicated model for object detection, dedicated model for segmentation, and so on. We will have more and more of those components coming together. And at that point, this is something we're already seeing in robotics applications. You can't then afford having everything running all the time on all input anymore. So my prediction is we will see more systems aspects coming into those deep models, where certain components are being activated from time to time, but not everything running all the time and computing, basically, burning computational resources.
Yeah, maybe a more interesting question I have actually for the rest of the panel. So how will we think about deep learning in 5 years from now? Not necessarily is it going to go away, but it actually changed a lot in the last 5 years. I mean, I remember we still put network diagrams in there, and we copied AlexNet in every single paper we wrote when I was still a postdoc. And that definitely doesn't happen anymore, right? We just say one sentence, we use this in this backbone. And now we talk about other concepts. And I'm sure this is going to change, right? And so which parts of it do you think will go away?
I guess I'll jump in. Something that I see that's been really different recently, as opposed to a few years ago, is I think we have to think about our data more. So it's not just the backbone or even the learning objective necessarily, although I think there are advances there as well, but also just exactly how are we processing data. I think it's kind of maybe even a little bit strange that we're still doing this total random sampling. There are new data augmentation techniques that people come out, and those seem to be really, really helpful. But I think one thing that we've learned over the last few years is how important that input data is to the whole learning process. And so I suspect there's going to be a lot more advances just in figuring out what's the most effective, efficient way to modify what we put as input and what order we use that data and which data we decide to use. And there'll probably be, right now, it's one sentence in the papers usually. We use this data set, we apply Randog or something, I don't know, like whatever is the initial augmentation scheme that you're using. And that's that. And that to me is kind of strange that we just say that we loop over the data this many times, because actually, especially as we grow our data sets, it's going to be more and more important that we figure out what data we need for learning.
I think going back to Philip's question, or I guess we're still on the same question. So what's going to disappear in 5 years? I mean, I have no idea, but one area, what I hope is that like I'd like to see like more advances in neural architecture search for that are more generic, that you can apply to different problems. I think we're still spending a lot of time thinking about the architecture when we start moving into new tasks, and then we discover a lot of things, but if there's like some magical algorithm, neural architecture search, you give it the input, you give it the output, and it's gonna all of a sudden tell you like what the best arrangement of everything is. I think that would be great. That area though is a little tricky. I mean, I feel like you need some massive resources to kind of work in that area, and then I mean, we've seen some pretty good big advances, I think, in neural architecture search, but it's nowhere near the level of like generalization that I would like to see. So maybe we'll be there in 5-10 years where we have a lot more tools that we can call on to kind of make these architectures and models for us. Maybe.
So I guess maybe we will see something like the inductive bias will disappear eventually, because from the beginning we use AlexNet. It really depends on the compute we have and also the data. So to me, because when I started research, it's already deep learning era. So to me, it's a tough question to criticize deep learning because I never do SIFT before. But it's like from AlexNet to VGNet to ResNet to Transformer these days, it's like we are trying to get rid of the inductive bias and also feed more data with more compute. We want the model to learn all these bias. So I guess as the time goes, eventually we want to generalize the model as much as possible and only feed data and ask the model to learn from the data, not design anything. So I think that's what I expected to see.
So I'll throw one in there now because that seems to go against what Judy was saying a little bit earlier, which was that in many regards we're moving away from just end-to-end training it, and we're putting back in these inductive biases, and we're showing that they work way better. So, for example, one of those applications that's super hot right now is NERF, where you put in those 3D inductive biases, and then things actually start to work. And Judy was mentioning that before with some examples as well. And on the other hand is what you're saying, and Sutton's bit of lesson, and all we need is bigger data and bigger compute and more general architectures that can learn everything from the data. But I don't know, where does someone want to bite and talk about where they fit? So firstly, I just want to note that Chris had to log off for another talk. So he says, thanks for a great workshop. So there's some hands up, but maybe if someone wants to jump on and have a comment on that.
I don't know if there's a conflict between the two. I mean, I don't know if there's really a conflict between having a more abstract formulation of your problem and then figuring out what the best way to solve it is, and having inductive biases. I mean, you can have options in this neural architecture search that do have inductive biases. And if you have a good way to evaluate these, they might come up and out on top, right?
Right. I think there's also a difference between specifying how something should be learned versus specifying what information should be learned as part of the process.
Yeah, so what I mean about the inductive bias really is the architectural perspective, because now to me, it's like we are using data to learn inductive bias. So eventually, maybe it's important to pick what data to learn, because when you feed the data, it tells the model what it should learn.
So I just wanted to jump in and introduce Katrina Frakiadaki, who is here now with her camera on. She's going to be giving a keynote invited talk later on, I think the last one of the evening. So welcome to the panel session. So you have your hand up. Do you have a question or a comment?
I do, but if Bastian wants to go first, I'll go next. No, you go first. Please go ahead. Okay. So one comment is, I mean, these attention layers, right? I mean, I don't think we're trying to get rid of inductive bias. I think we're trying to find the right inductive bias. I think this pointing and indexing, to me, it is completely mind-blowing how people thought about it. Correct? And the previous, this localities CNN lasted for so many years. And probably those transformers, and what do we expect to see more to encode this compositionality even better? Right. So I think we're not trying to get rid of the inductive bias. We're trying to find the right ones. That's number one. Number two, about Philip's question that says, what do we expect to change? So I think maybe in the robust video understanding workshop in 5 years, we're not going to see, maybe the output space is going to change. Maybe the output is not going to be, okay, object ID 1, and here is XYZ, and it goes to the left and so on, but it's going to be, okay, they seem to have just went to shopping. These people are getting out of the mall. There is one guy entering the car. Maybe we're going to have very, very rich label spaces. Maybe action recognition and tracking will be closer, so that because we do need these label spaces. And in fact, I mean, this is the hard thing in computer vision. We all know the input is the pixels, but we don't know what the output should be, because the output is built. I mean, for example, babies don't understand things like, I don't know, I go to work to make money. They understand he went to his mommy, because they understand about the missing mommy, right? So I think building rich label spaces and the understanding really what's happening, and pairing perception, like low-level perception, detection of objects, tracking the parts and so on, to cognition, what people say, right? To be able to do more inferences, maybe closer to language. I mean, language now has a little bit a negative connotation, but cognition, maybe we can say. I think maybe this is what we're going to see in 5 years. Or what do you guys think? So here I definitely agree. We are already talking on a higher level of abstraction than 5 years ago. So our concepts will evolve, and I fully agree. Also, the label spaces will evolve, and yeah, as you said, action recognition will be the next step for what comes after tracking. But at the same time, I'm also wondering, so I want to put this as a follow-up question, how close do you think we are to the limits of what we can learn statistically? Because at some point, the concepts that we want to infer are no longer really defined on a statistical sense, but they build more on other knowledge representations. And for action recognition, we're already hitting that limit where you can't have people perform a certain action or interaction 100 times for all actions that you care about. So at some point, we would need other forms of encoding that knowledge. Okay, a tiny comment on Bastian's comment. Maybe then we'll do what Judy said, that we'll say, oh, I'm really bad at
peeling garlic. Let me go to Amazon Mechanical Turk and ask them to give me, 1,000 garlic peeling videos, and also do some transcription and so on. And maybe we'll ask videos on demand on what to train, potentially.
I think to Bastian's comment, the main issue is that we don't know how to describe it, right? The issue is not the statistical aspect of the learning; it's that we don't know how to describe it. But I think there is actually, I think there is hope in the sense that if you look at kind of how zero-shot learning evolved in the last year with all these language models in the loop, where you can actually where you can replace all the nouns with just like this is an image of X in the CLIP model, for example, right? We were able to go away from these fixed concepts that maybe are limited to something that's a bit more open-ended. It's just an abstract feature vector, but we kept the statistical learning, right? We kept kind of the supervised learning paradigm. And so if we can do this for actions as well as just nouns, that would be nice. I don't think language will give us this, but I don't think it means that there is no way to still get this through statistical learning.
Well, you can think of language as a knowledge representation. Good language models have been trained on huge corpora of text.
Yeah, but the issue is we're not very good at describing actions, right? If I could act out something here, and you would not be able to explain me what I did in English language very well. The amount of expressive power I have in our language to describe kind of the causes and effects, or even the appearance of actions, is actually very limited, right?
I think that goes back to one of the criticism we have for deep learning for many people, right? Because deep learning, especially for self-supervised learning, people always say they are learning the correlation, not the causality. And that's why models are very good at finding shortcuts. Say, if you do action recognition, they will just classify based on the background most of the time. That's why optical flow, when you train models on that, just generalize a lot better than RGB when you have small data. But on the other hand, I think that relates to Phil's original previous kind of comments, say scale up. Because if you can scale up your model, correlation, if you have lots of cases, then correlation could lead to causality for most of the cases, although not all of them. But for some cases, definitely you can go towards causality, I think. And also causality is an active research community, I guess. And you do need to do active learning to break the link to check which is causal, which is right. That's what I understand.
I might push a little bit back on correlation and causality. I do think there's a difference between the two. And I don't think from just passive data we could learn causality. Now, I think the better question is, does it matter if we cannot learn causality for most of the applications that we'll have, right? Yeah.
Well, it depends. I mean, for some of them, maybe not non-security related, maybe it's okay. But some of cases, it's very related to safety. Then we do want to understand what's going on there, I think.
So let me just ask a real open-ended question and see if anybody bites. I want to know if anybody. So I'm real interested in having kind of maybe differences of opinion here. So I'm wondering if anybody has on the tip of their mind like a really controversial opinion that they think that other people in the panel would disagree with. It could be about computer vision, or it could be about anything really. But if anybody wants to jump on a controversial opinion, it could be about things we've talked about.
then I'd be really interested in seeing if anybody bites to that general open-ended question. I'll give it 10 seconds for people to think about it.
So I have one. I tend to ignore the domain difference between different domains unless it becomes a real big issue. And then I just switch domains. And now the question I have, I guess, is like, how much should we worry about our data domains, and how much should we just throw them all together?
I guess I'll answer that one. So my view is sort of both. I think that the two are not mutually exclusive. Like merging everything together, you should do that. If you have access to lots of data, you should create as strong and general purpose model as possible. But I guess the problem is that you're going to lose some specificity and some like specialization performance in the mix of doing that. And so you need the ability to still make the choice to adapt to a particular situation when you're in it. I guess the long-term challenge will be to be able to seamlessly switch between those two modes.
You disappointed me, Judy. I agree with that answer.
Yeah, what a great answer. I think what Judy is saying is that we need both to be generalist and to be able to jump domains, but also to be experts, to be really good at the particular domain, and that potentially humans also do the same, right? So we do have very general, and on things that we don't know we're slow, but we can still process them. But at the same time, we do become experts on things that we do often and so on. Yeah, that makes a lot of sense.
Oh, Tobias has a question. Go, Tobias.
Yeah, so before the discussion is over, I have one question for Weidi regarding your talk. You showed the video of the two golfing sequences, which showed actually the same move, but were different videos, right? And you said, okay, this is not good to have different feature vectors for this, so we are going to change our sampling scheme so that we won't have these two examples in the same batch. But I would argue that as a human, I can both tell that, okay, these two are different videos. These are different scenes, but they display the same action. So my question is, are we not really like a little bit oversimplifying the problem if we apply the same contrastive learning that is successful in images also to videos? So isn't the video data a little bit more complex in the sense that it can be the same sequence, it can be the same action, but it's a different sequence? What do you think? Can we apply the contrastive learning like we do in images also in videos, or do we really need a different representation, maybe related to the discussion that we had before on representations for video?
Well, like in my talk, I definitely mentioned the reason I'm interested in video is because there are so much signal we can play with. So a single task or a single representation is definitely not enough. And the reason we do that is really because the downstream task, like I said, is action recognition. So flow is the most distinguished feature or discriminative feature for action recognition. But if you do other tasks, then that's not the right thing to do. You can't use flow to pull two samples together. That's not right. And that's what I understood. But for videos, really, we are doing subdomains. Everybody is doing that. So for action recognition, that's the right thing to do. But for tracking, maybe that's not the right thing to do. Because for tracking, you want the instance to be separate. I mean, semantically, if two person, you still want them to be separate because that's two, identity. So it really depends on the downstream task. How do you do contrast learning and what to pull and what to push?
Would you think then? So, like for action recognition, okay, optical flow can be very good in determining that. But I mean, like you can also have changes in viewpoint, and then you have different optical flow. But essentially, like in the world frame, the motion of the scene flow of the scene is actually the same. So, do you think that we can learn like a unified representation that, like you said also in your talk, unifies the kind of like the appearance aspects, the motion in 2D and the 3D aspect of the scenes. So yeah, can we do this with the current vehicles of contrastive learning, or do we really need to dive into different representations here?
Well, I just mentioned a little bit. It's really, the computer vision task is so complex, and some of the tasks, they conflict themselves each other. Say tracking, and so one is semantic, one is instance. Semantic thing, you want two semantically two person to get together, but instance-wise tracking, you want them to be apart. So when you train the model, these two losses, they will contradict each other naturally, right? So if we want to train a big model, has to be at least several heads, and each head is responsible for one task. Right? But I can see it's definitely possible to train a huge model. That's also why, well, I'm super keen to scale the model up, but really it just needs compute.
So let me jump in with one, hopefully that will cause some discussion. So it might be a difficult question, but I think it's an important question, is that most of the time in this whole field, we're talking about how we can do things just better, how we can get better results, more useful. And has come to light more recently is that this can have, sometimes significant downsides to this. So there are risks, there are ethical concerns. So in some regards, as a researcher, it's easy to just ignore that and say, okay, we're doing the research. But the question is, the people of this panel are the top people in our field. So what would be the advice you would give, or the thoughts that you would have on how to approach thinking about the potential negative sides of computer vision, and maybe what we as a research community and as individuals might need to look into or think about? It's a very difficult question, so.
So this is a super difficult question. I myself have asked myself this question. I mean, for video and surveillance, we know that the Army is particularly keen on these applications. There are people that actually are so basically would have the courage to go to Canada exactly because they didn't want to be funded by the Army that much. It is, at least for me, it has been very difficult to give a good answer to this because, yeah, because the funding issue is not that easy to resolve otherwise. Do you see what I mean? If you decide not to, yeah, accept Army funding.
So I think there's, in my view, there's maybe two aspects of it. So what can we do? I mean, the bare minimum I really try to do is I just make sure that all the students I graduate are aware of the situation, right? And as a result, they choose certain places to work over others, not going into specifics. But that's kind of the bare minimum I think we can do, just make sure that they're aware. And like more to the point, like then it becomes like the hard spectrum is, should we take money from funding agencies that might use the technology in a way we don't want it to be used? And I think that's up to everybody's own thing. And like the other end of the spectrum is, should we stop doing research just because somebody uses tracking to track people, and kind of in a way that is not beneficial to those people? And I think that ship has already sailed. Like, this technology already exists, and I think we can maybe focus on other things that are less intrusive, like tracking objects, which is much better than tracking human beings, and that's already what's happening, and that's definitely something we can do. Can we reverse it? No, we cannot, right?
Awesome. Thank you very much for your answer. It's a difficult question that, but I think it's like you said, Philip. The minimum is that we can talk about it and be aware of it. And yeah, one of the big things in organizing a workshop was to say, you know, what are the ethical concerns of your workshop? And I mean, there are lots of ethical concerns in tracking. So I think it's important to talk about it as a community. Let me go with one final kind of round of questions. So there's 3 of you left in the panel. So Judy had to drop out. So we're going to start again with the talks at, so I guess I'm not going to say a time because different time zones, but in about 12 minutes. So go for one final round of questions. It doesn't have to be that long. We can have a break. But the last final round of questions is, what would be your top 1 or top 2 or top however long you want to talk piece of advice for someone, let's say in my position, someone who is a PhD student and wants to have a career like all of your careers so far? What would be, that ends it on a aspiring note? What would be the 1 or 2 or however many top pieces of advice that you would give to let's say to me?
I mean, I can start. Do whatever is most fun, and if you don't have fun doing it, don't do it. I think that's the general piece of advice, and everything else is sort of secondary. Like, I mean, if you go into an academic job, I know there's people that worry about tenure, and but I think you should still just do whatever is fun, because like, you should work on what excites you the most and what makes you happy, because if you don't, then like if the coin flip of tenure comes, you either wasted 6 years of your life on something that made you sad, or you had fun and it doesn't matter, right? And so, yeah, just do whatever you think is most fun and whatever you think kind of fulfills you the most.
So I see Sanya's arrived. We're actually wrapping up the panel session now, Sanya. We had one final question that maybe you can drop in and have an answer and share some wisdom with the audience, which was what would be your 1 piece of advice to someone that's a PhD student at the moment in the field of computer vision?
Yeah, I would just second Philip's advice, actually. You know, throughout career, I just had fun and it brought me quite far. So, you know, that would be my advice. Because if you can put your heart into it, which is typically associated with doing things that you're passionate about, then that's going to be rewarded. So don't worry about, having a lot of papers and be stressed about, funding and so many things. Just kind of do what you love, and I think things are going to come. Good things are going to happen. Now, for PhD students, I feel like, at least in my lab, I see oftentimes the younger students are worried about having a lot of publications. So it's more about, oh, I need to do, this many papers to graduate, this many papers to succeed. And I try to tell them that that's not the right metric, right? It's much better to actually do something for a longer time, even if you get scooped. Like, it's not, you almost never get scooped. You can always navigate. But release your work when you're ready, when you have done things that you're proud of, rather than just shooting papers out. So that would be my advice. Like get something out when you're really proud of.
Well, I guess I'm kind of the same position as Jonathan. So I'm really early researcher. So my advice maybe just from early researcher. So my experience was, I tend to do things that I don't know how to do it. I don't do things that I know I'm going to finish in 2 months, because there's a theory say, if you know how to do it, there will be thousands of people around the world. They all know how to do it. And if you compete with them, maybe someone from Google or Facebook from the industry, you just never win. So I tend to do things that I have no idea and spend some time to understand it. So that's why I like to explore different directions.
Yeah, great point from Wady. I also don't feel that I'm in a position to give advice. I think this is also a very difficult question. There are many people in the field that are fantastic, super hardworking, brilliant people, producing excellent work that beats every day the benchmarks. This is a very, very stressful, research environment to be in. So of course, doing what you like, not worrying too much about papers, trying problems that you cannot solve. This definitely puts you in a much riskier situation. But if you also don't worry too much if you manage to contribute or not, then you're going to be in a maybe better shape. Because in any case, you don't need to worry. The field is going to keep progressing. There are people around, so it's up to you to challenge yourself. So it's actually very personal journey here, right? That you do with yourself, because the field, no matter what, will progress.
Okay, awesome. So I think that's a good note to wrap up this panel session. So thank you to all the panelists, all the ones that are here in the chat at the moment, and all the ones that already had to leave. So I vote we take 4 minutes break, and then we start with Sanya since she's already here, and maybe we start 3 minutes earlier than scheduled, so we have more time for questions afterwards, because it's always good to have more time for questions. But let's take now a 3-minute break, because I already talked for a minute. And then Sanya's going to have an invited talk, and then Katrina is going to have an invited talk after that, and then we'll wrap up this workshop for today. So extremely excited for the last 2 invited talks, and we'll be back here in about 2 minutes after having a breath after that panel session. Okay, Sanya, do you want to see if you can share your screen if you're ready? So while you're doing that, I'll introduce you. So for our 7th keynote invited talk for the day, so our second to last one now for the day. So we have about an hour, a bit over an hour left of the workshop. I'm honored to introduce Sanya Fiedler, professor at the University of Toronto, and also working for NVIDIA. And she's going to be talking about neural simulation. So I wanted somebody to talk about the use of simulation for video understanding, and that was my thought of something that would be super interesting for the audience. And Sanya was the person that came to mind as the person with, that would be the most interesting to hear talk about that. So I'm very excited for your talk, and take it away.
Thanks, Jonathan. Thanks for inviting me to this workshop. Just to confirm, I have 20 minutes, right? Or a little bit more?
Yeah, so there's 30 minutes total. So if you go longer, there'll be less questions. So
I think I'm going to go shorter. I don't have so much to show about video, so I'm going to mainly talk about one project. All right, cool. Maybe I can start. Yeah, so I'm not going to really talk about simulation for video understanding. I'm going to talk about some new way of simulating, maybe. All right, let me start. So at NVIDIA, half of my time I spend at NVIDIA. The vision for the future is really in 3D, right? So the vision is that anything that is built will be visualized, and anything that moves will someday be autonomous. And anything autonomous will be, or maybe even needs to be, simulated, right? Before it's deployed, you need to test it in simulation before it can be deployed to the real world. So there is really a need for large-scale simulation that is both, physically accurate, can model all sorts of different sensors, including cameras, and can scale to really complex virtual worlds. And for this, NVIDIA has been building this visualization and simulation platform called Omniverse, which is really cool, actually. So it connects different 3D modeling softwares, for example, Blender, Maya, Unreal Engine. So any of this existing 3D modeling software can be plugged into this Omniverse as a connector and allows you to visualize that scene in this Omniverse scene. And so it just basically enables different people, even if they're in different parts of the world, they're using different modeling software to simultaneously edit the same scene and visualize everything real time, including real-time physics and so on. And it enables also to plug in tech. For example, if you have a new physics algorithm, your rendering algorithm, or if you have AI. So really a lot of my papers are kind of plugging our AI very easily into Omniverse as Python interface and demoing there. It's out there. So you guys, I really invite you to actually try it out. It's open beta is out. So you can imagine that this platform is super important for many different fields. And one of them is robotics. All right. So yes, it can be used for entertainment, architecture, and so on. But it's super important for simulating for robotics. So here I'm showing NVIDIA's Drive Sim, which has been revealed by Jensen a month ago at GTC, the latest version. So everything you see here, it's basically rendered in front of your eyes. It's all photorealistic, all the physics, lighting, everything is computed real time, which means that for the ego car, the simulated world, the real world are virtually the same. The sensor data is coming in at the same speed. And there's a lot of effort put into creating all these environments. And really nice thing about simulation is that it's super controllable, right? You have all the control you want over what kind of environment you're going to test your vehicle against, how many cars or other dynamic vehicles you're going to put on the road, weather, traffic signs. You basically have control over the scenarios. And really kind of one major effort here was on Omniverse, which supports this really high-end simulation of cameras. So you can have here, I think we're just gonna show it right now. So it's not just the ego camera, but you can simulate also other sensors like fisheye cameras and so on. So to me, this looks really realistic. So I'm super excited about this gigantic project. It's really a culmination of technology and art, in my opinion. So in my research lab in NVIDIA, we have been kind of working on 3D content creation that's going to power Omniverse and simulation in some ways, right? If you think about Omniverse, it's or even just Drive Sim, it's rendering is made super fast, but content creation is still the bottleneck. So how can you actually build AI tools that can make content creation and simulation much faster? Okay, so that means building up different scenes, assets, and maybe tools for editing them efficiently. And of course, for simulation, you also need to consider time, which means that we're also working on behavior models. So how can you actually train traffic models that are going to look realistic, as well as animation? So how can you drive characters around and animate them in realistic ways? And pretty much all this 3D technology that is common to all our projects is deployed in Kowloon SDK, which also links into Omniverse, has a nice visualizer of synthetic data generation that you can use, and it's all open source. Cool. But today I'm going to talk a bit about a different way of simulating, which is kind of like a moonshot project we're doing on the side, let's say. And we're going to focus on driving as a use case, right? So in driving, it's very easy to collect data, right? You just put your car on the road and, even in a single week, one car can collect over 160 hours of data, let alone if you have a fleet, right? This is like tens of thousands of hours you can be collecting, right? So the question is, can we learn how to simulate by just watching videos? Or let's say ego car making actions and then receiving videos as a result of that. So can we do neural simulation, meaning can we learn a graphics simulator directly from pixels? All right, so a year ago, we had this project called GameGAN, where there's a nice analogy with games, right? So how are games built? So there's some sort of a user control. The user can make different actions. And then there's a game engine that essentially computes the next state, takes this action, right? So it computes the next state, and then paints or renders the next frame. Okay. So what we're going to try to do is something similar, but imitate what a game engine does with a neural network. So we still want the human to be the one in control. So it's going to provide actions. And then the game engine is going to be imitated or consumed by a neural network. Here we call that GameGAN. And then this neural network is going to paint the next frame as a response to the user's action. Okay, so this can be used for many different ways, right? So you can think of this basically consuming a game that is operating system independent. You can just use it anywhere, right? You can think of it as compressing the entire game into these weights of this neural network. But really where the exciting part is when there is no game engine, right? If I'm looking at Pac-Man, I already have a game. Why do I need to simulate it? So really, when you go to the real world where we don't have access to the game engine, we don't have access to the matrix that drives the real world, maybe it's something like this can actually help us recover it. All right, so here was our initial take on this. So this is GameGAN, where the design is as follows. So you have these dynamic engines, which essentially at each time step receives an action from the user, encoded action. There is some noise that is fed into the dynamics engine, and there's an image from the previous time step. And all this is fed to the dynamics engine, producing the next hidden state. And then there's some sort of a rendering neural network that produces an image. And we also have this like memory module over here where it's trying to, the neural network is trying to push here some sort of a memory about the environment. For example, if I'm in some sort of a maze, I might want to remember what I have already painted in my previous time steps, such that if the user wants to return to that same place, then maybe the spatial memory has that information encoded inside. And of course, it's very important to have this noise here. So we want to model distribution of the game because there's stochasticity associated, right? There's more than one possible future going forward. And we want to basically train this as a stochastic, so a generative model. Okay. So how is this trained? Well, similar to regular GAN. So this has kind of a GAN architecture. So we have like a single frame discriminator that tries to tell that each painted frame looks realistic. A temporal discriminator that takes several frames and makes sure that they're all realistic. And of course, we want to make sure that action is actually taken into account. So we have a very simple action condition discriminator that takes, two different images and tries to predict back the action. So you're forcing these images to actually conform to that action that way. And of course, the question is, how do you train this? Well, you could have humans just play hours and hours of the game, but we essentially train an RL agent that learns how to play the game. So for example, a Pac-Man, we will have an RL agent like a DQM policy that tries to learn to play the game. And it was actually very important to collect trajectories from all stages of training, meaning even when the policy is bad, those are actually good examples from our GAN, because we want to make sure that we can cover all the possible states that this game engine can end up with. So we collected around 50,000 trajectories, and that was basically our target data for training. Here is an example of the results on Pac-Man. This is like Ego Pac-Man. I think Berkeley released a simulator in the game, so we try to encode it. Just kind of pay attention to how consistent the world is when it's painted. It's not 100%, but it's quite good. So the model has learned that the Pac-Man, if the Pac-Man eats the food, then the food needs to disappear, and that it cannot exit the maze. And there's also quite some large consistency in the actual generated maze. Cool. What you see in the end is kind of the romantic picture. It's the end product of this project. It wasn't like that during the development. So I just wanted to kind of share how things were during the development. So this was kind of one of our first results. And you can see that the maze was looking relatively good, although it was not super consistent. But what turned out is it was super hard to generate a ghost. All right, because Pac-Man is always in the middle of the frame here, so that was easy for the model to capture, but the ghost was kind of randomly placed and randomly appearing. And then we had to design this multi-scale discriminator and so on, and then suddenly the ghost appeared. Here is another example with a much smaller environment where we were debugging. And what you're gonna see here is that it was super hard to learn that Pac-Man has to die, which means that if it crashes with this red ghost, it should die. And it was almost impossible to make Pac-Man die. Why? Because most of the time, like only at the end of the trajectory, Pac-Man actually dies. And that's a very sparse event that is very hard to get, actually. We still haven't solved this fully, actually. All right, great. So then for the 40th anniversary of Pac-Man, and this was released, let me just show this nice video here. So this was on the original Pac-Man. You can see that the Pac-Man actually learned how to eat all the food. And the blue ghosts, if you eat them, disappear, and that ghosts change color. And that ghosts disappear if you eat them, which is a lot harder than you think. All right, great. And then I saw this video put online a week ago, actually, just 7 days ago, where someone took the code of GameGAN and trained it on Grand Theft Auto. So let me just play this because I thought it was pretty cool.
Welcome everybody to GAN Theft Auto. What you see here is me playing inside of a neural network's environment. This neural network was trained by watching a bot play Grand Theft Auto 5 on this particular stretch of highway, learning how to generate new frames from previous frames and player input. So every pixel you see here is generated from a neural network while I play. While generating the visuals or just improving them is interesting too, and there has been some interesting work lately with neural networks improving the visuals with Grand Theft Auto 5, in particular in attempts to make it look more photorealistic. This is something much more than that. The neural network in this case is the entire game. It's handling what happens when you press a key to turn left or right. There are no rules written here by us or the original Grand Theft Auto engine. The neural network is controlling all of this, along with what happens when we try to turn into another car, when we hit a wall, or what objects in the background should do, what the light reflection should do. It's doing all of...
I'm gonna stop it here. But It's amazing. In 7 days, this got over 550,000 views, and it's kind of nice to see someone else promoting your work. I wish my work would my videos would have so much take up, but this is very simple. It actually, the quality doesn't look so great, but there has been such amazing reception of this. And of course, as a researcher, I immediately start thinking, how can we actually improve this, right? This is still very blurry, and maybe we can make this better. So coincidentally, we have actually been working on the next version of GameGAN called DriveGAN, which is specifically tailoring simulation for driving. So learning from just driving data. Here, what I'm showing you is kind of the end result trained on Carla. So again, the user is controlling the wheel and the speed, and then the frames are being painted by neural net. So here is a train on Carla without any other agents in the environment, just for sanity checking. And here is if you actually train with many agents in the environment, which is a lot harder, but it's still able to capture some of these dynamics of other agents and their behaviors. Cool. So, the goal for this project for DriveGAN was really, we want to have a driving control, pretty much the same as a real car. So you want to have a wheel and a speed command. We want to have, again, our DriveGAN to synthesize these views. But as a graphics simulator, we want to also have interactivity. So some control over the environment. Neural control, we're going to call it here. So we want the person being able to control maybe the weather or some sort of a global properties of the scene that we are driving in, as well as maybe local structure, like the kind of vehicles or trees or things that should appear in the scene. So that was kind of the goal of this project. So we redesigned the GameGAN architecture a little bit. So first thing we tossed was the memory module, because maybe you don't really need to remember here the road you have already painted. And we wanted to explore more complicated architecture, so kind of take advantage of the state-of-the-art generative networks such as StyleGAN. So here, for this image generator, we want to exploit something like a StyleGAN. And one real maybe challenge for training this on driving data, there's just so much of it, right? There's thousands of hours that we could be training on. In our case, we're going to train this on 100 hours. So training this entire model on so much data would just be like super challenging. We didn't even attempt it. So what we wanted to do is somehow disentangle training of dynamics and then encoding and decoding of images. So what we want to do here is pre-train a network that is able to encode an image into some sort of a latent space. And then a generator here on the right is able to take that latent code and decode it back into the original frame. And while we're going to train the dynamics engine, we're going to keep this part frozen. So we're going to keep these latent codes frozen. And then the dynamics engine is only going to learn the transition dynamics in this latent space, which is a much easier task. Okay, so here on the right side for the image generator, we're going to exploit essentially a StyleGAN architecture with some minor changes. So instead of here being this content code being flat, we're going to make it spatial, which really improved the quality of the scene because it's a very complicated scene. So this helped it actually paint a more complicated scene than just faces and cars that the typical StyleGAN was generating. And we're going to train this as a VAE GAN, meaning that we want to jointly train both the encoder and decoder, right, with VAE and as well as the GAN kind of losses. And that turned out to be very critical. If we only train the StyleGAN as is and then try to train an encoder, we just couldn't get a very good quality over here for encoding images. So it's kind of very critical to train it as a VAE GAN. So let me just kind of paint the problem over here. So here on the right side are the original images, and here on the left, we're trying to encode those images, just static images over here. So I want to map each individual image into this kind of latent space or StyleGAN latent space, such that my generator can synthesize it back into the image that looks like the original image. And yeah, and that turned out to be quite a lot harder than we thought. So for example, the main object is always synthesized relatively well, although even here on the right, you see that even that is not working very well. but it almost never pays attention to other vehicles. Like it just deletes them. I know even the houses here, if you look at this house and this house over here, was very kind of blurry and not well reconstructed. Okay, so our thinking was that maybe this is because Stalgen has this like 1D latent code structure. So we turned this into a spatial latent code and really trained this as a VA again, and that improved the quality a lot. So here I'm showing a video, but essentially this is just encoding frame by frame in this latent space. So you can see that now you started recovering these other objects that can appear in the scene. So here is encoding real driving frames. And it's kind of interesting. So this is the input that we're trying to reconstruct. And these are reconstructed images by mapping in this latent space. And you can see the semantics is kind of preserved. Like I do get this car here and this building over here, but actually we are constructing an entirely different car. Right here is the same story. So it's kind of interesting that this generative models actually encode the semantics, but getting this perfect pixel reconstruction is a little bit hard. Here is one more example. Cool. And then in the model, we have this disentanglement into content code and theme code. So content code is the spatial latent code. So we're thinking that this is actually controlling where the vehicles and the buildings and so on are going to be. And the theme code is just a 1D code that we're using here in ADA, so in adaptive instance normalization layers, as kind of like a style vector, if you will. So it may be controlling weather and background and so on. So here I'm just showing like basically different sampled theme vectors. So this should be controlling the style of the scene and was trained completely unsupervised by just having this kind of inductive bias in the architecture. So you can see that you get these different weather conditions, even night versus day control. And here is playing with the content vector, and essentially what you're doing, because you have this spatial latent code, you can take one block, so one spatial block from some other frames that you have encountered and paste it into the desired location. So for example, over here, where this finger over here was clicked on this particular node, you replace it with some building latent code you have found maybe in another video. And then this is basically painting this building in this frame. Here I'm deleting maybe this trees here. I'm removing this tree, and here I'm painting another tree. So let me just show you how this works in practice. So here I'm making one car appear, and here is changing the weather, which is cool. This is the kind of control you want to have. Obviously, the quality is not yet there, but we are just in the beginning of discovering this line of work. This is gonna just show a longer roller, just so you have a sense of how well or not well this is working. So there's a lot of flickering, and I think this was because we downsampled the videos temporally, so the GAN had a trouble kind of learning the dynamics. That was just for efficiency reasons. And the road, I feel the road and the sky and the trees are actually painted quite well, but the cars are kind of choppy. They keep appearing and disappearing and maybe changing the type of vehicle is being painted. It's kind of fun to watch. Cool. These are some funny errors. So look at this bridge over here. Basically, the GAN gets stuck in this time hole, so it keeps generating that same bridge. I'm not really sure what happened here. And here we're again with that same bridge, and it just cannot get out from this bridge. And here it is again. And then finally we get rid of the bridge. All right. There's other funny effects, which obviously are expected maybe, but I'm not yet sure how to solve. So, I'm inviting everyone to work on this problem. So here is what you need to pay attention to before I play the video. So look at the driving controls. And what you're gonna see is that Seng, so the first author here, is gonna try to drive away from the lane. So he's gonna try to go here on the left, make an illegal maneuver essentially. Maybe park on this grass here on the left. Okay, and you're gonna see that DriveGAN doesn't allow him to do that, because what it has learned is wrong causality. If you wanna go on the left, if you're on this left lane, then the road has to change, because that's the examples it has seen. It has not seen illegal maneuvers. So every time someone was going to the left or the right, it was because the road was actually changing. And this is basically what it's trying to do. So let's play this. So here he is making a sharp left, and it takes a while, but then basically DriveGAN paints the road instead of actually making that illegal maneuver. So he's trying to turn to the right, and it was the same story. And that really kind of poses the question, right? Like, how do you solve this problem? If you have never seen certain illegal maneuvers, then obviously you cannot recover them. And there's a lot of kind of wrong causality this model has run just because it has seen only nicely behaved videos, right? So maybe one way to go in to solve this problem in the future is kind of bringing in graphics simulator where you can be crashing as much as you want and kind of have this GAN learn from both types of data. But maybe there's other ways. Here is the results on Gibson environment. So this is basically indoors. It's a driving wheel, but it's just left and right commands. So there's quite a lot of 3D consistency, actually. It's a bit blurry, but it's a lot of 3D consistency. And some comparison with other works. So, Action RNN is typically producing very blurry results. World model is not very consistent. It keeps flickering here with these different cars. GameGAN is not as sharp. So here we get a lot sharper results just because we're using better architectures. So here's some comparisons on the indoor environment on Gibson. You can see that we get a lot sharper results. And then on the real data. And basically what we're doing is we're giving it 1 or 2 frames, like sample from real data, and then we're asking all the models to continue into the future. So look at, in the ground truth, look at the bridge, because that was basically fed into the model, right? There's a bridge here, and almost none of the models, except for ours, is able to recover that bridge and kind of continue the video from there. And how do you evaluate this model? Well, there's not really much you can do except for human evaluation. So here we were asking people, which model has better visual quality and which model has better action consistency. And everything you see orange means that DriveGAN was winning. So we actually beat everyone else by quite a lot. Another thing that was particularly exciting for me for this type of work, and I'm going to finish after this, is resimulation. Right, so for robotics tasks, particularly for safety critical applications such as driving, if you have recorded some sort of an incident, some intervention, you want to retest your vehicle again to the future at that same exact scenario, right? Which means these days, someone will need to go and recreate that in 3D in a graphics simulator, right? And then you can go again and retest your vehicle in that scenario. So basically the desiderata is, if I have recorded some real video, I want to drive again into that environment, that scenario, but maybe taking different actions just to see if now I can actually handle that scenario. And the cool part about DriveGAN is a differentiable module of interactive world actually, which means that if I have some real video that I have recorded, I can actually go back and optimize the world parameters, right? I can just have a loss over here, and I can optimize both the actions that were taken as well as the content and theme codes over here, such that I can reproduce this particular video, right? And once everything is encoded here in my content codes, then maybe now I can do is redrive again by taking different actions. So here are some examples. On the left side, we had a ground truth sequence. Here is a reproduce scenario. So basically, we optimize actions and noise. Here is another example. Kind of pay attention both to inferred actions as well as the reproduced frames. One thing that we keep seeing is that the semantics is matched, but you're not able to reconstruct that exact car. So for example, here, the real video had this red car and we keep reconstructing some other car. Not sure exactly why that's happening. It's hard, I guess. Here is another example. Here, the inferred actions weren't actually that great, but the video is reconstructed quite well. And here is that same optimized video. And we're going to take a different actions where we're going to play the drive again. Okay. In particular, when this ego car is going to go again to the left, and then we're going to slow down. So just kind of pay attention to us slowing down while we are on the left. So here we're slowing down. So in real world, we're going to overtake, but then in slow down version, we are not, because the drive again is actually able to simulate that slowing down action quite well. I think I'm gonna skip this because we don't have time, and just kind of gonna show this, which is what we're working on right now. So we had this one more paper at CVPR that's basically showing that GANs are really good self-supervised learners. And if you just go and label a couple of frames that they're producing, then the features that are used to produce those frames are really good to like you don't need a lot of label data to actually generalize across the latent space across different generated scenes. So we're kind of applying the same idea now, but to drive GAN. So drive GAN meets dataset GAN. You generate a couple of frames, you're going to label them, and then we're going to train this label branch that's producing not only the image, but also the labeling, the semantic segmentation. So these are really early results that we're just getting now. But you can see that, by just having a couple of labeled frames, it's actually able to produce not just the image, but also quite accurate semantic segmentation in this case. And we're thinking that once we improve the quality of this GAN, both temporally and spatially, then maybe this is going to be even better. Cool. And that's basically brings me to my conclusion. Maybe a promising, exciting work is just simulating directly from pixels, so from pixels to pixels, which can be used for different things like model-based ORL, also for differentiable simulation. And there's a lot of questions we need to answer, not just in terms of quality, but also how do we simulate these more harder cases that we have never recorded. And that concludes my talk. Thank you.
Awesome. Thank you very much. That was fascinating. If anybody has questions, we don't have too much time. Okay, Katarina has a question. So.
Yes, thank you very much for allowing me to ask the question. So Sanya, here is a question I have forgotten to ask you. You have this beautiful dataset GAN where the human labels the generated images. And then you have this other paper that says we have real images labeled and we train a GAN to actually spit out both the image and the label. How would you, both of them are doing semi-supervised learning, okay? How would you compare these two approaches? It seems that one is working better than the other.
Wait, which one do you mean? Because in dataset again, you're training the labeling branch and you're just synthesizing a large data set, right?
Right. So the other paper you have in CVPR is this semi-supervised out of distribution. You remember?
Oh, yeah. So there's two different ways. So we basically had the same idea, which was GANs are really good representation learners, but there's different scenarios you want to tackle. In the first scenario, we were saying, let's just annotate what the GAN is able to generate. If it's not able to generate something, there's no hope we can teach it, right? And that was the dataset GAN paper, where basically we generate images, we label them, you train your label branch, and now we have this data generator that you can use for training any downstream network, right? The other paper was, well, what if I already have a large label data set? I want to be able to also use that, right? And there we went through the route of having an encoder. So if you can actually take an image, an input or a real image, and train an encoder, it goes back to the latent space, then you can do something similar to the dataset GAN by actually also leveraging the real annotated data.
Right. I thought that this is way more practical because then you don't need to label generated images, and we already have tons of real images annotated. So does this work better, or you think labeling the generated images works better?
They're trade-offs. So the other model needs more labeled data just because you need to train also the label branch with a discriminator. So in the low data regime, this model, dataset GAN model, is actually a lot better, but the other one catches up when you have a lot of data, right?
Yeah.
I think the real answer is in both of them. So I think you want to use the encoder to actually go and use the label data you already have, right? But the nice thing about synthesizing a data set is that now I don't need to use my GAN at test time. I can just train a transformer or whatever heavy architecture I have on the synthesized data set.
Right.
So I think it's a little bit of mix and match, but I'm excited about, all of these options, I guess.
Thank you so much.
Super cool. So I think that's the time we have for questions. I'm sure I could ask questions for the next hour, but in the interest of finishing when we said we'd finish, I probably shouldn't. So thanks again to Sanya for giving that amazing talk. So now we move on to the last talk of the day, and also super excited for this one. So Katerina Frakiadaki is going to be talking about, I guess, 3D scene representations for visual tracking. And I've seen some of her work recently and it's blown my mind. So I'm very excited to hear you talk about this. So without further ado, I'm going to hand over to you for your talk.
Yes, thank you so much for your kind invitation and for this great workshop. I have thoroughly enjoyed it. This talk links to some comments during the panel about 3D representations. And is, I would say, complementary to the other talks. So here is the main problem. We wanted to add permanence. Or how do we add object permanence to visual representations? So why we need the permanence? Because here you see that what the observations gives us is very, very partial view of the reality. There is no model completion. This is just the raw image observations. We know that when we people track this human and his head and his hands, we don't consider them as surfaces. We also consider what's behind them. So how do we get machine learning models to have the same understanding about the scene? So you may say SLAM does that. SLAM goes around the scene and builds a map, builds these point cloud maps, separates, given a video, the camera motion and the point cloud map, distills the scene appearance into a point cloud map. The problem is that whatever you see here, the camera has gone around and has seen it. What if next time you go to a very similar scene and you want to just by imagination paint the content the same way that people can do it at test time from a single image? SLAM doesn't do that, okay? So a model completion, we need to go beyond the SLAM architectures. We'll get inspired by SLAM, but couple them with the learning machinery. We need to be learning. We need to be essentially remembering how this scene got completed to be able to complete similar scenes and hopefully to be able to complete all those scenes outside of the distribution. There are fantastic recent works on 3D representations. Here is, some of my favorites and your favorites probably. We have nerves that can, if you give them lots of views on a particular scene, they can relight it and shows different views. These are object-centric methods that, given lots of 2D images, they build approximate 3D models of that object, dot object category, and so on. So all these rendering, pipelines, they care a lot about, graphics. How do you make photorealistic images? But similar to the previous talk, what is important is actually the semantics, the correspondences, the feature representations that you learn through rendering. So the questions we asked is, can we use such, encode and decode by rendering architecture to actually learn good visual representations, mostly self-supervised by moving around in the world? And can we build in on those architectures a model completion, so that what the network thinks in its heart is not only what it sees, but also what's behind. Here is Rodney Brooks, that he said early on that we actually do not need accurate 3D reconstructions for moving around in the world. So basically what he's saying is the representations that graphics architectures need, or that graphics applications need, may be different than the representations that artificial agents need. So that is true for the human brain. For sure, human brains don't care to, render every little place. Now, I mean, following on Sanya's, line of work, I think it does make sense to use AI to build better simulators and use the simulators to train your model in practical, applications like self-driving cars, where actually for safety concerns, we cannot interact in the world. And we have not figured out ways to teach our machines the way we teach humans through natural language and so on and so forth. One compromise that we have found between not building beautiful photorealistic, it is hard actually to build photorealistic simulation of the real world, but at the same time being able to complete and imagine beyond your current observation. So here is an observation. For you, it means a lot. For the machine, it's just a 2D surface. And we actually use, in our last at least year and a half, have been using these representations, 3D feature maps, which are essentially 3-dimensional grids, have 3 spatial dimensions, and at every grid cell, there is a feature vector that represents the geometry and the semantics of the scene. So these 3D feature maps is essentially the hidden state of our recurrent networks. So we call those networks geometry-aware RNNs. They have 2 main differences with previous recurrent networks. The first is the hidden state is not either 1-dimensional or 2-dimensional. It is actually 3-dimensional. And the second is the way this hidden state is updated. It's updated similar to SLAM methods. We'll be estimating ego motion and using it to transform features to aggregate them into that 3D feature map. So just to give you visually how the network works, here is an image sequence from a scene. And here you unprojected feed this into an encoder that takes the pixels and put them in a shell, in a 2D shell based on their depth values. If you don't have depth available, then you need to shoot that pixel all along the ray. And then there's going to be 3D convolutions that densify essentially this representation and go from the 2D cell to the a modally completed, let's say, 3D feature map of the scene. And when the next frame comes, again, the same encoder will be used, and you will be computing your 3D rotation and translation, ego motion, just like SLAM, and you'll use this estimate to actually transform the features and fuse them into your 3D feature map. And the same thing for the third frame. And what you manage to do is to create an explicit, stable 3D model of the world in your neural bottleneck in the heart of your network. So despite the fact that that point on the handle of the coffee machine actually changes XY pixel location after this transformation is placed exactly at the same point in the 3D feature map. Okay, so your 3D feature map is actually disentangled, separated from camera motion using explicit 3D inductive biases. So yes, so in contrast to the RNNs, what 2D RNNs would do will use convolutions, and essentially your hidden state will be contaminated by the camera motion. Now, important question is, can we use transformer architectures to actually learn those 3D inductive biases? For sure, building explicit 3D inductive biases helps over convolutional architectures that have those locality priors. But what about attention architectures? These are things that we're looking into right now, and I don't have answers to give today. So this is just the architecture. Is a network that takes 2D images of the world and builds these 3D feature maps. The question is, how do we train it? We will train it assuming that we have an agent that can move around in a scene and is trying to predict what it sees. For example, it says, what am I going to see if I move, if I translate and rotate that amount? Then he will, carry out a prediction. He will move there, will see the actual ground truth view, and so it's going to given that it's not the viewpoint of that query view, is going to transform its 3D feature map and neurally render it to spit out an image, and will compute a loss. Okay, and that loss is just a pixel-wise Euclidean distance, which we know is pretty bad loss to compute to be predicting images, but we will fix it in a little bit. Of course, you can also put an adversarial loss, but you know, you'll see that by adding contrastive losses, we actually learned feature representations that work better than image prediction. Now, what is the benefit of this explicit 3D representation? Somehow you get dramatic generalization in very dissimilar scenes. So here we can train our method on 2 objects, and we'll show that if you apply it on 4 objects, exactly because you don't go through tight 1D feature vectors or 2D, you know, or 2D feature maps, somehow, you know, you are able to generalize. So if you ask the network, to tell you how would this scene look from all around, and then you render the different viewpoints and you make a video, and this is exactly what I'm showing you, you'll see that this network, in comparison to a 2D network or a network that has 2D bottleneck or 1D bottleneck, has much better generalization. So we'll try to find alternative inductive bias to get this, you know, great out of distribution generalization without going through 3D feature maps, that we haven't been able to do that yet. But definitely this workshop has been very inspiring, and I really liked Philip's comment that, you know, the latent representation from a video should be variable, and you know, now that you have 4 different objects, better be 4 different vectors, and if you have 2, it should be 2. While here, our bottleneck is always the same. It just is a full 3D scene. All right, so being a full 3D scene, it can fit both when you have 2 objects as well as we have 3, 4, 16, without actually interference between them. But at the same time, okay, there's a huge memory consumption here, which we're gonna see in a bit how we can resolve. But at the same time, makes things hard when there are deformations and so on in dynamic scenes. So whatever I'm showing here is about static scenes and moving agents, you know, going around that static scene. So here is another loss that we tried. I mean, we tried the previous loss in a photorealistic environment in Carla, and actually it didn't work very well. And the reason is that you can never predict how a scene will look from a different viewpoint. By the way, at test time, even from a single view, you should be able to predict the full 3D feature map of your scene, right? So there is a lot of stochasticity and uncertainty that a deterministic model does not account for. One way to get around that is by using contrastive losses. So instead of trying to match pixels, you ask your network to predict a 3D feature map of that query viewpoint. And in pixel-wise, you correlate it with a feature map predicted from a concurrently trained 2D convolutional network that operates on the query viewpoint. So everything is trained from scratch. And you're trying to predict the 2D feature map you'll see from a query viewpoint. Okay, so this is much like contrastive predictive coding did, but by going through this 3D aware, let's say, architecture and geometry aware architecture. And you can do the same thing in 2D, or you can stay in 3D and do your contrastive prediction in the full 3D feature volume. In this case, the query viewpoint needs to be encoded into a full 3D map of the scene. So it looks something like that. You have your 2 feature maps, the one you predict and the one infer from the query viewpoint. And for every grid cell, for the corresponding grid cells in the same IJK location, you need to say, okay, these are positive examples and these are negative examples, and then you minimize the standard contrastive, you know, loss. And now if I take the inferred 3D feature maps and I slice them and I see them from an overhead camera, you'll see that the different objects are detected. And now I'm showing the same architecture on dynamic scene while it could only be trained on static scenes with a moving camera. So here the scene is dynamic because they're also moving objects. And you can use these features to actually track objects over time without ever seeing a dynamic video. Now you may say, what else can you do with your 3D feature map? Well, you are supposed to be doing whatever you would do from your 2D image, for example, detect objects. And the good thing about this 3D feature map is that as you move around in the scene, you actually have permanence. Objects will not disappear for your 3D feature map in the same way that objects don't disappear from the point cloud map of Slum. So if you run your 3D detector on that map, you will detect also objects that you saw in previous frames, but are missing from the current frame. So to train a detector, you need to be supervised. You need to have some small amount of training data of bounding boxes and labels paired with your images. And what we show here is that if you have a contrastive pre-training, because you actually, to train your model, you actually don't need to have any annotations, you just move around, then you will do much better than if you train from scratch, of course, but also better than if you just predict images. And I'm very excited about this data SEGAN approach that shows that, if you have the correct machinery, predicting images basically allows semantics to emerge. I think this is very interesting direction that we're also trying to look into. So one problem with the 3D feature maps is resolution. But recently, the last 2 years, we have seen a fantastic progress with implicit functions. Implicit functions essentially allow you to get features in an infinite resolution. So instead of actually having a feature grid with features, we're going to have a feature grid with implicit functions. We're not going to have a single implicit function because if, again, you go from a very tight bottleneck, you're going to lose this generalization that I showed earlier, that you can actually run your method in dramatically different scenes and still generalize. So what we're going to do is we're going to instantiate these functions that take as input the feature vector at every grid location, ijk, and a displacement from, let's say, the grid center. And they're going to have some trainable parameters. And they're going to map now this displacement, which instantiates essentially a point on the continuous 3D space to a feature vector, as well as to occupancy value, 0 or 1. And of course, the standard way to get a feature vector from a continuous 3D XYZ coordinate is to do trilinear interpolation. And this is what we've been doing so far. And now we show that if you train implicit functions, you actually can get dramatically more accurate features. Okay. Now, other than that, our architecture is going to stay exactly the same. It's just that now we have added implicit functions into our feature volumes. So, so basically here you can see we call this model COCO-nets from continuous contrastive networks. Continuous because of these implicit functions and contrastive because of the contrastive, also 3D. And you see that here we compute the tracking accuracy. We use this to track objects from frame to frame without imposing a locality around the local window. And you see that we're doing dramatically better than voxel features, but also better than this very strong baseline called 3D point contrast, which actually assumes that you do have views and you use triangulation to obtain supervision by saying that these two features are actually projection of the same 3D physical point, so you should put their feature embeddings close. Okay? So COCO-nets that actually impedes and modally, completes the scene is able to do better than this. And also it works well if you use it as a pre-training for a 3D object detector, a little bit more advanced than Mascar-CNN, like VOTnet from Leo Gibas's group. And of course, if you can apply it also object-centric and get great shapes out, very good generalization and so on across few points, even from a single image and so on. But you can also use it to track exactly like before. Sorry, these videos apparently don't start together. So yellow is the ground truth and blue is our predictions. And again, I mean, this tracking, by the way, is frame by frame, so it cannot survive occlusions. But again, what we see is that, you can track better than before, but without ever trained on a dynamic video. Okay. So these are different videos from Kitty. So in summary, what we said is that by moving around, by having edges moving around, they can learn a model 3D representations of the scene just by predicting different viewpoints, okay? And the test time from even a single image, you can actually get this, persistent 3D feature map, a model complete, so beyond your observations. And the second thing we said is that those features that you learn are actually also useful for tracking, and for tracking actually objects in 3D, because you're using 3D feature maps over time without having seen dynamic videos or whatever, without ever using, tracking supervision. So the papers that I mentioned are here, and Fish, Adam, Mihir, and Shamit are the main students behind this work. Thank you very much for your attention, and I look forward to your questions. Thank you.
Awesome. Thank you very much, Katerina. So I find this work to be extremely exciting. So this is a topic that I'm very interested in, kind of going into 3D and going to self-supervised for 3D. So I hope other people have some questions, but I can start until somebody asks some questions. So my first question is, so with this representation in 3D, I can think of two ways to train it, and I think in your paper you've done both, which is one is with the contrastive loss and one is with the novel view synthesis loss, the actual generative loss on like the scene from a different angle. So what are the kind of trade-offs and benefits from using those, and can you get more benefit from using both versus just one?
Yeah. So let me tell you, in both cases, we're predicting the next frame. Do you agree? But in one case, we are matching pixel values, and in the second case, we're matching features, correct?
Exactly.
But when we use the contrastive loss, we always also use the pixel prediction. It's just but because it trains faster, okay? So for pixel loss, if you want to use it, then you need to take care of the uncertainty. So we did try to augment this with the VAE, but because the uncertainty actually doesn't sit in the whole scene, different components of the scene may move differently. It's very hard to, model uncertainty in the whole scene level, if that makes sense. Okay, so if you don't want to be compositional, because these 3D feature maps are not actually the way they are right now, they're not compositional. You predict the whole scene, then it's hard to account for uncertainty. Of course, adding adversarial losses or other ways to allow the network not to predict the mean, the average, which is exactly what happens when you have Euclidean loss, would potentially help, if that makes sense. Another way, which I think it is a very promising direction, is you can still use these 3D inductive biases, but you can still allow the network to go through a compositional type of 3D bottleneck where you have different objects and you have the different background and so on. So if you can go through a scene decomposition bottleneck, potentially you can do way more interesting things. Now, in this work, we hope that first we're going to build a fantastic scene feature map, and then object detection will be much easier, and objects will be easily separable, objects will be easier to track, and so on and so forth.
So you mentioned, so I think still no questions from anyone else, so I can keep asking questions all day, no problem. So you mentioned the uncertainty, which is definitely like a big thing. Like if you want to generate what's on the other side of a table, that's extreme uncertainty about what's there. So you mentioned compositionality, but that doesn't quite get all the way, and like VAEs too. Do you have some ideas about how you can deal with such uncertainty in 3D scenes and stuff like this?
Yeah, I mean, when you're compositional, then for every, let's say, chunk of your scene is easier to manage because it doesn't explode. So you may as well add some latent vectors there and train it in a VA framework. That would be the simplest thing, potentially. Does this make sense? We did try to add a VAE, but we didn't see improvement in the features. Do you see what I mean? Yeah,
so for you, is the most important thing the features, or like potentially the generating the novel scenes like in the NERF? Because you also have some experiments in there in the paper, I think.
Yeah, so the question is image generation the purpose or learning good representations? So actually learning good representations is the purpose, but I think what blows my mind is in Sanya's work, you showed that, look, the more beautiful the image is, the better the representations behind. So I thought that this is, I don't know, at least I believe that people were stuck on this question for a long time, and people were saying, GANs generate beautiful images. What about the semantics? What about the representations? We actually didn't have a big boost. I would say, right, from this type of generative models before. But I see this changing now, okay? So in our work, we saw like by not generating images, but by generating features contrastively, you actually get better more correspondable features, right? And right now, the truth is that, yes, self-supervised contrastive learning is the state of the art on unsupervised feature learning in 2D, so as well potentially in 3D. I mean, there's a lot of domain knowledge in contrastive learning, right? So in contrastive learning, you say, okay, forget about the size and forget about the occlusion and forget about this. You augment all those dimensions and you ask the network to learn a representation that is invariant to all those things that you actually augment. In generative models, you don't have this, right? So the model needs to really, model everything, right? Do you see what I mean? But when it works, amazing levels of detail come out that we humans had not pre-labeled or pre-annotated anyway.
Cool. So I'm going to keep asking questions because we have some more time. So my next question is, so I might have misunderstood something, but my understanding was your model takes in kind of one frame at a time and generates the 3D features from one frame and uses multiple frames for training, but at inference, it just takes one frame.
Right.
So have you looked into or thought about like accumulating those frames over time? Because that seems like a natural thing to do once you have 3D, right? To get more information.
So at just time, you can totally accumulate. Okay, you can totally accumulate. Now, here's the problem. If you want to accumulate, you need to have the way to accumulate. So if you're in a static scene and you know your ego motion, that's what you're going to do. Here, because we were tracking, right? We were tracking. So that's why we didn't know, where the object is going to go. All right. So that's why we unprojected every frame independently and then try to correspond the features of the object we're tracking. Yeah. Does this make sense?
Yeah, so I guess there's multiple ways that one could go about this. So you could have like very late accumulation, like features per frame and try and join them. Or you could also have like very early accumulation, like you only create features after looking at lots of frames. Do you think one direction or the other is going to be more promising?
So, I mean, what I'm looking right now is into iterative architectures that try to iteratively, localize the object and then, featurize and localize the object again and featurize and so on. Right, this is what we're trying to do right now to handle dynamic scenes. The problem with 3D is that once you get things work okay with the cars that actually rigid chunks moving, right? So this is very convenient to model. But once things start deforming, right, like the door of the car opens or the cut starts curling up and so on, and it's not clear how to create correspondable representations. Do you see what I mean?
So I guess like your recent work took motivation from the nerfs that were built on static scene. Now there's some real interesting dynamic nerfs for video that maybe some lessons can be learned there. I think there's lots.
Right, yeah, like some 3D flows that actually, propagate the features and then combine them and so on. Absolutely, yeah, I think that makes a lot of sense. But at the same time, this architecture has solved a lot of problems for us in other domains. For example, for manipulation, you are playing with objects and each time you change viewpoint, the scene looks so different. Well, now that you have a 3D map, then you don't need to worry about the viewpoint. You don't need to worry that an object is seen very partial in the image because you have it there in your map as a whole. Do you see what I mean? It's much easier to predict intuitive physics, to estimate interactions of objects and so on with these persistent representations, let's say.
So is this direction the main direction of your research, or are you also doing research in other kind of directions, or is this kind of like?
Yeah. So by this direction, you mean the 3D feature maps?
Yeah.
I mean, yeah, sure. We're very excited about object permanence. We're very excited about what is the right representation for dynamic scenes and so on. I mean, right now we're trying to encode permanence in a little bit more implicit ways. And yes, we've used these feature maps for perception, for manipulation, for language grounding. Again, language grounding there helps because in these 3D feature maps you have permanence and you have size, and you can, you can map language to the 3D feature map of the scene that the language depicts as opposed to a specific image, right? You can change the scene the way you like. So you can do a lot of, I don't know, interesting, I mean, thanks to object permanence, you can do a lot of things that you could not do using 2D images. But I want to say that we're actively trying to find other ways beyond 3D feature maps as bottleneck to encode things like object permanence and size permanence and so on. But I do think that is very, very, very important for video understanding.
So yeah, okay. I think that's enough questions for me for the minute. So I think thank you very much for your talk. It was super interesting.
Thank you for the invitation.
Yeah, no, thank you again. So that was the last invited talk for the day. So in the schedule, I have now 10 minutes, and there's 8 minutes left for closing remarks. So I don't have all that much to say. I just wanted to again. Maybe I just quickly share my screen to say the last little thing that I wanted to say. 1 second. Here it is. So I just wanted to make sure that I thanked the workshop sponsors again for allowing this to happen, because without them, we couldn't have put on this workshop, and we couldn't have put on this challenge. And again, I wanted to thank all of my co-organizers. Again, when I reached out to them sometime last year wanting to put on this workshop and this challenge, I really appreciate them for supporting me in doing that. And of course, lots of other people to thank, all of the people that presented, all the talkers, all the speakers, all the people that submitted papers, all the people that submitted challenge results. This workshop wasn't about me, it was about all of you sharing and coming together. So thanks again for all of that. I am here for 5 minutes, and I would love it if anybody wanted to just share general feedback on the workshop or anything, but otherwise, or have a chat for 5 minutes. But otherwise, you're all free to go and enjoy your weekend. And I hope you enjoyed the workshop. I enjoyed it. It was long. Oh, Bastian has something to say. Yes.
Yes. On behalf of all the other co-organizers, I wanted to thank you for putting all of this together. I think this was a really great workshop with amazing talks and very, very nice program altogether. And I know this has been a lot of work for you, so thanks for putting in that work.
Yeah, it's been my honor, and thanks for, I guess the last people to thank are all the people for coming. So now it's slowly been a bit quiet. I think we have about 50 people at the end, but at one point there was 130 people at one time attending. So thanks to all of those people. I'm sure in total, when you sum up the people attending, I think maybe 300 plus people would have attended today. So that's very exciting. And I look forward to the next one. I will be hoping to have this again at next CVPR, hopefully in person. And see you all then.
Thank you. See you.
Okay, so I'm gonna end this now, and all of the talks will be available online. Is that okay with you, Katarina, if I post your talk online? Yes, awesome. Fantastic. Okay, so thanks again, everyone, and see you all at the next CVPR in person.
Yep, thanks, bye.